All right, people. I believe everybody is doing great, nice, and absolutely fine. So, welcome to Unacademy NEET English. And today we have the biggest marathon in the game of NEET 2.0 series, okay? That is complete modern physics, complete modern physics. And we say in this particular session, we will be completing the 3 chapters. When it comes to the 3 chapters, the first one you have dual nature of matter and radiations. The second one you have atoms, and then the third one is nuclei. Okay, whatever the topics you have for your NEET syllabus, we are going to understand each and every single thing from the scratch, from the basics. If you have not studied modern physics before, if you are learning it for the first time, I am giving you the guarantee you will be able to understand each and every single point, and you will be able to solve the problems in the upcoming time also. So before that, let me know in the chats if I'm perfectly audible, visible to each and every single student. Everyone means everyone. And most importantly, if you have not liked this session yet, I would want you guys to smash the like button as soon as possible. Smash the like button as soon as possible. Okay? Okay? Great. Okay. Yes, JEE students can also watch this session because I'll be showing you a lot of problems out there. Okay, concepts will be, we say in depth, everything, and it will be to the point. Okay, so that we can finish this particular session in, we say, 10 to 12 hours. Okay, and if you have not liked this session, and I would want you guys to smash the like button as soon as possible. Okay, and let everybody join, and I am starting the session. Let everybody join, and I am starting the session. Okay. Okay, guys. Now. Let's first talk about what are the chapters that we need to discuss. What are the chapters that we need to discuss over here? Okay, what are the chapters that we need to discuss over here? We say the first one that we are going to talk about is, we say, dual nature of matter and radiations. The second one we have over here, that is atoms. And the third one we have over here, that is nuclei. So these are the 3 chapters that we need to finish in this one, from the scratch, from the basics. Now, guys, I hope everybody has joined. Let's start with the first chapter. That is what we call the dual nature of matter and radiations. Okay. Everybody over here, listen to me very carefully. I would want you guys to focus completely over here. Now, the very first thing over here is dual nature of matter and radiations. Before this, let's talk about this light. Okay, we have light. Let's suppose I have got a bulb over here. So we say bulb gives the light. Bulb is a light source. Let's understand that this light over here. We say the question is this light a wave or a particle? I am asking you the simple question. This light, okay? Let's suppose I have got the light source over here. Light source means which gives the light source. Okay? We say the light comes out of this light source. Sir, is this light a wave actually? Is this a wave coming out? Okay. Is this light made up of waves? Or we say this light is a particle, or these are the particles coming out of this light source. Okay. So this was basically the biggest battle between a lot of physicists back in time. Okay. And then, my dear friends, few of the scientists like Newton, they came up with the conclusion. They said light is a wave. According to we say Newton, they said light is a particle. They said light is a particle. According to the Newton, they said light. And other physicists also supported him, said yes, light is a particle, because he gave many proofs out there. And then there was another physicist, his name was Huygens. Okay, his name was Huygens. He said this light is a wave. He said this light is a wave. It is basically wave coming out of this light source. Okay. So many number of people out at that point of time didn't believe him, because he wasn't that big scientist as when we talk about the Newton. Okay. Then afterwards, there was an experiment which was done. That is what we call the YDSE, Young's double slit experiment. You might have heard about YDSE. We said this YDSE clearly proves that light is a wave. Okay. Now from this onwards, people started believing that yes, this light is a wave. This was the strong proof that light is a wave. And then again, my dear friends, I would want you to focus over here. Then again, we say Einstein came and he performed this photoelectric effect experiment. And this photoelectric effect experiment completely proved that light is a particle. Light is a particle. So light is made up of particles. What is the strong proof for this photoelectric effect? Light is a wave. We say there is a strong proof, that is YDSE. So finally, my dear friends, now I would want you guys to focus over here. Finally, we came up with the conclusion. We say this light has dual nature. Okay. So light behaves like a particle. Light behaves like a wave. It depends upon the surroundings. Like when we talk about the Young's double slit experiment, in that case, we have to study this in the detail in the upcoming time. Here I say light behaves like a wave. And when it comes to the photoelectric effect, here light behaves like a particle. Guys, the amount of detail I say, just keep remembering that. Okay. Don't ask me, sir, where does that come from, this come from? You guys are NEET aspirants. You have to get 180 out of 180 in your NEET physics. So the detail I'm saying, just keep that in your mind. Okay. So we say this was the strong proof for wave. This was the strong proof for particle. So finally we said light is a particle. So when it comes, light is particle as well as wave. When it comes to, my dear friends, listen to me very carefully. When it comes to dual nature of matter and radiations, here we have to study photoelectric effect in detail. It is all about photoelectric effect. So we say in modern physics, in this dual nature of matter and radiations, guys, I would want you guys to listen over here. We say here we consider light as a particle. Like tomorrow, after few days, when we will move on to the wave optics, over there I'll tell you we have to consider this light as a wave. Okay, I'll be saying if light is falling on something, it is wave falling. Here I'm saying if light is falling on my hand, means these are the particles falling. Okay, so in this chapter, we will consider light as a particle. From now onwards, you'll remember one thing, that what is light is made up of particles. Okay, now my dear friends, I'll just write the first point over here. What is that? We say light is made up of small, tiny particles. Light is made up of small, tiny particles called photons. We say light is made up of small, tiny particles which are called photons. We say if this is the light coming out of the light source, we say these are what we call photons. Okay, these are what we call photons. So if I say this is a bulb over here, from the bulb we say light is coming out. This light is falling on my hand. So I can say these are the photons falling on my hand. As simple as that. As simple as that. Okay. Now, my dear friends, we say, since You might have heard this also. If I say light is falling on my hand, you say, sir, this is energy falling on my hand. So I can say this light is made up of photons. So these photons will have the energy. So we say these photons are also called packets of energy. Packets of energy. Yes. So as of now, I told you about the light. Sir, what is light? Light is made up of waves. Light behaves like a wave also. Light behaves like a particle also. It depends upon the surroundings it is interacting with. When we talk about YDSC, over there it behaves like wave. When we talk about photoelectric effect, over there it behaves like a particle. Okay? And sure, in this chapter, we'll have to study photoelectric effect. So here it will behave like a particle. So here simply we consider this as a particle. And my dear friends, we say these are the small tiny particles called photons. And photons have got the energy because light has energy. So photons have got the energy. Please tell me in the chats till over here, is this crystalline clear? The basic theory. Is this crystalline clear? I would want you guys to tell me in the chats. Is this crystalline clear? Okay. Now, let's move on to the first topic that we have in this one. This is actually the first topic. That is energy of a photon. We'll be talking about the intensity also. Wait. Let's talk about the intensity, this energy of a photon. Now, guys, since you said photon has energy, how much energy it actually has? See, guys, when it comes to energy of a photon, I say, energy of a photon is simply, we say H multiplied by F. When Planck's constant, what is this H? H means Planck's constant. When Planck's constant is multiplied with the frequency, it forms what? Energy of a photon. Sir, is there any proof for this? There is no proof for this. No proof was given for this. So I'll just directly write when Planck, H means Planck's constant. When Planck's constant is multiplied with frequency. When Planck's constant is multiplied with frequency, it gives energy of light. Energy of light. Okay? So simply from now onwards, F is frequency, H is Planck's constant. So, my dear friends, listen to me very carefully. When it comes to this frequency, what is this frequency? Frequency means number of cycles per second. Okay? Like, let's suppose I have got a wave over here. This is the wave. I would want you to focus. Okay, this is the wave. And could you please define, sir, one cycle of the wave? One cycle means from here till here. This is one cycle of the wave. And one time period means from 0 to capital T. How much time it is taking to complete this one cycle. So how many number of cycles, if you take the area over here, how many number of cycles will cross in 1 second? That is the frequency. Okay? Number of cycles per second. Now, guys, I would want you to focus exactly over here. We say this frequency is further equal to, we say, C divided by lambda. Just remember whatever I keep telling you over here, okay? Just remember whatever I keep telling you over here. We say this frequency is further equal to C by lambda. If we put it over here, we say this energy of light will come out to be, that is Hc divided by lambda. That is Hc divided by lambda. Okay? And what is this lambda? Lambda is what we call the wavelength. Lambda is what we call the wavelength. I'll make you understand everything. And what is this H? H is Planck's constant. Planck's constant. Okay? And what is the C? C is speed of light. Speed of light. Speed of light. Okay, c is speed of light. Now guys, furthermore, we say when it comes to the value of h, we say it is 6.6 into 10 raised power minus 34, we say joule second. This is the value of Planck's constant. And when it comes to the speed of light, this is 3 into 10 raised power 8 meter per second. This is the speed of light. Okay. Now what if you put these values in this equation over here? So can I write? So we can write over here energy of a photon will come out to be. What is the value of Planck's constant? That is 6.6 into 10 raised power minus 34. Okay. And when it comes to c, speed of light, that is 3 into 10 raised power 8 meter per second. And then we say divided by lambda. Now guys, when you multiply this with this, what you will get is that you will get energy is equal to 2 into 10 raised power minus 25 divided by this lambda. And this is the energy of a photon in joules. And this lambda is what we call the wavelength, and we measure the length in, we say meters, we measure the length in angstrom, nanometers. So this is the wavelength over here in meters. So I'll just write over here, this is the energy. This is the energy of a photon. This is the energy of a photon. In joules. Okay. This is the energy of a photon in joules. And lambda is in meters. Okay. So as of now, we got three equations of energy of photon. The first one is h into f. Second one is hc by lambda. And then you have this detailed one, that is 2 into 10 raised power minus 25 divided by lambda. Now guys, we say when it comes to the energy, see, you say mass. If I say, sir, this is the box over here, its mass is 1 kgs. You can also say its mass is 1000 grams. Okay, you can measure the mass in different units, in kgs, in grams, it's one and the same thing. But similarly, you have got the energy over here. You can measure the energy in joules also. You can measure the energy in electron volts also. Here, usually the energy of photon is less, so we measure it in the electron volts. Okay, so we say here, we usually measure the energy in electron volts. Here we usually measure the energy in electron volts. So this energy is given in joules. We have to find the energy in electron volts. Yes. Now guys, remember, like you say 1000 grams is equal to 1 kg. Similarly, you say 1 electron volt, okay? 1 electron volt is equal to 1.6 into 10 raised power minus 19 joules. This is the value of 1 electron volt. Electron volt is also the unit of energy. Joules is also. Now, can you find the value of joule over here? This J, so from this we can say 1 joule will be equals to. That is 1 EV divided by 1.6 into 10 raised power minus 19. I can write it something like this. Yes. Now guys, tell me one thing. This is the value of 1 joule. Now put this 1 joule over here. I would want you guys to put this in the equation first. Okay. I say put in equation first. So you'll say this energy of a photon will be, that is 2 into 10 raised power minus 25 divided by, we say lambda. Okay. And instead of this joule, you will be getting 1 EV divided by, we say 1.6 into 10 raised power minus 19. Okay. Now, my dear friends, I can say over here, while you solve this, I'll say on solving this, guys, focus over here. We'll get the energy of a photon as 12400. divided by lambda. This energy will be in the electron volts, and when you consider lambda in angstrom. So angstrom is also the unit. Yes, angstrom, in angstrom we measure the length. Length is 4000 angstrom, something like that. Okay, this will be the energy of a photon in electron volts. But when you consider this lambda in angstroms, after doing the calculation, you get this. Also, we say we'll get the energy of a photon as 1240. Here, 1240. Okay, divided by lambda. This is also the energy in electron volts. But when you consider the lambda in nanometers, I'll give you the proper feel of both of these two equations. So as of now, we got how many equations of energy of photon? 1, 2, 3, 4, 5. Okay. So this is the energy of a photon in electron volts, but when lambda, its wavelength is in angstrom. This is the energy of a photon in electron volts, but when lambda is in, we say nanometers. When lambda is in nanometers. Yes. Now guys, let's suppose, now take the feel of these two equations. See. And how do we exactly get it? On solving this, you can get this and this. Now see. What I'm saying is that, let's suppose we have got a photon over here. Okay. This photon is falling. And I'm saying wavelength of this photon is, let's suppose, 4000 angstrom. 4000 angstrom. Okay. I'm saying find energy of a photon in electron volts. Now, when you have a question something like this, lambda is given in angstrom and energy you guys are supposed to find in electron volts, what will you do? You'll say, sir, energy will be 12400 divided by lambda in angstrom, and energy is in electron volts. And I can say over here, E is equal to 12400 divided by, instead of lambda, you'll be putting over here, that is 4000. It'll come out to be approximately 3.1. So directly, and if I say, my dear friends, I have got a photon over here. This photon has got the wavelength of 310 nanometers. This photon has got the wavelength of 310 nanometers. And I'm asking you, find energy of a photon in electron volts. What will you do in this particular case? Sir, I'll be using the formula E is equal to 1240 divided by lambda in nanometers. And this is in the electron volts. That's what I was explaining. I'm saying use this equation when lambda is in nanometer. Use this equation when lambda is in angstrom. So I can say in this particular case, so this will come out to be, that is 1240 divided by, when it comes to the lambda, so this will be 310. Solve it and you will get the answer. Okay. Is this clear? Is this clear? Tell me, guys. Everybody out there. Now, guys, and if somebody wants you to find the energy of a photon in joules, okay, and lambda is in meters, then you'll be using this equation. Now, let's move on to one more question. Let's suppose we have got a question over here. What is the energy in joule associated with a photon of wavelength 4000 angstrom? The question says that we have got a photon over here, and its wavelength is given as 4000 angstrom. We have got a photon over here and its wavelength is given as 4000 angstrom. Yes, absolutely cool. And we are supposed to find energy of a photon, okay? In joules, we are supposed to find the energy of a photon in joules, and let's find an electron volts also, and in electron volt, EV also. Right? See. Whenever you have to find the energy of an electron in electron volts and lambda is given an angstrom, guys, see, I'll be using E is equal to 12400 divided by lambda, and this lambda is in angstrom, this energy will be in electron volts. So I can say over here, this will be 12400 divided by, what is the value of lambda? This will be 4000. Okay, and this will come out to be approximately 3.1 electron volts. Cool? Yes. Now guys, we have to find the energy in joules also. Guys, see. To find, we say energy in joules. To find energy in joules, we say energy of a photon will be, that is 2 into 10 raised power minus 25 divided by lambda, and this is in joules, this is in meters. This is the formula. This is the formula. Now guys, I can say over here energy of a photon will be, I'll write over here 2 into 10 raised power minus 25 divided by, what is the value of lambda? Guys, if we talk about this is in the angstrom, you have to convert this in the meters. Always remember, we say 1 angstrom is equal to 10 raised power minus 10 meters. Always remember 1 nanometer is equal to 10 raised power minus 9 meters. Now, if you have to convert this 4000 into the meters, what will you write? 4000 into 10 raised power minus 10. As simple as that. And this will be the energy of an electron in joules. Please tell me in the chats everything is crystal and clear till over here. Please tell me in the chats everything is crystal and clear till over here. Okay? Okay? Yes. It will be simply over here. That is energy of a photon is 0.5 into 10 raised power minus 18 joules over here. 0.5 into 10 raised power minus 18 joules over here. Now guys, let's move on to, I hope you got the crystal clear feel of how do we find the energies, okay? Now guys, listen to me very carefully. Listen to me very carefully. Energy of a light. See, let's suppose I'm taking a light source over here. This is the light source. I'll say this is the light source. Okay. And we say light is exactly coming out of the light source. Light is exactly coming out of the light source. Light is exactly coming out of the light source. Okay. My dear friends, can I say this is the light coming out of the light source? This is the light. And when it comes to the light, is light made up of one photon or many number of photons? We say many number of photons. So we say this light, either you say light or you say n number of photons. N number of photons. Yes. Now guys, I can directly write in this particular case, we say, if we talk about the energy of light, can I say, if you find the energy of n number of photons, that will be the energy of light, as simple as that. So you say energy of light is energy of n photons, because light itself is made up of n photons. And so I can say, what is the energy of one photon, guys? That is h into f. What will be the energy of two photons? 2hf. What will be the energy of n photons? nhf. So I can say that will be n, h, and that is f. So this is the energy of light over here. Or you can also write it. You can also write it in this particular case. E is equal to, that is n, h, c divided by lambda. And sure, you can find this, sir, n will be equals to this. N means the number of photons. So I can say this n will be equals to, take this lambda over here, okay, or from this also. I'll just write over here, guys. We say as when it comes to the energy of light, you say that is nh into f. If somebody asks you to find the number of photons, you'll simply say number of photons will be E divided by h into f. Okay, so this will be the number of photons, or directly from this also you can calculate. So n will be equal to E divided by lambda upon hc. Here also you can write where n is the number of photons, as simple as that, where n is the number of photons. Now let's suppose the question over here is find the number of photons in 6.63 joule of radiation energy. It is saying that you are given a light over here, this radiation light is falling, and energy of light, energy of radiation is given as 6.63 joules. Okay, and frequency in this case is given as 10 raised power, we say 12 hertz. 10 raised power 12 hertz. Okay, and you are supposed to find what? You are supposed to find number of photons. Find the number of photons. Can I say in this particular case, as we recently saw, energy of light is simply, that is NH into F. Yes. So if we find this N over here, this will be energy divided by H into F. And I can say this N is equal to, what is the value of energy that is given? That is 6.63 upon, what is the value of H? Planck's constant. We say it is 6.6 into 10 raised power. We say 6.63 actually. 6.63 into 10 raised power minus 34. Okay. And multiplied by 10 raised power, we say 12 in this particular case. Okay. Okay. Now, if you solve it, it will come out to be this, and this will cancel. 34 minus 12, it will be minus 22. It will go in the numerator. It will become 10 raised power, we say 22. So number of photons in this particular case came out to be 10 raised power 22. Number of photons per second we'll see after some time. Please wait. Please wait. Okay. Is this clear? Now guys, see, okay, this is the question on momentum. First we have to understand the momentum. Okay, cool. Let's now talk about the momentum of a photon. Guys, see. When it comes to the momentum of a photon, we say as. Guys, you might have seen, you might have studied in your mechanics, if we have a particle, its mass is m, and it is moving with a velocity v, we say it has momentum. Momentum is equal to mass into velocity. Okay, this is the general formula how we write the momentum. Okay, in case of a particle of mass and velocity v, more is the mass, more will be the momentum. Now, when it comes to the momentum, what does momentum actually, what is the value of momentum? Guys, see. We say momentum here is, we say P is equal to H divided by lambda. What is H? H is Planck's constant. Lambda is wavelength, or you say de Broglie wavelength. We say this H is Planck's constant, and this is, we say, wavelength over here, wavelength. So what I'm trying to say is that when Planck's constant is divided with wavelength, de Broglie wavelength, it gives the momentum of a photon. Is there any proof for this? There is no proof for this. Okay. So we say directly you have to remember momentum of a photon is H divided by, we say, lambda. Yes, absolutely clear. Now guys, we say as we know, what do we know? We say energy of a photon is Hc divided by lambda. This we have studied recently. Now, instead of this H divided by lambda over here, can we put P? Yes. So I can write E is equal to P into C. We can say energy of a photon is simply P into C. And what is this? I can say this is the relation. This is the relation between, I can say, energy and momentum. This is the relation between energy and momentum. Now guys, one more thing I just want to tell you over here. Again, when it comes to the energy of a photon, we say this is hc divided by lambda. Okay. And one more thing, when it comes to the momentum's normal basic formula that you have studied in mechanics, we say momentum is mass into velocity. Yes. And here, momentum of a photon is, we say mass of photon into velocity of photon. Guys, what will be the velocity of photon? What will be the velocity of photon? We say, sir, photon means light. What is the speed of light? So whatever is the speed of light, same will be the speed of photon. Why? Because light itself is made up of photons. So whatever be the speed of light, same will be the speed of photons. So this will be m into c. So I can say in this particular case, this will be m into c, and this c over here, and this c becomes c square. Now, don't you think one c and this c will cancel? Okay. So this mass comes out to be equal to, that is h divided by lambda c. Okay. Sir, what is this? What is this? What is this? We say this is the moving mass of a photon. This is the moving mass of a photon. This is the moving mass of a photon. Sir, what does moving mass mean? Means if a photon is moving, photon is always in motion. Whatever is its mass in motion, that will be the moving mass of photon. Sir, what about the rest mass of photon if you bring the photon at rest? Not possible to bring the photon at rest. So we say rest mass of photon we consider 0. A rest mass of a photon is 0. Some books write rest mass of the photon is not defined. Okay, whatever you take it. Okay, so this will be the moving mass of photon, and rest mass of the photon is 0. This is the relation between energy and momentum. This is the momentum of a photon. Yes. Now guys, one more thing. What is that? That is when it comes to this photon, we say photon is a chargeless particle. Sir, what does chargeless particle actually mean? Means it does not have any sort of charge. Okay. So if we place, guys, we have studied if this is an electric field. If you place a charge in this electric field, we say force will act on it and it starts moving because of that force. But when it comes to the photon, it does not have charge. So if you place the photon in electric field or the magnetic field, no force will act on it. It will not deviate. So we say electric field and magnetic field, just directly remember it, does not deviate the photon. Why? Because charge is equal to 0. Because photon is a chargeless particle. Okay? Great. Guys, I would want you guys to smash the like button if you have not liked the session yet. Cool. Now, guys, a momentum of a photon of wavelength this much. You're given a photon over here. This is the photon. And its wavelength is given as how much? We say 5,000 angstrom. 5,000 angstrom. And if you convert this into the meters, how do you write it? You'll write it 5,000 into 10 raised power minus 10 meters. So 1 angstrom is 10 raised power minus 10. And my dear friends, when it comes to the momentum, you say simply that is h divided by lambda. H divided by lambda. So you can write over here, this momentum will come out to be, what is the value of h? 6.63 into 10 raised power minus 34 divided by, when it comes to the value of this lambda, it is 5,000 into 10 raised power minus 10, and solve it, get the answer. This is the how we find the momentum, because you have to convert this lambda into the meters over here. This is in the meters. Okay, now guys, one more important thing over here is, that is power of light. Guys, give me the signal in the chats if everything is crystalline clear with the fire emojis. With the fire emojis and heart symbols. Heart emojis and fire emojis. Everybody in the chats. I'm waiting for your signal. Everyone means everyone. Somebody is sending directly HEART, heart. But I cannot find the heart over here. This is heart from my side. HEART. Okay. Even somebody is writing fire emoji nahi mil raha. Fire emoji, I'm not getting fire emoji. I can't find it. Okay, great, great, absolutely great. Now, let's talk about the power of light. Now see. My dear friends, let's suppose I say, I have got over here two bulbs. This is the first bulb. Okay, this is the first bulb. This is B1. And let's suppose I have got another bulb over here. This is the another bulb which is connected over here. This is B2. So we say, what is bulb? Bulb is a light source, okay? Bulb is a light source. Bulb gives us light. So light comes out of the bulb, okay? And I'm saying this is the light comes out of this bulb. This is the light coming out of this bulb. Guys, focus completely over here. This is the light coming out of this bulb. This is the light coming out of this bulb. Yes. Absolutely cool. Okay. And when it comes to this bulb, this is the light. And why do you show it with these dots? Because we consider the light as a photons over here. So this is the bulb, light coming out of this bulb. This is the light coming out of this bulb. Light coming out of this bulb, light coming out of this bulb. If I ask you the question, sir, this is the light, means if this is the light, okay, means this is energy coming, this is light, this is photons, means this is energy coming out. Okay, what if I ask you in this particular case, in which bulb? Okay, tell me, what is the difference between this bulb and this bulb? What is the difference between this bulb and this bulb? What is the difference between this bulb and B1 and B2? We say from B1, more number of photons are coming out. Okay. Yes. From B1, more number of photons are coming. Density of the photons is large over here. Okay. So I say, when it comes to the bulb B1, we say in B1, or we say from B1, more energy slash photons is coming out every second. Okay. So we say, so I can say power of B1 is greater than power of B2. Power of B1 is greater than power of B2. What is power? Power means how much amount of energy the light source is giving every second. This is giving more energy every second. This is giving less energy every second. So this power is simple, bro. I've got the two bulbs over here. This is having the 100 watt power. It is giving you 100 watt. This is giving you, sir, 50 watt, 20 watt only. Sir, this bulb is giving a lot of energy every second. This bulb is giving less energy every second. So power of this bulb is less than, power of this bulb is greater than power of this bulb. So how much amount of energy is coming out every second? How many number of photons are coming out every second? So I can say, so power is defined as energy falling per second. How much amount of energy is falling every second? How much amount of energy is coming out every second? So I can write the power in this particular case as power is, we say, energy energy upon time, energy upon time. Okay, energy upon time. And when it comes to the power, what is energy, guys? Energy of light, you can say that is NHF divided by, we say, T. Okay, even you can write it, guys, over here, even you can write it something like this. Power is equal to, that is NHC divided by lambda into T. This T is the time. So power is NHF divided by T. NHC by lambda into T. This is also power, that is also power. And my dear friends, even you can find one more thing also over here. Why? Because NHF is energy. Even you can find one more thing also over here. We can say also, when it comes to this N divided by T, what is this N divided by T? Or N divided by T from over here. You can say N divided by T. This is number of photons per second. So you can write this as, take this lambda over here. This will be P divided by lambda upon HC. So you can keep this in a box. You can keep this in a box. Okay. So what is this? Where N by T is the number of photons per second. Means how many number of photons are falling every second. That is what we call the P lambda upon HC. So simply, power means how much energy is coming out every second. Energy upon time. That's how we define power. Okay. And guys, the notes of this PDF or every single session or any important update will be in the Telegram channel. I hope you have joined my Telegram channel previously. Okay, that is t.me/Yawar Manzoor. Okay, so this is my Telegram channel. You can join it. Over here, we put up all the notes, whatever you have, every single detail we put up here only. t.me/Yawar Manzoor. t.me/YAWARMANZOR. You can search it on the Google and you will reach it onto this. Okay. Next. Let's do one thing. Let's take a look at this question. Let NR and NB respectively be the number of photons emitted by a red bulb and blue bulb. Now guys, let's suppose we have got the two bulbs over here. I'm taking two bulbs over here. Red bulb and blue bulb. This is red bulb. Okay, this is a red bulb. This is a red bulb. And this one is blue bulb. This one is blue bulb. Okay. Now, I say photons are coming out of this blue bulb. Understand carefully this question, guys. Photons are coming out of this blue bulb because it is sending light. And photons are coming out of this red bulb. Photons are coming out of this red bulb. Okay, yes. And how many number of photons? It says NR. NR is the number of photons coming out of the red bulb. And when it comes to the number of photons of blue bulb, that are NB. Okay. Respectively emitted by the blue bulb and red bulb of equal power. And it says power of red is equal to power of blue. Whatever the energy per second this is giving, same energy every second this is giving. So power in both the cases will be same. Then which will have more number of photons? Okay, which will emit more number of photons? You guys are supposed to tell me in this particular case, which will give, if this is a blue bulb, this is a red bulb, blue bulb, which bulb is sending more number of photons? Is NR more or NB more? Is NR less or NB less? So power of both is equal. Now guys, see, how do we solve it? We say when it comes to the power, what is the formula of power? We say formula of power is NHF divided by T. This is the basic formula. So I'll just write over here, this is NH, I'll write something like this, NHF divided by time is equal to NHF divided by time. Now when we talk about the red bulb, so means number of photons of red, frequency of red. When we talk about the blue bulb, number of photons of blue, frequency of blue. Sir, time and time will be same for both. And Planck's constant and Planck's constant will be same for both. You can say H cancel, T and T cancels. So here, NR and FR is equal to NB and FB. Means, guys, product of these two quantities, N and F, number of photons and frequency, is equal. These two product of these two is equal to product of these two. Now, remember one thing. We say as. Always remember frequency of red is less than frequency of blue. Here, this quantity is small, frequency of red. Here, this quantity is large. In order to be them equal, we say number of photons of this red has to be more. So, NR has to be greater than NB. Why? Because then only they will become equal. If you say, sir, FR is less, NR is also less, so this will become less, this will become more. So how is it possible they will become equal? No. So if one quantity is small, another quantity has to be large. So then only their product will come out to be equal. So NR is greater than NB. So this will emit more number of photons. Next, gentlemen, we have got this one. If the power of light is 10 kilowatt, okay? If the power of light is 10 kilowatt, kW, okay? If the power of light is 10 kilowatt, wavelength is 310 nanometer. Wavelength is 310 nanometer, okay? Find the number of photons per second. You guys are supposed to tell me what is the number of photons per second. Recently, I told you, what is the formula for number of photons per second? N by T, P lambda divided by HC. Directly we'll be putting up over here. So we say as number of photons per second is equal to P lambda divided by HC. Please tell me the answer of this in the chats. Okay. Yes, this is 300 nanometer. Sorry. 300 nanometer. 300 nanometer. Please tell me the answer in the chats. Everybody, everyone means everyone. I have given you the formula. Just you have to apply the values and get the answer. Okay? Okay? Tell me, guys. We say number of photons N divided by T per second. What is the value of P? 10 kilowatt. Okay? So this will be over here 10 raised power 4. And lambda. This is after converting into the watts over here. And what is the value of this? I can write over here, this is 300 into 10 raised power minus 10. Okay, divided by H into C. What is Planck's constant? Planck's constant is 6.6 into 10 raised power minus 34. Okay, multiplied by speed of light, 3 into 10 raised power 8. Guys, always remember from now onwards, value of HC directly, that is 2 into 10 raised power minus 25. Always remember this value from now onwards directly. Okay, now solve it and check the answer. Okay, calculation I am putting on you guys. Next, you have got this. In a monochromatic source of light, as of now, ignore this monochromatic, okay? When we move on to the wave optics, I'll explain over there, okay? We say, if we have a light source operating at 200 watts, means light source operating at 200 watts means if this is the light source and its power is given as 200 watts. That is what is meaning of this one. We have a light source. It is giving you the power of 200 watts. Emits 4 into 10 raised power 20 number of photons per second. This is the light source over here. This is the light source over here. See guys, something like this. This is the light source over here. It is giving the light, it is giving the photons. And how many number of photons per second? So we say N by T in this case is given as 4 into 10 raised power 20 photons per second. Find the wavelength of the light. You guys are supposed to tell me what is lambda. What is the value of lambda? Don't you think this is easy? extremely easy. It is like pure butter. See guys, we say as when it comes to the power, you simply say that is NHC divided by lambda into T. This is the formula of power. Find lambda over here. Lambda will come out to be that is NHC divided by, take this P over here. This will be T and this is lambda. Now value of N by T in this case is given. You can say, sir, this lambda will be. What is the value of N by T? You can write 4 into 10 raised power 20. It is directly the value of N by T. What is the value of HC? I told you value of HC. This multiplied by this is 2 into 10 raised power 25. So 2 into 10 raised power 25. Okay. And divided by in this particular case. Okay. This is not lambda. Lambda we took over there. This is power. NHC divided by PT. Okay. And what is power? Power in this case is given as 200. Okay. Solve and get the answer. Let's move on to the next topic. That is what we call the intensity. Guys, smash the like button if you have not liked the session yet. Okay. Let's now. Okay. There is a great comment. Okay, I just want to read it. I know somebody is writing over here. I know I'm being selfish. But feeling bad for those who are not watching this amazing lecture. We are the one gonna score 180. Right, guys? Absolutely right. Magnetism will be posted by tomorrow or day after tomorrow. Now, guys. Intensity of light. Let's take a look exactly over here. My dear friends, let's suppose I take once again the two light sources. This is the first bulb over here or the light source, whatever you call it. Okay. And this is the second bulb over here. I'm taking in this particular case. Okay. This is again B1. This is again B2. And we say photons will come out of this. Now I'll make it something like this. These are the photons coming out of this bulb. These are the photons coming out. And these are the photons coming out of this bulb. Now, my dear friends, in this particular case, let's suppose I'll place a sheet over here. I'm placing a sheet over here. This is the sheet I'm placing over here. Don't you think that these photons, this light falls onto this sheet? These photons, this falls onto this sheet? Yes. Now, I'm saying take a unit area in this particular case. Take a unit area in this particular case. Okay. This is the unit area. Okay. This is also what? Unit area. I'm asking you the simple question over here. What is that? If somebody asks you, on this unit area, let's suppose A, and this is unit area B, I can say on unit area A, more number of photons are falling every second. Do you believe that? Yes, sir. I can say over here as on unit area A, more number of photons are falling every second. Okay. On unit area A, more number of photons are falling every second. And on as compared to B. So can I say, guys, I'll just write over here. So intensity at A is more as compared to B. So here intensity is more, here intensity is less. What is actually intensity? Intensity is number of photons falling every second on unit area. If you have to take the area over here, sir, this is the area. If you increase the area, then it is different. We say, let's suppose I'm taking unit area. So we say, sir, photons are falling, more photons are falling. So if more photons are falling, sir, energy will be more, power will be more. Yes. So if power is more, we say intensity is more. So I can say definition. So intensity is defined as energy falling per second, per unit area. So how do we write it exactly in the mathematical form? So I can say intensity will be simply energy falling per second, energy upon time per unit area multiplied by the area. So you can say this intensity is also energy upon time is what? Power. You can also, it is power into a power by area, power divided by area. And you can also say we can say also, when it comes to the intensity, you can say intensity. When it comes to the energy, you say this is NHF divided by, energy of light is NHF divided by, and we say area and we say time. This is the formula for intensity. Even also you can write it something like this. Sir, intensity will be simply, that is NH, instead of F, you can say C by lambda. So it is NHC divided by lambda A into T. So this will be the value of intensity exactly over here. This will be the value of intensity exactly over. That is NHC divided by lambda AT, NHC divided by lambda AT. Okay. Okay. Cool. Okay. Next. So what is intensity? The amount of energy falling per second per unit area, or power per unit area. Directly also you can say it something like that. Power per unit area also. Now guys, I would want you guys to focus exactly over here. See. One more thing. This is important that I'm gonna say right now. See, when it comes to the intensity, look at this formula. You see, if I say, consider the unit area over here, here unit area, means in both the cases, you are keeping the area as constant. Yes, sir. This is the light coming out of these light sources. We say, sir, this light source. Unit area. Whatever the area you are taking over here, same area you are taking over here. So area is constant. We say here, if we take same area. Okay. So we say, and when it comes to area becomes constant. When it comes to time for both is same. So we can say area, time, and this Planck's constant and this Planck's constant h, this h are constants. So can I say then this intensity depends upon, it is directly proportional to number of photons, and this intensity depends upon the frequency. Yes, sir. I am saying you have got the two sources over here. Here you are taking area 1 meter square. So area becomes constant for both. Time, sir, time is 3 seconds. 3 seconds, time is constant. H is Planck's constant. So intensity only depends upon N and F. So intensity is directly proportional to N. Intensity is directly proportional to F. So means if you increase, guys, if you increase the number of photons, intensity will increase. If you increase the frequency, intensity will increase. But if we talk about for a given source, given source. Okay, given source means one source. Sure, you have got two sources. Let's suppose you are taking only one source and the light falls on this one, light falls on this area also. In that particular case, we say this frequency also we take as constant. Why? Because we say frequency depends upon the source. This will have another frequency. These photons have another frequency. If you are taking one source, given source, in that case, frequency will also become constant. If frequency also becomes constant, then we say intensity only depends upon number of photons. Then intensity only depends upon number of photons. Please tell me in the chats, how many of you understood this? Okay. How many of you understood this? Please give me the signal in the chats. If you are taking one source, then frequency also becomes constant. We say, in this particular case, we say, because frequency depends upon the source only. Okay? If you are changing the source, frequency will change. If you keep one source, frequency will be same. So, and. Also remember this, frequency does not depend upon, frequency does not depend upon the distance, from the source. Okay, because we say frequency does not depend upon the distance from the source. And what does that mean? If this is the source, if you are saying, sir, photon is leaving from the source at R1 distance, what is the frequency of the photon? Whatever is the frequency of the photon, same frequency will be at R2 distance. This is R and this is 2R. So whatever is the frequency at A, same will be at B. I can say frequency at A divided by frequency at B will be 1:1. Why? Because frequency does not depend upon the distance from the source. Even if you send this photon in water, in some other medium, its frequency will remain same. Frequency only depends upon the source. If you keep the stronger source, maybe frequency will change. If you keep the same source, frequency will remain the same. I hope, ladies and gentlemen, this is crystal and clear. Now, guys, take a look at this question. If the intensity of light is doubled, then the number of photons will be, see. What will I do over here? I say, as when it comes to the intensity, you say simply NHF divided by A into T. Okay. What did I tell you? That is H, A and T are constants. You are taking these as constants. Okay. Because nothing is mentioned about these things over here. Yes. When you see in a question, nothing is mentioned about area, time, something like that. You take these constants. And is there anything about the frequency? No. So here you take frequency also constant. When nothing is mentioned about the frequency also, you take frequency constant. So we say here intensity only depends upon number of photons. So if intensity is doubled, number of photons will be doubled. As simple as that. Next, take a look over here. Guys. If the intensity of light and frequency both becomes double. In this case, it is saying that in this case, intensity is doubled. It says frequency is doubled. Okay, both. What will happen to the number of photons? Guys, tell me one thing. We say as intensity is equal to N H F divided by A into T. A, T, H is constant. So I can say intensity is equal to N and F. So here they have mentioned the frequency. When they talk about the frequency in the question, means you'll have to consider that. Okay, when they do not say anything about the frequency in the question, you consider the frequency as constant. So I can say here number of photons will be I divided by F. Now if they are saying n is, if they are saying I is doubled, so it becomes 2I. If they are saying frequency is doubled, it becomes 2F. 2 and 2 will cancel, so it will be I by F only. And what is the value of I by F? That is n. So n dash will remain n only, so it remains the same, it remains unchanged. Is this crystalline clear, ladies and gentlemen? Okay. Great, great, great. Next, let's talk about this question. Let's talk about this question. When the intensity of light source is increased, okay, the number of photons emitted by the source in unit time increases. Guys, see. Here it says that, in the question it says that intensity is increased. It says that intensity is increased. What does increase in intensity mean? And nothing they are talking about nothing is mentioned about the frequency. If intensity is increased, we say so means number of photons is increased. So number of photons is increased. Okay. If number of photons are increased, the total number of photons by the, okay, directly, yes, correct. A is correct. Let's talk about B. Total energy of photons are increased. If number of photons are increased, guys, we say as. Second, let's check for the option second. I'll just say, if n is increased and we say energy of light is NHF. If n is increased, we say energy of light is increased. So if energy of light is increased, I can say over here, total energy of the photons per unit time also increase. Energy of light increase. B is also correct. What about C? More energetic photons are emitted. What does that mean? More energetic photon means the energy of one photon is also increased. Energy of every single photon is increased. Guys, see, we say as. Let's talk about the third option. We say energy of one photon is H into F. So if you increase frequency, we say energy of photon will increase. If you increase frequency, energy of photon will increase. But if you increase or decrease the number of photons, nothing is going to happen. So energy of photon depends upon frequency. So we say this is wrong. This is wrong. Okay, because energy of one photon does not depend upon number of photons. Faster photons are emitted. What does faster photon mean? Photon moves with the speed of light only, na? Do you think it is possible that something will move with a greater than speed of light? No. So it will only move with the speed of light. This faster photons are emitted is wrong. Okay. So A and B in this case is correct. Let's talk about this one. Find frequency of A by B, FA by FB. Okay. IA by IB. Ratio of photons per unit time, per unit area also. Okay, very important question. I would want you to listen to me very carefully. You have got the source over here, and we say from the source, we say photons are coming out. So it reached, we say, point A, okay, which is at R distance. And it reached then point B, which is at 2R distance. I am asking you, what is the frequency of photons at A, and source is 1 only? What is the frequency of photons at B? Clearly, I can say frequency at A divided by frequency at B is 1:1. Why? Because I recently told you frequency does not depend upon the distance from the source. Okay? Yes. Yes. Okay. Let's talk about the intensity. Guys, now you have to focus over here. This is a source. When we talk about the intensity, we say intensity is equal to NHF divided by A into T, A into time. Guys. We say, let's suppose this is I told you when you consider area as constant, then frequency does not depend upon it. But if you are talking about the source over here, please look at me. If this is the source, we say this is a unit source. This is a ball over here. Okay, ball is glowing. Now tell me, sir, if you go at r distance, don't you think that here intensity of light will be more at r distance? Intensity of light will be more. If you go at 2r distance, I can say intensity of light at 2r distance is more. Yes. Sorry, less. Because, see, guys. This is the bulb. Sir, at this distance, large intensity, large, we are getting so much of brightness. And if you see at the corner of the room, sir, less brightness. Why? Because distance is very large to that point. Area is more, area. If area of the room is more, we say brightness will decrease, intensity will decrease. Okay. For a unit source, I am saying. So can I say here, intensity is inversely proportional to area. Area is pi r square. Area of this is what? Pi r square. So intensity is inversely proportional to r square. I hope you are getting it. When I say you take area as constant, then you consider it constant. But when you see this is the light source, sir, at this much area, intensity is large. Now increase the area, sir, intensity will decrease. Intensity is inversely proportional to area. Or intensity is inversely proportional to r square. So can I say here, intensity at A divided by, I say, intensity at B will be, what is the distance at A? Sir, that is 1 by r square. So 1 by r square upon, this will be 1 by 2r whole square. Okay, 1 by 2r whole square. Now take this in the numerator, it will become 2r divided by r and it is whole square. This and this will cancel. So 2 square is 4. So intensity at A divided by intensity at B is 4:1. So that's what I was saying. Intensity at lesser distance will be great, more. Intensity at farther distance will be less. Do you all agree? Tell me guys, do you all agree? And if you check over here, in this case, I have placed the two areas at the same distance. I have placed the two areas at the same distance from the bulbs, from the light sources. And here, in this particular case, the 2 points are at different distances. 2 points are at different distances. Okay. Now, one more thing we need to explain over here. One more thing. What is that? What is that? Guys, see. We say, as when it comes to the intensity, you say this is NHF divided by A into T. NHF divided by A into T. This is the intensity that we have over here. This is the intensity that we have over here. Okay. Guys, can I say here, T, H and F are constants. Sir, why? Why are you considering these as constants? Because source is unique, one, so frequency is constant. Time is constant. Same. What about the second thing? H is also constant. So can I say in this particular case, intensity is proportional to N by A, number of photons divided by area, or intensity is directly proportional to number of photons. Intensity is inversely proportional to the area over here. Yes. Now, can I say, guys, as a whole, I'm saying it is directly proportional to this quantity, N by A. So when I say intensity at A divided by, We say intensity at B. What is this? Number of photons per unit area. So can I say intensity at A will be number of photons per unit area at what A? What is this number of photons per unit area? Number of photons per unit area at A will be something. Number of photons per unit area at B will be something else. Yes. So I can say divided by, because it is directly proportional. So IB will be number of photons per unit area at B. We say it will be simply 4:1. Why are you saying 4:1? Because whatever is the ratio of intensity at A and B, same will be the ratio of number of photons per unit area. Number of photons per unit area, 4:1, 4:1, because it is directly proportional. So this also we were supposed to calculate over here. Ratio of photons per unit area at A and B. Please tell me in the chats if everything is crystalline clear. Guys, give me the signal in the chats if everything is crystalline clear. I would want you guys to tell me. Great, great. And if you have not liked the session, and I would want you guys to smash the like button. Now comes the radiation pressure. Okay, let's now talk about the radiation pressure. See guys, what does radiation pressure actually mean? What does radiation pressure actually mean? See, guys, let's suppose we have got a surface over here. And this surface is what? It is mentioned over here. This is completely absorbing surface. It is that surface. If you are sending the light, it is completely absorbing the light. And this surface over here is completely reflecting surface. If you are sending the light, it is reflected over here. Its intensity is I. It is reflected with the same intensity I. And this light is absorbed over here. Okay. Yes. Now. We say when light falls onto this surface, guys, if we say this is the area and you are pressing this area, you are applying the force over here, we say pressure will be created. Yes. Force per unit area. So pressure on this hand will be created. Yes. So when radiation falls onto this area, there will be pressure, and that pressure is what we call the radiation pressure. So I say when radiation falls onto the surface, okay, pressure is exerted. Pressure is exerted on the surface. Called radiation. Pressure. Okay. When radiation falls onto the surface, pressure is exerted on the surface called radiation pressure. Yes. Now guys, what is the value of that radiation pressure? Okay. We say in this particular case, it will be the intensity. If I say intensity of the radiation is I, it will be I divided by C over here. It will be I divided by C. The amount of intensity that has divided by, we say the speed of light, divided by the speed of the radiation. Okay. And what is this I? I is what we call the intensity. And what is the C? C is what we call speed of light. C is what we call speed of light. Yes. Now, we say as. When it comes to the pressure, we say it is force per unit area. Yes, sir, we have studied this. Can I say instead of this pressure, I can write force divided by area. And you'll send it over here. Just let me write over here. So I can say, instead of this, I'll write force divided by area. and this will be I divided by C. Yes. And I can say, take it over here, this force will come out to be, that is I into A divided by C. Guys, what is I into A? Tell me. When it comes to the intensity, intensity means power divided by area. Take it over there. Power will be I into A. Okay. So I can say this force comes out to be equals to, that is I into A is also called power divided by C. What is this F? F is the force exerted by this surface because of this radiation. F is the force exerted by the surface because of the radiation. And what is the pressure? Pressure is simply, that is I divided by C. You can directly put this in a box over here. Now, we say in case of completely reflecting surface, in case of completely reflecting surface, we say when it comes to the radiation pressure over here, that will be 2I divided by C. So in this case, radiation pressure will be 2I divided by C. In case of completely reflecting surface, we say radiation pressure will be 2I divided by C. Okay. Okay. Now guys, can I say why? Because I and I, you are taking over here 2I. In this case, completely absorbing, I divided by C. And one more thing, can I say this pressure is force divided by area is equal to 2I divided by C. Take this area over here. So I can say this force will come out to be, that is 2I into A divided by C. So this force will be, that is 2I into A is pressure, power. 2I is power divided by C. So mention it where F is the force exerted by the radiation on the surface. I hope radiation pressure concept is also clear. Yes, this is also clear to each and every single student. Guys, give me the signal in the chats. If everything is crystalline clear, I would want you guys to tell me. Everyone means everyone. And smash the like button if you have not liked it yet. Now guys, take a look over here. Let's move on to the photoelectric effect. I have told you the complete detail about the photon theory, intensity, we say power of light, whatever the things you need. Okay, everything I have told you. Now guys, photoelectric effect. What is photoelectric effect? See guys, what does photoelectric effect mean? Let's suppose you take a metal surface over here. Sir, what kind of metal surface? Anything, okay? Photosensitive metal surface. Cool. And let's suppose light is falling on it. Light is actually falling on it. These are the photons falling on it. This is light. We are performing this experiment actually. We took a photosensitive metallic surface. Photosensitive metallic surface. Sir, what is this photosensitive? Ignore photosensitive, simple the metal surface. We say photons fall on it and we saw this. We are performing this experiment. When photons fall on the metal surface, we saw electrons are ejected from the metal surface. So we took a photosensitive metallic surface and light falls on it. We observed that electrons are coming out of this surface. So this process is what we call the photoelectric effect. I'll just write over here. When light falls on a photosensitive, when light falls on a photosensitive metallic surface, and electrons are ejected from the surface, the process or the phenomena is called photoelectric effect. Photoelectric effect. The process is called photoelectric effect. As simple as that. As simple as that. Okay. Now guys, we have to study this in detail. Before this, you need to understand work function. Work function means phi. What is this work function? We say the minimum amount of energy, required to pull out the electrons from the metal surface, So it is the minimum amount of energy required to pull the electrons from the metal surface. What is that? See, let's suppose I have got a metal surface over here, and this is another metal surface I am taking. Okay. I'm saying, if you want to pull the electron from this metal surface, let's suppose if I say work function of this is 2 electron volts. Guys, understand this. And if I'm saying work function of this is 5 electron volts, what does it mean? It means that if you have to take out the electron from this metal surface, if you want to pull the electron from this metal surface, what are you supposed to do? You will have to send a photon. And the energy of that photon should be at least what? 2 electron volts, equal to the work function. Why? Because this work function gives you an idea how much amount of energy is required in order to pull out the it is not like electrons will come out by itself. No, you have to give the energy to them so that they use the energy to come out of the metal surface. So how much is the minimum energy required in this metal surface? We say 2 electron volts. Now, in order to pull the electron from this metal surface, we say this photon should have at least the energy of 5 electron volts. That is what is mentioned. The minimum amount of energy required to pull the electron from the metal surface. The minimum amount of energy required to pull the electron from the metal surface. Okay? So here, it depends upon the metal. This metal has got 2. This metal has got 5. Some other metal will have something else. And I can say, phi depends upon the material. So it completely depends upon the material. Okay, some materials will have different, some materials will have different. So how much energy is it? If the energy is less than 2 electron volts over here, it is not possible to pull out the electron from the metal surface. Okay. Conditions for photoelectric effect. Guys, what is the first condition? We say as. The first condition is energy of photon. Conditions for photoelectric effect means how photoelectric effect can take place, how it is possible. You'll say energy of photon should be greater or equal to work function. Energy of photon should be greater or equal to work function. If energy of photon is less than work function, then electron will not come out of the metal surface, then photoelectric effect will not take place. And I can say then only then only photoelectric effect will take place, then only photoelectric effect will take place. Okay. Now guys, see. I would want you guys to understand, how do we write energy of photon, that is h into f should be greater or equal to? Sir, what is this work function? Guys, understand this. Work function is itself the energy. It is also the energy. So if you multiply Planck's constant with frequency, you get energy. Don't you think that here also, if I just write h into f naught, this Planck's constant, this frequency will also give energy. That is what we call the work function. If work function is energy, this is energy. Energy is h into f. Here also I can write h into f naught. So from now onwards, you will remember that we can write this work function also equal to h into f naught. So this and this will cancel. So the frequency of photon should be greater or equal to f naught. So where f naught is called threshold frequency, which is the minimum frequency, which is the minimum value of frequency at which photoelectric effect takes place. At which photoelectric effect takes place. Okay, like this is the minimum value of energy at which photoelectric effect takes place. We said this is the minimum value of frequency at which photoelectric effect takes place, threshold frequency. Don't you think I can also write this as frequency c by lambda? This will be c by lambda is greater or equal to, this will be c by lambda naught. This and this will cancel. So this and this will cancel. Take it or do the cross. So lambda naught should be greater or equal to, we say lambda. Guys, where lambda naught is what we call the threshold wavelength. Where lambda naught is called threshold wavelength. Okay. So we say the photon which you are sending, guys, please understand this. The photon which you are sending should have the energy greater than work function or equal to. Cool. The photon which you are sending should have the frequency greater or equal to threshold frequency. Cool. The photon which you are sending should have the wavelength less than the threshold wavelength. Wavelength should be less. If it is greater than threshold wavelength, then photoelectric effect will not take place, because frequency is inverse of this. Energy is inversely proportional to lambda. Okay, so we say the photon should have, this is the maximum value. This is the maximum value of wavelength at which photoelectric effect takes place. So which is the maximum value of wavelength at which photoelectric effect takes place. Guys, please tell me in the chats if this is crystal and clear. Give me the signal in the chats. I would want you guys to tell me ASAP. Everyone means everyone. ASAP. Cool. One more thing. We say it is a 1-to-1 interaction. It is a 1-to-1 interaction. What does 1-to-1 interaction actually mean? That means that is one photon can take out only one electron. only one electron. So you'll say, sir, if the work function of this is, let's suppose 2 electron volts, I'll send a photon over here 10 electron volts. Sir, this 10 electron volt photon will take out 5 electrons. No. One can take out only one, even if the energy of the photon is very large. Sir, what about rest of 2 electron volts it will use in taking out? What about the rest? Will that be wasted? We have to study that. Wait for some time. Okay. So this is what we call the conditions of photoelectric effect. Let's move on to the experimental setup of photoelectric effect. This is what we need to understand now. Experimental setup of photoelectric effect. See guys, when it comes to the experimental setup of photoelectric effect, looks like this. It looks something like this. See guys, we say it is not like, sir, I'll do this photoelectric effect out in the sunny day. No. There has to be a proper setup. See, you say, you take a chamber over here. This is what we call the vacuum chamber. Okay, closed shaped tube. And there is an opening over here. Why we place the opening over here? So that light can enter from this opening. And it falls onto this metal surface. This is the metal surface. Metal surface, this one we call cathode. And another metal we place over here, we call it anode. Right? Understand this? You have this tube-like structure in which you have cathode and anode. And light falls onto this cathode through this opening. And this cathode is connected to a voltmeter over here. Why? So that we can measure the potential difference in this setup. Okay. 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 And you are basically connecting an ammeter also. Why? Because ammeter will help us to find the current. This will measure the current over here. And then you are connecting a switch and you are connecting a battery. Sir, what is the use of all of these? Please wait, you'll get to understand. You'll get to understand. Now see. I want you to exactly listen to me very carefully. We say, this is the cathode. Light falls onto the cathode. On this metal surface, what is going to happen? You say electrons will come out. Electrons will come out of this metal surface. Okay. So I'll just write over here the first statement. When photons fall on the cathode, when photons fall on the cathode, electrons are ejected from the cathode. Okay. So electrons come out of the cathode. Okay. Now guys, let's suppose you are sending a photon over here. This photon is falling on the cathode. Because of this photon, an electron comes out of the cathode. One photon takes out one electron. Guys, understand this. If I say, if energy of a photon is, let's suppose, 8 electron volts. The photon which you are sending, it has got the 8 electron volt energy. And work function is 2 electron volts. Means, if you want to take out the electron from this metal surface, it should have how much? It is having how much work function? 2. Okay. Now, if you want to take out the electron, so means minimum energy required is 2. Tell me guys, you are sending 8 electron volt. 2 electron volt, this electron takes out in coming out because it has to come out. Okay. So what about the rest of 6? 8 minus 2. What about the rest of 6? We say rest of the 6 is used as kinetic energy. We say rest of 6 electron volts is used as kinetic energy of electron. What does that mean? Guys, when electron comes out of the metal surface, it is not like it will stay there only. No, it has to move forward also. It has to produce the current also, because that is the ultimate goal. So it has to move forward also. So in order to move forward, it uses some energy. That is what we call the kinetic energy. So can I say in this particular case, kinetic energy will be 6 electron volts? And even I would mention over here, this is the maximum kinetic energy. This is the maximum kinetic energy. Why? Because all of the 6 electron volts go into the kinetic energy. Okay. Now, next. If let's suppose another photon is falling over here, I say if energy of photon is, let's suppose 8 electron volts and work function is 2 electron volts. Okay. Now, guys, understand this. When this electron is coming out over here, it is not like the electron has to go through the smooth journey. Now it is coming out, now it will move freely. No. While coming out, while moving, it has to face a lot of collisions out there with the atoms, ions, molecules, okay? So in collisions, we say it will waste the energy of 2 electron volts. It will waste the energy of 2 electron volts. So what about here? Here we considered collisions are 0. Maybe if there is an electron which is very lucky, he didn't face, that electron didn't face. Why am I mentioning he? Electron is not a he or she. That electron didn't face the collisions. So that's why I mentioned all of the rest of the energy will go into the kinetic energy. In this case, electron is facing some collisions while coming out, while moving forward. So I am saying 2 electron volts will go into the collisions. Okay. And can I say in this particular case, kinetic energy will be 8 minus 2, that will be 4 electron volts. Yes. Now guys, we say afterwards, let's suppose one more photon is coming and it is falling. It has the energy of 8 electron volts. It is interacting with the electron, okay, another electron. So work function is 2 electron volts. Work function remains constant for a metal. Okay, so we say collisions. Your collisions it is facing is how much? How many collisions it is facing? Let's suppose in collisions 4 electron volts is wasted. So in this particular case, kinetic energy will be what? 2 electron volts. 8 minus 4 is 4. 4 minus 2 is 2. Now, let's suppose if another electron is falling. If energy of an electron is 8 electron volts, work function is 2 electron volts, and this electron is facing lot of collisions, and all of its rest of the energy, 6 electron volts, is wasted in the collisions. Can I say in this particular case, kinetic energy of the electron will be 0. No kinetic energy means while the electron is coming out of the surface, okay? And this electron is seeing the ultimate army of what? The huge army of atoms, ions, molecules facing extreme collisions, and those atoms, ions, molecules does not let this electron to go forward. So it is using all of its energy in collisions, but still it is not moving forward. So we say kinetic energy in this case is 0. So these electrons will stay over here. Just they'll come out and they'll stay over here only. They won't be able to move forward. Okay. Now. So can I say, guys, in this experiment, electrons can have 0 kinetic energy also. Electrons can have maximum kinetic energy also. We say, so electrons can have kinetic energy from 0 to maximum. It can be anything. It depends upon the collisions the electron is facing. It depends upon the collisions electron is facing. If electron faces more collisions, kinetic energy will be less. If electron faces less collisions, kinetic energy will be more. Okay. Now. Can I say from this statement, guys, can I say, I'll just write over here. So in case of 0 collisions. Can I write, guys? I say energy of a photon is equal to, we say some part of the energy of the photon is used in work function in coming out of the metal surface, and the rest of the energy is used as kinetic energy maximum. Energy of photon is used in work function and kinetic energy maximum when collisions are zero. So this is what we call the Einstein's photoelectric equation. This is called Einstein's photoelectric equation. And because of this only, Einstein got the Nobel Prize. Okay, he didn't get the Nobel Prize because of the E is equal to mc square. No, he got the Nobel Prize because of this equation. Okay. Okay. Now, guys, listen to me very carefully. Listen to me very carefully in this case. So this is called the Einstein's photoelectric equation. Now, what I'm saying over here is, let me take one more page. Let's suppose I'll make this over here once again. This is the metal surface. See, guys, I'll make this over here. This is the metal surface, and this is what cathode. I'm saying this is the cathode, and this is the anode over here. I'm saying this is the anode over here. Okay, this is the anode over here. This is the anode over here. And in this particular case, I'm connecting a battery. Okay, and here is the switch. This is the battery. Now, guys, tell me one thing. I would want you to tell me one thing. It is something like this. I'm connecting this cathode with the battery, switch, and anode with the battery. This setup only. What I want to make you understand is that, let's suppose light is incident over here, incident radiations. Because of this light, because of these photons, let's suppose 10 electrons are coming out. Okay, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I'm saying 10 electrons are coming out. Okay. So suppose I'll mention over here. Suppose 10 electrons are coming out of the cathode. What I'm trying to say is that, suppose 10 electrons are coming out of the cathode. Light is falling on this cathode. We know electrons come out. Let's suppose 10 electrons are coming out of the cathode, and only 4 electrons are able to reach anode. Only how many electrons are able to reach anode? We say 1, 2, 3, and 4. Only 4 electrons are able to reach anode. Why, sir? What about the rest? Maybe rest of the 6 are facing maximum collisions. That's the reason these electrons, rest of the electrons, are not able to reach anode. This is cathode and this is anode. Cathode and this is anode. Now, what do we do actually? Now, we say we will connect the switch. Connecting the switch means we are connecting the battery over here. Connecting the switch means we are connecting the battery. And my dear friends, let's do one thing. We'll connect the positive terminal of the battery from this side to this side, and negative terminal of the battery to this side. This is what we call the positive terminal. This is called the negative terminal. So while you connect the switch, what does this battery do? Guys, this we have studied in the electrostatics, or we say current electricity. This or capacitors. We say, guys, do you remember in case of capacitors, I told you this is one plate of the capacitor, another plate of the capacitor. If the battery is connected something like this, we say this positive terminal will create positive charge over here. Positive charge will be occupied onto this plate. And negative terminal is connected to this plate, so negative charge will be occupied onto this plate. Now, see here, what is going to happen? We say this positive terminal is connected to this plate. We say this positive terminal will create the positive charge on this plate. Okay. Okay. So I'm saying that connect the battery. Connect the battery, which creates positive charge onto the anode, And if this battery is creating positive charge onto the anode, I would want you to focus over here. If this battery is creating positive charge, what does that mean? Basically, it is applying potential difference. This battery has, let's suppose, 10 volt potential difference. Sir, because of this 10 volt, it is able to create some positive charge. Sir, 20 volt, now more positive charge. 30 volt, now more positive charge. Okay. So I say, let's suppose, guys, now, we say at 0 volt EMF means when battery is not connected. When battery is not connected, that is 0 volt EMF. When you connect the battery, it will have some EMF or potential difference. So it creates some positive charge. We say at 0 volt, could you please tell me how many number of electrons were able to reach anode by itself? Okay. How many number of electrons were able to reach by itself? Sir, 4 electrons. We say 4 electrons. Okay. Number of electrons reaching anode. At 0 EMF, I'll say this is number of electrons reaching anode. Now, let's suppose you connected the switch and battery creates the potential difference. Some positive charge is created. Let's suppose at 10 volt EMF. Okay. Let's suppose at 10 volt. I'll just write now 10 volt only. Okay. Plus 10 volt. So I'm saying now some positive charge is occupied. Because of this positive charge, it will attract the electrons now. It will attract the electrons, some electrons, because positive attracts negative charge. It will attract some electrons now. Now let's suppose 5 electrons, we say reached cathode. Now, I say let's apply more potential difference so it creates more positive charge. So now this more positive charge is now stronger. It will attract more electrons. Let's suppose 6 electrons are reaching now anode. Again, increase the potential difference to 30 volts. Again, I'm saying 7 electrons are reaching anode. Again, increase. Let's suppose I'm making it 40 volts. Let's suppose 8 electrons are reaching anode. I'm making it 50 volts. We say in case of 50 volts, 9 electrons are reaching anode. And I'll make it 60 volts. I say 10 electrons are reaching now anode, and positive charge is strong. Now tell me one thing. If I apply more, let's suppose I'm applying 70 volts, how many electrons would be able to reach anode? How many electrons? You say, sir, 10 only. Why? Because only 10 are coming out. It is not possible. So how, if somebody says 11, no, only 10. If I say 80 volts, how many electrons? We say, sir, 10 electrons, because 10 are only present. Now, let's plot the graph between, guys, see. Now, these are the electrons which are flowing from cathode to anode. Don't you think that since flow of these electrons produce current, because flow of charge is current, since flow of these electrons produce current and is called photocurrent. So these are, why do we call it the photocurrent? It is because of the photons. When photons fall on the cathode, then only electrons come out, then only those electrons move, then only current is produced. So that's why we call it the photocurrent. Now let's plot the graph between. I'll just write over here. Graph between photocurrent versus EMF. Let's plot the graph between photocurrent versus EMF. Guys, see. What I'm trying to say in this particular case is, if I plot the graph between photocurrent versus EMF. So here it is I, and in this case it is EMF, photocurrent versus EMF. Photocurrent versus EMF. Tell me one thing, guys. When it was 0 volts, at 0 volts, how many electrons were flowing? Sir, 4. So at 0 volts, current is not 0 because 4 electrons are flowing. 4 electrons are flowing. So I can say in this particular case, at 0 volts, value of current is something. Value of current is something. It is not 0. Now, as we keep on increasing the potential difference or EMF, okay, we say current is increasing, okay, and it becomes constant at some point. Why, sir? Here it becomes constant. See, as you keep on increasing the potential difference, we say current increase, and then it becomes constant. 10 electrons, 10 electrons, 10 electrons. So I say over here, so we say this is, let's suppose this is 0 volts, 10, 20 volts, 30 volts, 40 volts, 50, and after 60 it becomes constant. And when the current becomes constant, it is called the saturation current. Saturation current. It is called saturation current. And I would want you to focus exactly over here. What is that? Let's suppose, I hope you got the feel of this graph. This is the saturation current or the peak current. One more thing. Let's suppose if somebody says, reverse the polarity of the battery. Reverse the polarity. Can I copy this page? Oh, delete this. How to, yeah. Yes. I'm copying the page over here. Let's make it over here. Okay. This is the another page, so don't worry. Okay. Now guys, see. What I'm doing is that I'm reversing the polarity of the battery. Reversing the polarity of the batteries, change the terminals. Okay. Positive here, negative here. So I'll do one thing. I'll do one thing in this case. So I'll connect the positive terminal from this side and negative terminal from this side. Okay. Yes, this is the negative. If negative terminal is connected to this one, so I can say in this particular case, it will create negative charge on this plate. It creates negative charge onto this plate. Okay. Now guys, we say if terminal is reversed, let's say as 0 volts, how many electrons were flowing? 4. Now I am saying, let's suppose I'm applying minus 10 volts. Okay. I'm reversing the polarity of the battery. Now I'm saying minus. So now because of this, negative charge will be developed over here. And we know, sir, this negative charge repels the electrons. If 4 are moving at 10 volt EMF, I'm saying only 3 electrons will reach anode because it is repelling. Okay. So I say only 3 electrons reach. So we say when polarity of the battery is reversed, when polarity of the battery is reversed, negative charge is occupied. Negative charge is occupied on the anode. Negative charge is occupied on the anode. Okay. And electrons are repelled. Electrons are repelled. If electrons are repelled, now at some negative charge, we say only 3 would be able to reach. Okay, let's suppose you are increasing minus 20 volts. So I can say now only 2 electrons are reaching. Let's suppose at minus 30 volts, only 1 electron is reaching. At minus 40 volts, I say 0 electrons are reaching. All the electrons are repelled. Why? You have created the strong negative charge. Now, let's make the graph. If you increase the EMF, if you increase the potential difference from the negative side, we say photocurrent will decrease, flow of electrons will decrease, so photocurrent will decrease. So I can say, my dear friends, the graph will decrease, and we say the graph will kind of decrease, and it will reach. Okay, and guys, see. I say this is 0, minus 10 volts, minus 20 volts, minus 30 volts, minus 40 volts. The point, and this is what we call the V naught. And I'll just mention here only. We say the potential, the negative potential at which photocurrent becomes 0 is called stopping potential. Okay, what I'm trying to say is that the potential at which photocurrent is 0 is called stopping potential. Okay, and this V naught is what we call stopping potential. V naught is called the stopping potential. Yes, cool. So this is the graph of current versus EMF, photocurrent versus EMF in case of photoelectric effect. And one more thing also at stopping potential. Guys, see. We say kinetic energy of electrons is equal to potential energy. Kinetic energy of electrons is equal to potential energy. Very important. Now, what I'm trying to say is that, let's suppose I have this pen. I'm holding this pen at height h. What is the energy stored in the pen right now? It is, sir, potential energy. What if I release the pen? We say it will fall down. That potential energy will be converted into the kinetic energy. So here I am saying it is holding potential energy or kinetic energy, one and the same thing, because this potential energy only will be converted to kinetic when it falls down. Same is the case over here. Guys, we say at stopping potential, these electrons face maximum repulsion. Now, these electrons, all the 10 electrons are waiting over here at maximum because this negative charge is repelling. If you remove this negative charge from this, if you remove the negative potential, we say they start flowing. So when they are placed over here, they have got potential energy. Okay, they are waiting. When this is like this pen, it is kept over here. When the pen is released, it falls down, it gets converted to the kinetic. Same. These are waiting when the potential is removed, negative potential is removed, stopping potential is removed. They start moving, these electrons start moving. So this potential is converted to kinetic. That's what I'm saying. At stopping potential, kinetic is equal to the potential. Okay. At stopping potential, kinetic energy of electrons is equal to the potential energy of electrons. Now, if we say potential energy, what is the value of potential energy? Guys, we say potential energy is equal to, that is charge multiplied by potential difference. This we have studied in the electrostatics. Remember this directly. We say potential energy, or we say potential, electric potential is equal to potential energy divided by charge. And this potential energy is equal to charge multiplied by potential difference or potential. Now here. What is the charge on an electron? That is E, 1.6 in 10 raised to minus 19. And which potential we are talking about? Stopping potential, that is V naught. So it will be EV naught. So can I say this potential energy is equal to kinetic energy, and that will be equal to EV naught. So I say the value of kinetic energy here is how much? EV naught. Is this point clear? Please give me the signal in the chats. I would want you guys to tell me. Is this clear in the chats? Is this clear? Tell me, guys. Okay. No. We're done with the photoelectric effect. Okay. Let's delete this slide. Okay. Break I'll give exactly at 8 o'clock. Okay. Let's now move on to this one. Okay. This series, I would want you to focus. See, guys, we say if frequency changes, energy of photon changes, kinetic energy of electron changes, stopping potential changes. I'll tell you. Wait. We say as when it comes to the energy of a photon, it is h into f. So if frequency f increases, okay, we say then we say energy of photon increases. As simple as that. If f increases, we say energy of photon increase. Okay, cool. Next, if energy of photon increases, guys, understand this very carefully. We say as energy of photon is simply h into f. Energy of photon is simply h into, okay, done with this. If energy of photon increases, we say as energy of photon is equal to work function plus kinetic energy maximum. Now, guys, if energy of photon increases, we say kinetic energy will increase. Why? Because if you are sending a photon which has got large energy, so some part of this will be used in the work function and rest of the portion will be in the kinetic energy. So we say kinetic, if energy of photon increases, then kinetic energy increases. Okay. Then as if kinetic energy increases, guys, tell me one thing, as kinetic energy is equal to EV naught, stopping potential into E. If kinetic energy increases, then we say stopping potential increase. If kinetic energy increases, then stopping potential increase. That's what I'm saying, bro. If frequency increases, photon energy increases, kinetic energy increases, stopping potential increases. So they are directly proportional to each other. They depend on each other. Next, if intensity increases, okay, if I say intensity increases, we say intensity is proportional to number of photons. Okay, if I increases, then we can say number of photons will also increase. And if more number of photons are falling on the metal surface, we say more electrons will come out. Why? Because it is one-to-one interaction. You send more photons, more electrons will come out. So if n increases, then number of electrons will increase. And if number of electrons will increase, okay, more electrons are flowing, don't you think that current will be more? Why? Because current is flow of charge, flow of electrons. So if number of, so I'll directly write photocurrent increases. So we say intensity, number of photons, number of electrons, photocurrent, they have the relation with each other. They depend upon each other. But this series does not depend upon this series. Keep that thing in your mind, my dear friends. Keep that thing in your mind, my dear friends. Let's suppose we have got these graphs. We have got these graphs over here. Now, if somebody wants you to plot these graphs, guys, photocurrent and intensity. We say if intensity increases, number of photons increase. Number of electrons increase, photocurrent will increase. We say it depends on each other. Graph will be linear. Photocurrent and frequency. If frequency increases, energy of photon increases. Kinetic energy increases. Stopping potential increases. They do not have the relation with each other, so graph will be constant. Kinetic energy and intensity. This is energy, this is number, so graph will be constant. They do not depend on each other. Stopping potential and intensity, graph will be constant. Is this clear? Is this clear? Because maximum times they have asked something like this. Are they dependent? Are they independent? Okay, cool, absolutely cool. Now guys, compare the intensity and frequency of the three graphs. Guys. In this particular case, this is photocurrent versus EMF. Now they have got the same saturation current, same photocurrent. We say here photocurrent is same, or we say saturation current is same. So intensity is same. Why? Because photocurrent and intensity is directly proportional. And they have got different stopping potential. This has got V1, this has got V2, this has got V3. And here V0 is different. Here V0 is different. So if V0 is different, my dear friends, guys, so frequency is different. Frequency is different. Okay? Cool? Absolutely cool. Yes, sir. Now, let's talk about this one. Comment on the frequency and intensity of the two graphs. Tell me in this case, they have got the different photocurrent, different saturation current. Don't you think here intensity is different? Even I can say I2 is greater than I1. Photocurrent is more, saturation current is more, intensity is more. So here intensity is different. Okay. And what about the stopping potential? Guys, they have got the same stopping potential. V0 is same. So I can say frequency is same. Because stopping potential and frequency have the direct relation. Guys, I would want you to give me the signal in the chats if everything is crystal and clear. Please, and please. All the people out there, whosoever is watching, give me the signal first. Then only we can move on to the next question. Tell me, is everything crystal and clear? Great. Now, guys, let's take a look over here. The figure shows the photocurrent graph versus photocurrent and this. Are you able to see this graph? Are you able to see this graph? Are you able to see this graph? The graph is something like this. The graph is something like this. Okay. So we say it is between photocurrent and potential, EMF. Something like this, something like this. This is the graph. And the curve over here is mentioned as, this is A, this is B, and this is C. Guys, in this case, don't you think that when it comes to this curve, A and B have got same stopping potential. A and B have got same stopping potential. So I can say in this particular case, they have got the same frequency. Okay? A and B have got the same frequency. Okay? A and B has same frequency. Okay, but different stopping potential, and stopping potential is same, but different intensity. I is different. Okay. And when it comes to C and B, they have got the same photocurrent. C and B have same intensity, but different frequency. Why? Because they have got the different stopping potential. If intensity, guys, if photocurrent is same, intensity is same. If stopping potential is different, means frequency is different. Now let's check at the options. Curve A and B represents incident radiation of different frequencies. A and B represent the intensity, different frequencies. Same frequency. Option A is incorrect. Curve A and B represent the incident radiation of same frequency. Yes, A and B has same frequency, but why? Stopping potential is same. But different intensities. Option B is correct. Curve B and C represents incident radiation of different frequency. B and C has got the same frequency. Sorry, different frequency. That is correct. Why? Because stopping potential is different. And different intensities. No, their intensity is same. This is wrong and this one is also wrong. I hope this question is also clear. Let's talk about this one. See, guys, over here, Einstein's photoelectric equation. We say, as we know, we recently saw energy of a photon is equal to work function plus kinetic energy maximum. Guys, can I write it something like this also? I can say this will be, see. I can say this will be H into F is equal to, this work function I can write H into F naught. I have told you previously, I can write this in the form of H into F naught. Then we say plus. Over here, can I say kinetic energy will be EV naught? We can write it something like this also. Okay? Yes. Now, put this in a box. Now, guys, one more thing I just want to mention over here. We say in terms of wavelength. We want to write this equation in terms of wavelength. See, we say energy of photon is equal to work function plus kinetic energy maximum. Guys, see. We can write this as H into F is equal to H into F naught plus this I can write as 1 by 2 mv square. because kinetic energy is also 1 by 2 mv square. Kinetic energy of an electron, either you say EV naught or 1 by 2 mv square. Now here, I can say HF. F we can write C divided by lambda, okay, is equal to, you can write this H C divided by lambda naught, plus we say 1 by 2 mv square. So you can write this equation in the form of this also, okay? Just the simple basic things you should know actually. You should know these two forms also. Now here, graph between the stopping potential and frequency using Einstein's kinetic energy, Einstein's photoelectric equation. See guys, we say as you have to plot the graph between V naught and F, or V and F, stopping potential and F. We say as, when it comes to the energy of a photon, it is equal to work function plus 1 by 2 mv square, okay, or work function plus kinetic energy maximum. Kinetic energy maximum. Now guys, can you write this as H into F is equal to, you can write this as H into, or keep it phi only, no problem, plus you can write this as EV naught. We have to plot the graph between V naught and F. Now take it over here. We say EV naught will come out to be HF minus phi. You can say this V naught will come out to be, that is H into F divided by this E minus, because this will go in the denominator, phi divided by E. This you got the equation over here, okay? Now in this particular case, we say compare with, we say Y is equal to mx plus c. What is the Y is equal to mx plus c? Y is mx plus c is the equation of a straight line. Okay, it is the equation of straight line. So if I plot the graph of Y versus X over here, if I plot the graph of Y versus X, Y is equal to mx plus c. We say graph would be something like this. If C means intercept, where the graph is starting. If C is 0, graph starts from origin. If C is positive, graph starts from upper side. If C is negative, graph starts from lower side. Now, don't you think this equation exactly looks like this? So graph of V naught versus F is a straight line. Graph of V naught and F is a straight line, as simple as that. Now, listen to me very carefully. We say here you have V naught, here you have Y. We say here V naught is Y. And here you want to plot Y versus X. Here you want to plot V naught versus F. So F in this particular case is X. And this M means slope. So we say in this particular case, M is slope. And this slope here is M, here is H divided by E. H is, guys, H is Planck's constant. E is charge on an electron. So this is constant. Both are constant. So graph is constant. Graph of a straight line is constant. Cool. And C is minus phi divided by E. What is C? C means intercept, from where the graph is starting. If the value of C is 0, graph starts from origin. Now, in this particular case, let me plot the graph. So this is V naught and this is F. Guys, don't you think that C is negative? So graph starts from negative intercept. So it will be something like this. And if you check the slope of this line, here it is making theta less than 90. This angle is less than 90. So I say slope has to be positive. No, not the negative slope. Slope is positive. Because slope is positive constant. Okay, so value of C is minus phi by E. And M is slope. Slope is, what is the slope? Slope is h divided by E, which is constant, and which is positive. It's positive. If it was negative slope, then the graph would have been something like this. This is the negative slope. Here, slope is positive, C is negative. C is negative. Okay? I hope this is clear. Okay. Now, guys, give me the signal in the chats. Give me the signal in the chats if everything is crystalline clear. Give me the signal in the chats. Now, guys, see. The question says light of frequency 1.5 times the threshold frequency. Light of frequency 1.5 times the threshold frequency. So light is, let's suppose, falling, and it is saying that light is, let's suppose, falling, and it's saying that its frequency is 1.5 times the threshold frequency. Means frequency of light is greater than the threshold frequency. So we can say photoelectric effect will take place. Okay? On a photosensitive material, this falls on a photosensitive material. Photoelectric effect will take place. If frequency is halved, it says that if frequency is halved, if f is halved, okay, means if frequency is halved, so that is half of 1.5 of f naught. So we say then frequency will become 0.75. Okay, half of this 0.75 of f naught, 0.75 of f naught. So 0.75 of f naught is less than the threshold frequency. So then photocurrent, photoelectric effect will not take place. Why? Because frequency is less than threshold frequency. So photocurrent is equal to 0. Option D. Photocurrent is equal to 0. Okay. Next, this is a good question. For a certain metal V, this is frequency. Call this as F. For a certain metal, F is 5 times of F naught, frequency F naught. The maximum velocity coming electron is, guys, see. Let's suppose you have got a metal over here. This is a metal surface. Okay. The question says that there is a photon which falls on this metal surface, and its frequency is 5 times the threshold frequency. We know, sir, from this electron will come out, and that electron, it is saying, has a velocity of 8 into 10 raised power 6 meter per second. Okay. Then it says, if a photon, if V is equal to 2 times of V naught, means if F is equal to 2 times of F naught, if we say another photon falls onto this and its frequency is, we say 2 times of F naught, and we know here also electron will come out. Okay. And this electron will have what velocity? We are supposed to find the velocity of this electron. Okay. So we say this is a metal surface. On this metal surface, photon is falling. Its frequency is this. Velocity, the electron which comes out, it has got this velocity. If this photon is falling, the electron which is coming out, what will be its velocity? Guys. In case one, use photoelectric equation. In case one, what does photoelectric equation mean? We say energy of a photon is equal to work function plus kinetic energy maximum. Tell me one thing. Can I write it something like this? Energy of a photon is simply h into f is equal to this. I can write h into f dot plus I can write this as 1 by 2 mv square. Already we have discussed this. So here, what is the value of f? It says frequency is 5 times f naught. So I can write over here 5 times h f naught minus is, and take it over here. It will become minus h f naught is equal to 1 by 2 m v1 square. Now how much it will be? 5 minus 1 is 4. 4 hf naught is equal to 1 by 2 m v1 square. Call this as equation first. Now I am saying use photoelectric equation in case 2. So that is this same equation, that is h into f is equal to h into f naught plus 1 by 2 m v2 square. And what is the value of frequency over here? That is 2 times of hf naught, and take it over there, minus hf naught is equal to 1 by 2 m v2 square. So this will become 2 minus 1 is 1. hf naught minus is equal to this will be 1 by 2 m v2 square. Call this as equation second. Okay. Now what I want you guys to do is divide first and second. What is first? First is 4 hf naught divided by, this is second, that is hf naught is equal to, here it is 1 by 2 m v1 square divided by 1 by 2 m v2 square. This and this will cancel. So I can say v1 divided by v2. It will be simply that is a root of 4. That is a root of this 4. Okay, because this is v1 by v2 whole square is equal to 4. So square will come over here. It will be root 4. That is 2. So I can say take a 2 over here. Root 4 is 2. So v2 will be v1 divided by 2. Simple calculation I am doing. So I can say v2 is equal to, what is the value of v1? 8 into 10 raised power 6. 8 into 10 raised power 6 divided by 2. So v2 will come out to be 4 into 10 raised power 6 meter per second. So velocity of the second electron is 4 into 10 raised power 6. Guys, tell me in the chats, is this clear? Tell me, guys. Is this clear? Great. Next question you have over here. Two radiation energies. Okay, similar type of question. Two radiation energies, 1 electron volt and 2.5 electron volt. This is the metal surface once again. And here this photon is falling. It has got the energy of 1 electron volt. Okay. Falls on this metal surface, which has got a work function of how much? This has a work function of 0.5 electron volt. Okay. And we know when this falls onto this metal surface, electron will come out. Okay. It has got the speed v1. It says 2 photon energy, radiations of photons energy is 1 electron volt and 2.5 electron volt. Another photon which is falling over here, it has got the energy of 2.5 electron volt. Okay, falls on a photosynthetic metallic plate. Work function is this: the ratio of maximum speeds of the emitted electrons. Now here in this particular case, this electron is coming out. This electron is coming out. It will have the speed v2. This electron is coming out. It will have the speed v2. Okay. Here. Because of this electron is coming out, because of this electron is coming out, we are supposed to find what is the value of v1 divided by v2. Guys, we'll use the same approach once again. We say use photoelectric equation in case 1. In case 1. What does that say? That says energy of a photon is equal to work function plus kinetic energy maximum. Now tell me guys, in this particular case, can I say energy of a photon in first case is 1 electron volt is equal to work function is 0.5 electron volt plus 1 by 2 mv1 square. Okay. Now 1 minus 0.5 is 0.5 and I can write 0.5 as 1 by 2 electron volt is equal to 1 by 2 mv1 square. Don't cancel this 1 by 2 as it is. Keep it. Equation 1. Okay. We say use photoelectric equation in use photoelectric equation in case 2. This is the case 2. And I can say in this particular case, what is the energy of photon? That is 2.5 electron volt is equal to, what is the work function over there? 0.5 electron volt. Then we say plus kinetic energy maximum 1 by 2 mv2 square. Call this as equation 2nd. Now 2.5 minus 0.5, that is 2 electron volt is equal to 1 by 2 mv2 square. Call this as equation 2nd. Okay. This as equation 2 minus this. Now divide first and second. Divide first and second. You divide this and this. So 1 by 2 upon 2. It will become 1 by 4 EV, electron volt, is equal to, this will become, let me write it. This is 1 electron volt divided by, 1 by 2 electron volt divided by 2 electron volt is equal to, this is 1 by 2 mv1 square divided by 1 by 2 mv2 square. This and this will cancel. So this is 1 by 4. So I can say in this particular case, v1 divided by v2 came out to be v1 by v2 whole square. It will go over there. It will become 1 by root 4. Okay. So it will become 1 by 2. v1 by v2 came out to be 1 by 2. 1 is to 2. So answer is this one. Option A. 1 is to 2. In a photoelectric emission process, a matter of work function 1.8 electron volt. So phi is given as 1.8 electron volts. The kinetic energy of the most energetic electron, kinetic energy is given as 0.5 electron volts. We are supposed to find the corresponding stopping potential will be. Guys, tell me one thing. We say as. When it comes to the kinetic energy, what will you say? It is equal to EV naught. And this is given how much? That is 0.5. Okay. We say, sir, EV, electron volts, is equal to EV naught. E and E will cancel. So V naught will come out to be 0.5 volts. So which option? Directly I can say option 3. Tell me guys, is this clear? Is this clear to each and every single student? Okay, let's move on to this one. let's move on to this one. See guys, in this particular case, we have almost finished 80% of the photoelectric, 80% of dual nature, only 20% left. Then we'll move on to the next chapter. Matter wavelength or de Broglie wavelength. Guys, see. When it comes to the light, I want you to understand this. We say light has got wave nature also, light has got particle nature also. What are the strong proofs that clearly prove that light is a wave? Interference. Sir, what is this interference? YDSE. Because in YDSE, this interference is proved. Okay, that is what we say wave nature. Diffraction. This also we'll study in the upcoming time. Okay. What are the strong proofs which support the particle nature? We say photoelectric effect that we recently studied. Tell me here, guys, in photoelectric effect, did you consider the light as a wave or you consider it particle? You say photons are falling. You didn't say, sir, it is wave falling because of the wave electron is coming out. No, it is particle falling. So photoelectric effect, black body radiation, okay, another concept, Compton effect. We said these are the strong proofs which clearly prove that light is a particle. These prove that light is a wave. Okay. Now guys, then comes the hero. Okay. Hero of the story. His name was de Broglie. Okay, de Broglie. He was a law student actually. He was not a physicist. And he gave the law in physics. You see the level of that hero, or you say villain. We said then de Broglie came. He said light is not a wave. He said light is not a wave, nor a particle. Light is not a wave, nor a particle. Okay. And we say it is a form of energy. We say it is a form of energy which sometimes behaves as a wave, Okay. Which sometimes behaves as a wave and sometimes particle. He said light is not a wave nor a particle. It is a form of energy. Okay, another statement. Light is a form of energy which sometimes behaves like a wave and sometimes particle. When it is falling in a photoelectric effect experiment setup, it behaves like a particle. When it is, we say, interacting in the Young's double slit experiment, over there it behaves like a wave. Even he also said every particle in the universe and depends upon the surrounding it is interacting with. He said every particle in the universe, not only light, everything in the universe shows the wave nature, is a wave. Like this particle, you, me, everything is a wave. Okay, so we say matter also have dual nature. That's why the name of the chapter is dual nature of matter and radiation, matter and light. Matter means you, me, we are made of matter. He said this matter also has dual nature, wave nature as well as particle nature. Okay, everything in this universe has a wave nature as well as particle nature. Okay. So I know you are confused, sir. This marker has the particle nature. We can clearly feel it. We can clearly experience it. We can touch this marker. Okay, because we can feel its particle nature. How is it possible? How can we say it has a wave nature? Guys, see, there are a lot of waves which we cannot see with our eyes. So similarly, the wave which is associated with this particle, that is called the matter wave. We cannot see that matter wave, but it has the wave nature with it. Okay, now you will say, sir, this wave should have the wavelength. Okay, we say if a matter shows the wave nature, he said wavelength, it will have the wavelength. Its wavelength will be lambda is equal to h divided by p. Lambda is equal to h divided by p. Don't you think it is like momentum is equal to h by lambda? What was this lambda? De Broglie's wavelength. Okay, so I say this De Broglie's wavelength lambda is h divided by p. That is Planck's constant divided by momentum. Planck's constant divided by momentum. No derivation for it, he said. There is, because he was a law student. How is it possible he'll give the derivation? So no derivation for it. Just remember, he said, just remember, this is my law and remember it. So everything in this universe is a form of energy. You, me, everything is energy. And this energy sometimes behaves like a particle and as well as wave. It has a particle nature as well as wave nature, Okay. Everything in this universe has a wave nature, and a wave is associated with it called matter wave. It has wavelength also called matter wavelength, or we say de Broglie wave or de Broglie. And this lambda is equal to h divided by p or h divided by mv. What is m? M is the mass of that particle, v is the velocity of that particle. So means, my dear friends, if a particle is moving with some velocity, we say it will have the wavelength of how much? Lambda is equal to h by mv. So from now onwards, you'll say everything in this universe which is moving has some mass, has velocity, has wave, has a wavelength associated with it. It is a wave itself, so that wavelength is h by mv. Guys, give me the signal in the chats if everything is crystalline clear. Everyone means everyone. Please, please, please. Okay, great. Guys, smash the like button if you have not liked the session yet. I would want you to hit the like button. Now guys, see, de Broglie wavelength in terms of, okay, Wasim sir always used to make fun of me in this. He used to say it is de Broglie's wavelength. And I say it is de Broglie's wavelength, okay? I like to say de Broglie. Noun is a naming word, okay? I can say anything. I like de Broglie instead of de Broglie. I can say it. Okay, what is the correct pronunciation, guys? Now, let's take a look exactly over here. We say de Broglie's wavelength in terms of kinetic energy. Okay, cool. Now see, we say as if a particle is moving with some velocity, it will have a lambda is equal to h divided by mv. Okay, cool. This is the de Broglie's wavelength in terms of what? Momentum, in terms of mass and velocity, in terms of momentum. Now tell me one thing. I would want you to understand one thing. What is that? We say as. When it comes to the kinetic energy, we say kinetic energy is 1 by 2 mv square. I want you to multiply with m and divide with m. So what will it will become? Kinetic energy is equal to m into 2 will become 2m. M into m is, this is m square v square divided by, we say 2m. Take it over here. So I can say mv, this is whole square, is equal to kinetic energy. So it will become 2m and this is ke. Now take the square over here. So this mv will become under root of 2m ke. Okay. Okay. Now guys, I would want you to understand one thing. We say put in equation first. We say put in equation first. So I can write over here, this lambda will come out to be h divided by. Okay. So we say mv. Instead of this mv, I can write 2mke. So we say this is lambda in terms of kinetic energy. This is lambda in terms of kinetic energy. H, lambda is equal to h upon under root of 2mk. Okay. Next one. Okay. Now guys, de Broglie's wavelength for a relativistic particle. See guys, we say relativistic particle means that particle which is moving with a very faster speed, which is moving with a speed comparable to the speed of light, like electrons, protons. Okay, so we say that particle which has speed comparable to the speed of light. That particle which has a very large speed compared to the speed of light. Okay, electron, proton example. And when it comes to the mass, we say mass of that particle is, guys, remember, its mass, we say m is equal to m naught under root of 1 minus v square by c square. See guys, in our real life, if a particle is moving, it has mass m. It is the rest mass. When it is moving, we say, let's suppose its mass in motion is m. We say this m is equal to m naught. Rest mass is equal to mass in motion. Because when a mass moves with less velocity, its mass does not change. When an object moves with less velocity, its mass, we consider it constant. But when an object moves with a very huge speed, we say its mass will change according to this relation. We say if an object moves with large velocity, very large velocity, its mass changes, and it is extremely huge, guys. It is extremely huge. Okay, so m is equal to m naught under root of 1 minus v square by c square. What is this m naught? This m naught is what we call the rest mass. When the object is at rest, how much is the mass? This is mass in motion. Mass in motion. Now tell me one thing. If an object is in motion, so we say as. If an object is in motion, it will have lambda is equal to m into v. If an object is in motion, we say it will have de Broglie's wavelength, lambda is equal to h upon mv. So I can say over here, this lambda will be h upon m, h upon, we say v. Instead of this m, or just write, instead of this m, can I write this? I'll write m naught upon under root of 1 minus v square by c square. Sir, this is rest mass. What is this v? V is the speed of that object with which it is moving. Sir, what is c? C is the speed of light. Now take and multiply it by this velocity v. Multiplied by this velocity v. Take in the numerator. So I can say lambda is equal to h into v. Sorry. H into this quantity. 1 minus v square by c square divided by, we say, m naught into v divided by m naught into v. Okay. Next you have, we say charge accelerated with potential difference delta v. Charge accelerated. I'll show you that also. Mohammad Musa Shah, I'll show you that also. Wait. Charge accelerated with potential difference delta v. We say as. Guys, charge accelerated with potential difference delta v. Don't you think its kinetic energy will be, guys, if you remember, I recently told you here, the crystal clear explanation. So here, charge is accelerated with potential difference. This was, guys, Q delta V. It has got kinetic energy is equal to potential energy is equal to Q delta V. Instead of Q, you write E. Instead of potential difference delta V, it is right. You write V naught. So actually, it is Q delta V. So kinetic energy is equal to Q delta V. if a charge is accelerated with a potential difference delta V, if a charge is accelerated with a potential difference delta V, it has kinetic energy is equal to Q delta V. Now, as we know, guys, tell me one thing. We recently saw this form. Lambda is equal to h upon under root of 2mke. Instead of this kinetic energy, I would want you guys to put this value. So we say lambda is equal to h upon under root of 2mke. Instead of kinetic energy, we'll be putting lambda is equal to under root of, we say 2m q delta v. So this is the de Broglie's wavelength in terms of potential difference. Okay. So guys, let's take a break till 8:50. Break till 8:50. Break till 8:50. And this is a long break. I would want you guys to come back exactly at 8:50, okay? This is the dinner break. Yeah. Okay, take care till then. Check, check. Okay, guys, we are back. So, ladies and gentlemen, welcome back to the session. Back to basics. Let everybody join, and we are starting the session once again. Let everybody join and smash the like button if you have not liked the session yet. Okay, okay. Cool, 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 cool. Now, guys, let's take a look exactly over here. Let's take a look exactly over here. Okay. Charge at rest in an electric field. See, let's suppose I'm saying I have got the electric field exactly over here. This is the electric field. Okay. And in this electric field, I'm saying I have placed a charge. We have studied in electrostatics. Whenever we place a charge inside the electric field, it experiences force. Okay, it experiences force. Okay. And this force is equal to Q times of E. And because of this force, it starts moving. And it will gain the velocity V. It starts moving and it will gain the velocity V. And if we talk about that velocity, we say V is equal to U plus A into T. This is how we can find that velocity. And we say V is equal to, initially it is at rest. So then acceleration. What is the acceleration of the charge? That is force upon mass. So force is equal to Q into E, okay, divided by mass is exactly m and time is, we say, sir, T. So this is the velocity of the charge which is placed in an external electric field. If you place the charge in external electric field, it will experience force. It starts moving. It will have velocity. V is equal to U plus AT. Initial velocity is 0. Acceleration will be force divided by mass. A is equal to F by M. Time is T. Now tell me, if we write its de Broglie's wavelength as, we say lambda is equal to H divided by M into V. So I can write lambda is equal to H divided by mass. In this particular case is M only. What is the velocity? Velocity of this charge is, that is Q E T divided by, we say, M. This M and this M will cancel. So lambda will come out to be, that is simply H divided by, that is Q E and T. This is the de Broglie's wavelength of a charged particle which is initially placed at the rest in the external electric field, then it starts moving. Then charged particle placed in the magnetic field B. Guys, see. Let's suppose I'm taking a magnetic field exactly over here. This is the magnetic field B. And in this magnetic field, I'm sending a charged particle which is Q. I have told you so many times previously in magnetism also. Okay, I have not told you as of now, okay? Because that part of the magnetism will be posted tomorrow. Remember here, whenever the charged particle moves with a velocity V in the magnetic field, it performs circular motion, okay? It will perform circular motion. Directly remember this, okay? Whenever the charged particle enters the magnetic field perpendicularly like this, it will perform the circular motion, okay? And we say here Q performs circular motion. Circular motion. I want you guys to see over here. Whenever any body performs the circular motion, we say centripetal force will act on it. So Fc acts on it because a body in a circular motion has centripetal force. And that's if the radius of this circle is r. We say, sir, that centripetal force will be equals to, that is mv square divided by r. This is a basic formula. If a charge enters the magnetic field, it performs the circular motion, and this will be the force. Also, when charge enters the magnetic field, B, we say it experiences magnetic force. Like in this particular case, we say when charge enters the electric field, it experiences the electrostatic force. When charge enters the magnetic field B, it experiences the magnetic force. And that magnetic force is equal to, that is Q, V and B. Q is the charge, V is the velocity, B is the magnetic field. QVB sine theta is 0. Directly remember this. Okay. And this magnetic force and this centripetal force will be equal over here. We say here, this centripetal force will be equal to this magnetic force. Guys, whatever I say, just remember. Charge enters magnetic field, it starts performing circular motion. Due to circular motion, centripetal force will act. Also, when charge enters magnetic field, magnetic force will also act. Both the forces will be equal. So I'll write this centripetal force is mv square divided by r. This is equal to, that is qv, and this is b. V and square will cancel over here. So in this particular case, I can say this velocity will come out to be, r will go over here, qb and r divided by, we say, m. Now tell me, we say as we know, guys, as we know, I would want you to understand, as we know, lambda is equal to m, lambda is equal to h divided by mv. If you want to write the de Broglie's wavelength for such particle, what will you write? You'll write, sir, lambda is equal to h divided by mass of this particle is m, and velocity of this particle is, that is qbr, okay, divided by, we say, m. This and this will cancel. So lambda will come out to be h upon, that is qbr. So I can say this is the de Broglie's wavelength of a charged particle which is placed in a magnetic field. This is the de Broglie's, and this is the de Broglie's wavelength of that particle which is placed in the electric field. Okay. Now guys, one more thing. For a gaseous molecule at temperature T, we say, for a gaseous molecule, I would want you to directly remember, we say kinetic energy of a gaseous molecule at temperature T is 3/2 kBT. As of now, you directly remember it. Okay, these are the things we study in the upcoming time. What is KB? KB is called the Boltzmann's constant. Okay. Now guys, we say, as we know, recently we studied lambda is equal to h upon under root of 2m, and we say ke, 2m ke. So can I say lambda will be h upon, we say, under root of, this will be over here, that is 2m. Instead of this kinetic energy, can I put this? So I'll write over here 3/2, and this is kBT. T is the temperature, kB is the Boltzmann's constant, T is the temperature. And I can say this 2 and this 2 will cancel out, and this lambda will come out to be over here, that is h upon, and this will be 3m, and then we say kBT under root. Okay. This is the de Broglie's wavelength for that particle for a gaseous molecule at temperature T. Okay. Next, for an electron moving in the nth orbit. Guys, look at this. Now don't get confused. Sir, what is this gaseous molecule? Give me the example, how this is moving, how it will have kinetic energy. Now is not the time to think about that, okay? So whatever I say, just listen to it and remember it. So we say, for an electron moving in the nth orbit, let's suppose if I say I have an atom over here, this is the center of the atom, nucleus. We know around the nucleus, electrons revolve. We know around the nucleus, electrons revolve. Okay. And I'm saying over here, this is the electron which is revolving. This is the electron which is revolving in the nth orbit. After some time, we'll have to study this in detail. Okay. This is the electron which is revolving in the nth orbit. Which orbit is this? This is the nth orbit. Nth orbit. Sir, what is orbit? Orbit is that circle in which electron is revolving, that path. It can be first, second, third, nth. For first orbit, n is 1. So we say, guys, this we will be studying in next half an hour. We say kinetic energy of an electron revolving in nth orbit. Kinetic energy of an electron revolving in nth orbit, you guys will be directly writing as of now, it is 13.6 divided by n square. Okay. In an nth orbit in hydrogen atom. Okay, 13.6 divided by n square. Now guys, how do we write the de Broglie's wavelength for such particle? You say, sir, lambda is equal to h upon under root of 2m ke. So I'll write over here lambda is equal to h upon, we say under root of 2m, and instead of this kinetic energy, what I'll write over here is 13.6 divided by n square. Now this square and root will go up, so n will go up, so it will be nh divided by, we say under root of 2m into 13.6. Okay, you'll be keeping it something like this. Next. Okay, so we are done with all the forms of de Broglie's wavelength for the different number of particles out there. Please tell me in the chats if everything is crystalline clear till over here. Please tell me in the chats if everything is crystalline clear till over here. We are done with the photoelectric effect. Now few questions are left and we will move on to the next chapter, atoms. Okay. Tell me guys. Is everything crystalline clear? Is everything crystalline clear till over here? We are done with the photoelectric effect. And then we will move on to the next session. Some questions are there. So find the ratio of velocity of proton and alpha particle if the de Broglie wavelength of both are same. Guys, when we talk about proton, okay, we say its mass is, we say, sir, m. And its charge is, we say, sir, E. And when we talk about an alpha particle, always remember, this alpha particle, it is made up of 2 protons. It is made up of 2 neutrons. Protons are those particles which are present inside the nucleus. Neutrons are also those particles which are present inside the nucleus. Neutrons are neutral. Protons have positive charge. So when they mix, they form alpha particle. So when it comes to the mass, we say mass is 4m because two protons have 2m. 2 neutrons have 2m. 2m plus 2m is 4m. Charge it has, that is 2e. Why? Because 2 neutrons are neutral. Protons will have the charge 2e. Cool. Now guys, what does the question say? Question says you have got a proton and an alpha particle. Both have the same de Broglie wavelength. So means lambda of alpha is equal to lambda of proton. Okay. Now how do we write it? This will be h divided by mass of alpha particle. We say velocity of alpha particle is equal h divided by mass of proton divided by velocity of proton. Yes, I can write it something like this. Now guys, see, this h and this h will be cancelled. Now take it over here. Okay, one more thing. I can write 1 upon mass of alpha particle is 4m. 4 times mass of proton. This is velocity of alpha is equal to 1 upon mass of proton is m. Velocity of proton is Vp. M and M will cancel. Take this Vp over here. Velocity of proton divided by velocity of alpha. Take it over here. This will be 4:1. Velocity of proton by velocity of alpha. This ratio is 4:1. We were supposed to find the ratio of velocity of proton and alpha particle. Vp by V alpha. Okay, one more thing. Now look at the question. An electron of mass m, when accelerated through a potential difference V, you have an electron which is accelerated through potential difference V, has de Broglie's wavelength lambda. Guys, if we talk about an electron, it says that electron is accelerated through potential difference V. Its de Broglie wavelength is lambda. Can I say electron wavelength will be h upon under root of 2m q delta V? Because if a particle is accelerated with some potential difference, its wavelength will be h upon under root of 2m q delta V. Yes. Now here I can say this lambda E will come out to be, that is h upon under root of 2. Mass of electron is m, charge on electron is E. Potential difference in this case is given as V. And more importantly, this wavelength is given as lambda over here. Cool? Yes. Then it says the de Broglie wavelength associated with a proton. Now, if we talk about a proton, we say for a proton, if we talk about a proton, how can we write de Broglie wavelength? Sir, lambda of proton is equal to h upon of mass m, capital M, h upon under root of 2 capital M q delta V. What is charge on proton? That is also E. Charge on proton is positive, charge on electron is negative, but magnitude wise same. And potential difference same delta V. Okay. Now we are supposed to find lambda of proton. This is given as lambda. Now do one thing. Divide the two equations. Divide the two equations. What am I supposed to write? What am I supposed to write over here? Guys, I can write this lambda of proton divided by lambda of electron will be equals to, what is lambda of proton? H divided by, we say under root of something like this. Lambda of proton divided by lambda of electron. H divided by will be equals to H divided by under root of, we say 2m E into V whole divided by H divided by under root of 2m E into V. Now tell me what will cancel out over here. I can say H 2 root 2 V E E. So it is over here lambda of proton divided by lambda of electron is equal to, it is 1 divided by root m upon, I can say 1 divided by, this is capital M, okay, upon 1 divided by under root of small m. Okay, do the reciprocal. I can say lambda P divided by lambda E is equal to under root of small m divided by capital M. Okay, now lambda of E is given as lambda. So you can take it over here. Lambda of P is equal to lambda under root of small m divided by capital M. So which option here is matching? Option second. Option second. Now, if the velocity of an electron is doubled, its de Broglie frequency will be, guys, its de Broglie velocity frequency will be, guys, we say we say lambda is equal to h divided by mv. Can I say lambda is inversely proportional to velocity? Okay, yes. Lambda is inversely proportional to velocity. Now, also we know, lambda is inversely proportional to frequency, or frequency is inversely proportional to lambda. If lambda is inversely proportional to velocity, lambda is inversely proportional to frequency, don't you think that frequency and velocity are directly proportional? So I can say frequency is directly proportional to velocity. This is inversely proportional to this. This is inversely proportional to this. So this and this are directly proportional. So if velocity is doubled, if V is doubled, don't you think that de Broglie frequency F is also doubled? Option C. Let's talk about this one. This was the question which was actually asked in NEET 2021, 2016 and IIT 2021. It's a good question. See what does it say. I'll read out to you. An electron of mass m. You have got an electron. Okay. You have got an electron. Okay. Its mass is small m. And a photon of energy E. And you have got a photon. Okay. An electron of mass m and a photon of have the same energy. This has got energy. This has got energy. You have a photon, you have an electron. Both have got the same energy. The ratio of de Broglie's wavelength associated with the electron and the de Broglie wave. Okay, we are supposed to find lambda E divided by lambda P. De Broglie wavelength of electron divided by de Broglie wavelength of photon. That's what you are supposed to see. Now see, if we talk about an electron, I would want you guys to listen to me very carefully. If we talk about an electron, we said de Broglie wavelength will be something like h upon under root of, since energy is given, we write 2mq delta V. Mass of electron is m, charge on electron is E, and potential energy, okay, 2m ke. It's in the, not in the 2m kinetic energy. Kinetic energy is given as E. They have got the same energy E. So lambda h upon under root of 2m kinetic energy. Cool. Now when it comes to the photon, see guys, we say in case of photon, how do we find lambda? We say energy of a photon is equal to hc divided by lambda. Take this lambda over here. This will be lambda of photon is equal to hc divided by E. This is how we find the de Broglie wavelength of photon. And for electron, proton, for particles, something like this, we find it like this. For photons, we say it something like this. Now, I would want you guys to divide the two equations. Divide the two equations. If you divide the two equations, you'll get lambda E divided by lambda P is equal to, we say this is h upon under root of, that is 2m into E whole divided by hc divided by, we say E. Now here h and h only will get cancelled out. So I can write over here lambda E divided by lambda P will come out to be, take this in the numerator, it will become E divided by this C, and then under root of 2m into E. Guys, this will go in the numerator, E will go in the numerator, C will go in the denominator. That's what, and then already you have this. Now what I can do in this particular case is, we say multiply with root E, do the rationalization, and divide with root E. Now, root E into root E will become E. So this E with will cancel with, guys, root E into root E is E. This E will cancel with this E. What remains over here? Root E in the numerator, and then you have this denominator. Lambda E divided by lambda P is equal to, this is guys 1 by C. Then we say under root of this E divided by over here 2m. You can also write it something like this. Lambda E divided by lambda P is equal to 1 by C. Then we say, what is the value of root? 1 by 2. You can write this is E divided by 2m whole raised power 1 by 2. And you can clearly see lambda E by lambda P, E by 2m. I guess option 1 is matching. Option 1 is matching. Yes. Let's talk about this question. This was the question which was asked in JEE Mains 2021. The following have the same kinetic energy. The one which has largest wavelength. You have alpha particle, you have proton, you have neutron, you have electron. Guys, remember one thing. When it comes to the mass of alpha particle, we say it is greater than mass of neutron. Okay, it is greater than mass of proton. It is greater than mass of electron. Or we say neutron and proton have almost same mass. There is no difference. Or you can say mass of neutron is slightly greater than the mass of proton. Okay, yes. Now see. If this is the ratio, this is the basically comparison of the mass. So alpha particle is made up of 2 neutrons, 2 protons. That's why mass is large. Now you tell me one thing. Now we say lambda is equal to h upon under root of 2m ke. 2m ke. It says in the question, all of these particles, be it alpha particle, be it proton, be it neutron, or be it electron, they have got the same energy. Kinetic energy is constant, h is constant, 2 is constant. So can I say this lambda is inversely proportional to mass under root of mass? Yes. So the one which has large mass will have less de Broglie wavelength. So I can say in this particular case, lambda of electron will be greater than, lambda of proton will be greater than, lambda of neutron will be greater than lambda of alpha particle. So this was the ratio and this was the question which was asked in JEE Mains 2021. Please give me the signal in the chats if this is clear. Tell me. Next. Now guys, figure shows, take a look over here. Figure shows the situation in which an electron is moving in electric and magnetic field. In which of the cases the de Broglie's wavelength of electron is increasing? Guys. I can say lambda is equal to h divided by mv. Okay. We say lambda is inversely proportional to velocity. Okay. Lambda is inversely proportional to velocity. So if in all the 4 cases, if velocity of the charge decreases, then we say lambda increases. If velocity decreases, then lambda will increase. Now you have to see in all the 4 cases in which velocity is decreasing. Guys, see. Direction of electric field is backward. This is the negative charge. We know, we have studied if this is the electric field, if in this electric field you place the negative charge, force acts in the opposite direction of electric field. If it was positive, force acts in the same direction. Now this is the direction of electric field. Force on this will act in the opposite direction, F. Now see, force and velocity are in the same direction. So if you push, if it is moving in the forward direction, if you push it, its velocity will increase. We say here, V increases. If velocity increases, we say lambda decreases. Okay, so this is not the option. We have to check that case in which de Broglie wavelength is increasing. Now take a look over here. We say in this particular case, guys, I would want you to focus. In this particular case, we say this is the negative charge. It is moving in the forward direction. Okay. And electric field is also forward. Now here, force on this will act in the backward direction, opposite. Now here, velocity and force are opposite. So here, this force will try to stop the electron. So here, velocity decreases. If velocity decreases, we say lambda increases. Okay, so option B is correct. Now see, here you have got a charge. Here, this is magnetic field. This was electric field. Now this is magnetic field. Guys, this is the velocity of the charge. Guys, remember one thing. Whenever you place a charge in the external magnetic field, whenever you place the charge in the external magnetic field, force will act. F is equal to, that is QVB sine of theta. This is the force. Here, force is Q into E. Q is the charge. Okay, Q is the charge. V is the velocity. B is the magnetic field. And theta is the angle between velocity and magnetic field. Here, angle between velocity and magnetic field is 0 because they are parallel. So I can say force in this particular case is QVB, and then I'll write sine of 0. Sine 0 is 0. So force will come out to be 0. Okay. Force will come out to be 0. Now check here. In this particular case, theta is 180 degrees. Velocity is forward, magnetic field is backward. In this case, magnetic force will come out to be, and if force is 0, means velocity is constant. Velocity is constant. And if velocity is constant, we say lambda is constant. Lambda will not change. So this is not the option. We have to check that option in which lambda decreases. Lambda increases. Here, force will be QVB sine of 180. Sine 180 is also 0. So magnetic force in this particular case will be 0. If here force is 0, so means on this charge velocity will remain constant. No force is acting. If velocity is constant, we say lambda is constant. This was actually a good question. Mention it, important. So with this, we are done with the dual nature of matter and radiations, with all the topics and with sufficient number of questions. Okay. Great. Great. Now comes the atomic physics. Now we have the second chapter. Okay, now we have the second chapter. I would want you guys to tell me in the chats, did you like it? Okay. No, I know you liked over there, but I'm saying, did you like it? Okay. Did you like to learn this chapter? How was it? Everyone in the chats. Okay, great, 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 great. Now, guys, let's move on to the atomic physics. Let's move on to the atomic physics, or the chapter name is atoms. Or the chapter name is atoms. Okay. Okay. Now we need to talk about atoms. Atoms. Now the first thing is, what are we going to study in this chapter, atoms? Okay. Guys, see, I'll say in this particular case, you are going to study different models of an atom. Different models of an atom. Guys, what I'm trying to say in this, if you learn the atomic structure over here, you don't have to study in the chemistry afterwards. That is my guarantee. Now see, when it comes to the chapter atoms, so basically everything in this universe is made up of atoms. Okay, this marker is made up of atoms, everything, small tiny particles, atoms. Now we need to understand that how this atom actually looks like. Back in time, okay, different number of physicists came and they gave the different models of atom. Someone came, he said atom is like a watermelon. Yes, actually, like if you see watermelon, it is like atom. So another one came, he said atom is like this. Another one came, atom is like that. So we have to study all those, we say, models over here. The first one is, his name was Thomson. He was the first guy who came up with the atomic structure, model of atom. Okay, how atom actually looks like, he said. Okay. Now guys, we say when it comes to the Thomson's model of atom, he said, look at this. In an atom, we say, first point I'll mention, first point. He said, an atom is exactly like a watermelon. He said an atom exactly looks like a watermelon. Okay. In an atom, electrons are present and are distributed like seeds are present in the watermelon. Now guys, see, he said if you have the watermelon over here, okay, we know in the watermelon you have this red portion that you actually eat, that we actually eat, and then you have these seeds. He said this red portion is called positive charge. In an atom, positive charge is like this only. And these seeds are like electrons. Similarly, atom will be like this, positive charge and negative charge and electrons. Okay. Electrons are distributed exactly like seeds present in a watermelon. Okay. And the red part is protons, is positive charge. Okay. Okay. And he said this positive charge is continuously distributed. It is not present at a fixed position. No, it is distributed randomly over here. In the complete sphere, in the complete atom, it is distributed. Okay. And these seeds over here represent what? Electrons. Okay. And one more point he said. He said atom is electrically neutral. He said atom is electrically neutral. What does that mean? Number of positive charge present is equal to the number of negative charge. We say a body is neutral when the amount of positive charge on the body is equal to the amount of negative charge. So he said the amount of positive charge over here is exactly equal to the amount of negative charge. So that means atom is neutral. He said atom is electrically neutral. Okay. An atom is a positively charged sphere of radius 10 raised power minus 10 meters. He said radius of atom is 10 raised power minus 10 meters, in which electrons are embedded in between, in which electrons are placed in between, embedded in between. One and the same thing saying again and again. Okay. And the positive charge and whole mass of the sphere is uniformly distributed. That is what I said. The positive charge is not present at one position, but it is uniformly distributed. The amount of positive charge at this position is equal to the amount of positive charge at this position. It is uniformly present everywhere. You cannot say positive charge here is more, here positive charge is less. No, it is uniformly distributed. Okay. Okay. Yes. Okay, this was basically the Thomson's atomic model, completely theoretical, nothing mathematical. Is this clear? Now we will move on to the Rutherford's atomic model. Rutherford's atomic model. Guys, is this clear? Tell me in the chats, is this clear? Is Thomson's atomic model clear? Yes. Now guys, take a look over here. Now we have a Rutherford's atomic model. Rutherford didn't give what? The theoretical model, no. He performed an experiment. Rutherford performed an experiment. I'll just write performed perform an experiment. And the name of that experiment was, we say alpha particle scattering experiment. Alpha particle scattering experiment. Guys, is this diagram visible to each and every single student? I hope so. Yes, yes. So, while he performing this alpha particle scattering experiment, on the basis of the results that he got over here, he basically gave us his model. He explained his model. Now see, what is this alpha particle scattering experiment? Let me make you understand. See, he took an alpha particle source, radioactive source. He took an alpha particle source. We say this is source of alpha particles. Source of alpha particles means which has a lot of alpha particles. We say source of light. Source of light means which has the light, which gives the light, which has a lot of photons present in it. Source of alpha particles mean which provides the alpha particles. Okay. Now we say this is the alpha particles which are coming out of this. Okay. This is the alpha particle source. And then he placed a gold foil. Ignore this AU. Consider this as a gold foil over here. This is the gold foil. We say this is the gold foil. Then he placed a gold foil in front of it. Okay. And then, my dear friends, behind this gold foil, he placed the fluorescent screen, a screen. Okay. Why the screen? Because on this screen, we can see these alpha particles falling. Okay. And this was the screen. This was the screen. This was the screen. This was the screen. Now, my dear friends, what did he actually do? We say a beam of alpha particles is coming out. This is what we call the beam of alpha particles. Write it over here. Beam of alpha particles. Beam of alpha particles means a large number of alpha particles are coming out. So from this source, we say large number of alpha particles are coming out. And you have this gold foil exactly over here. He saw that when these alpha particles were coming out, and guys, alpha particles have positive charge, okay? Because it is made up of protons and neutrons. So when these alpha particles are coming out, after crossing this gold foil, we say they are falling on the screen. You can see these bright spots present on the screen. Bright spot is giving us the idea this alpha particle is falling. These alpha particles are falling directly on the screen. Okay. And only few alpha particles are getting deviated. Like over here, these are only few alpha particles. Maximum number, 99.8% alpha particles are directly crossing and falling behind the screen. Okay. Now guys, listen to me very carefully. First, I'll write over here. We say, he observed when these alpha particles were crossing the gold foil, when alpha particles crossed gold foil, 99.8% were directly, 99.8% were directly falling on the screen. 99.8% alpha particles were directly falling on the screen. Only 0.14% were deviated. Only 0.14% were deviated. That is, guys, I'll write next point. That is 1 in 8,000 alpha particles. 1 in 8,000 alpha particles are deviated. Okay. So when these alpha particles were crossing the gold foil, all of them were, we say, crossing and falling onto the screen. Only some were deviated and present over here. Now guys, listen to me very carefully. From this diagram also you see. Okay. See guys, first I'll make you understand. What does it mean? What does it mean? What does it actually indicate? What does it actually indicate? So he said, guys. So he said, only that alpha particle, only that alpha particle is reflected or deviated, which hits the positive charge, positive charge. What I'm trying to say is that, guys, see. Let's suppose if I say this is the atom over here. I would want you to focus exactly on this. If I say this is the atom over here, okay? This is the atom. And we say in this atom, we say you are sending this alpha particle, these lot of alpha particles. Tell me one thing. If I say positive charge is present in the entire atom, here it is positive charge in the entire atom. You'll say, sir, this positive will repel this and it will be deviated like this. This positive will repel this positive, maximum number, like we say at least 20 to 30% alpha particles will be deviated if positive charge is present in the entire atom. But that doesn't happen. Almost all the particles were crossing. Only 1 in 8,000 was reflected back. What does this indicate? This indicates positive charge is actually present. This indicates positive charge is actually present only at one unique position. So this indicates positive charge is present only at one unique position. So the alpha particle which is along this will be reflected back. Rest of the alpha particles will cross very easily. This will cross. Only that will be reflected back, which falls on this. So from this we can say, so positive charge is present at a unique position in an atom called nucleus. So positive charge is present at a unique position called nucleus. Like you can see from this image also. Guys, we say these are the gold atoms. These are the gold atoms over here. Okay, you have a gold foil. They have got different number of atoms. Okay, now at the center of the atoms, this is the nucleus. Guys, see. This is the nucleus. Nucleus. Now, if this is the alpha particle, these are the alpha particles. Now, this alpha particle is coming, it is crossing easily. This alpha particle is coming, crossing easily. Now, see. Now, this alpha particle you see, which is along the nucleus, it will be deviated or it will be reflected back. Okay. Now, see. This alpha particle is directly crossing. And look at this, my dear friends. Take a look at this alpha particle. This alpha particle is coming and it is directly hitting the nucleus, so it is coming back. Okay. So I can say in this particular case, according to the Rutherford's atomic model, so alpha particle, we say nucleus is present only at one unique position. That unique position is what we call the nucleus. We say positive charge is present at one position. That is what we call the nucleus. Okay. And how many? We say 1 in 8,000 was reflecting back. I hope you got the feel of this topic. I hope you got the feel of this topic. And one more thing I just want to say in this particular case. What is that? What is that? If we make the graph between, this is theta and this is n. What is n? N is the number of particles reflected back. Okay, number of particles reflected back. Guys, tell me one thing. Can I say almost all 99.8% particles are directly crossing at how much angle? If they are directly crossing, means theta is 0. At theta is equal to 0 degrees, maximum number of particles are directly crossing. Theta is equal to 0 degree means particles are crossing. So graph is something like this. Okay. And when it comes to the theta is equal to 1, here theta is equal to 0 degrees. At 0 degrees, number of particles crossing are maximum. At theta is equal to 180 degrees, one particle is reflect. 180 means what? Something like this, and it comes back. Angle is 180. Okay, comes back, falls and comes back. Crossing means 0 degree. And we say at 90 degree, only few particles. So 90 degree and 180 degree, this will be the graph between n and theta. Guys, give me the signal in the chats if this is crystalline clear. Everyone. Crossing at 0 degree means, if I say, guys, this is the incoming line. Okay. And after crossing, this is the line. What is the angle between this line and this line? 0 degrees. This is the incoming line. And after falling onto the gold foil, it is reflected back. What is the angle between this line and this line? They are anti-parallel. Theta is equal to 180. At 180, how many particles are reflected back? Only one. Yes or no? How many particles are directly crossing? All. Okay. And he also said, guys, he also said, radius of atom is equal to 10 raised power minus 10 meters. And radius of nucleus is equal to 10 raised power minus 15 meters. Keep this thing in your mind. Okay. So what did he actually say? So positive charge is present at a unique position called nucleus. And he also said, electrons are revolving around the nucleus. Electrons are revolving around the nucleus in random orbits, not the fixed orbits. In random orbits means electron can revolve in any orbit. It's not like it will revolve in one only, in second orbit only, in any orbit randomly. Okay. So this was the detail. Now let's talk about the drawbacks. We said drawbacks of Rutherford's model. First one. It cannot explain the line spectrum of an atom. Sir, what is line spectrum? Please wait. We have to study the spectrum in detail after some time. Till then, wait. Okay. And still, I'll tell you. That is, when photon comes out of an atom, its energy wasn't the fixed. No, you won't be able to understand as of now. Please wait for the line spectrum until I explain this. Second, we have, it couldn't explain the stability of an atom. Yes, let's understand this. Okay. It couldn't explain the stability of an atom. as when charge moves in an orbit, okay, let me tell you what does stability of an atom actually mean. What does stability of an atom actually mean? See guys, what was the biggest drawback of Rutherford's model? We say this is the nucleus. Rutherford said this is the nucleus. And around the nucleus, he said the charge is revolving around the nucleus. The electron is revolving around the nucleus. The electron is revolving around the nucleus. Okay. He said when charge revolves, we say when electron revolves, we say this is the circular motion. This is the circular motion. And when we talk about the circular motion is an accelerated motion. Whenever a particle moves in circle, it's an accelerated motion. Why? Because it has centripetal acceleration. So this circular motion is what we call the accelerated motion. Okay. If this is the accelerated motion, my dear friends, we say here charge accelerates. So charge is accelerating. Guys, basic idea of electromagnetic wave is whenever charge accelerates, electromagnetic wave is produced. Okay. So whenever charge accelerates, we say electromagnetic wave is produced. Because we say source of electromagnetic wave is accelerated charge. Whenever charge accelerates, electromagnetic wave. What is electromagnetic wave? Electromagnetic wave is light, radiation, energy. So that means energy is released. Energy is released. Guys, means when this charge is revolving in the circle, it is radiating the energy. It is radiating the energy. Okay. It is radiating the energy. Why? Because electromagnetic wave is produced. If energy is released, if energy is radiated, my dear friends, I can say it is losing the energy. It should collapse into the nucleus. Guys, if the electron which is revolving is losing the energy, this nucleus will keep on attracting it because this negative charge, positive charge. So it will lose its energy. It will lose its energy. Okay. It will lose its energy, and it will collapse into the nucleus ultimately. So this proves atom is unstable. Atom is unstable. Okay. But we know atom is a stable system. Atom is something which is extremely stable. So he couldn't answer all of this. People asked him these questions. They asked him, atom is stable. According to this logic, atom is unstable. Please give us the answer. So that's why this was the drawback. Okay. Atom is unstable, but we know atom is stable. Atom is stable. So this was his drawback, because he couldn't give the answer to this. Now let's move on to the next model of atom. That is what we call the Bohr's model of atom. Crystal clear next. Okay. Let's talk about the Bohr's model of atom. The Bohr's model of atom basically gave the answer to this. The Bohr's first postulate gave the answer to this drawback only. So Bohr's model of atom is divided into three parts, or we say three postulates. First postulate, second postulate, third postulate. Bohr's first postulate is explaining this. Okay. Now see, Bohr's first postulate says that an atom, an electron in an atom could revolve in certain stable orbits without the emission of radiant energy. Okay. So without the emission of radiant energy. Now guys, what does Bohr actually say? Let me just tell you in the first orbit. In the first postulate. See guys, we say this is the nucleus. We say this is the nucleus. Around the nucleus, we know atom is revolving. Around the nucleus, we know atom is revolving. Okay. Electron is revolving. Okay. And my dear friends, if electron is revolving, okay, we know it is a circular motion. We know it is accelerated motion. Okay. If it is accelerated motion, we know charge is accelerating. And if charge is accelerating, my dear friends, we know, sir, wave is produced. Charge is accelerating, wave is produced. But Bohr said it is not the electromagnetic wave, but stationary wave is produced. Stationary wave is produced. And stationary wave is that wave which does not radiate energy. So means an atom, no doubt it is revolving, it is accelerating, wave is produced, but stationary. So energy is not radiating. So if it is not radiating the energy, it will not collapse into the nucleus. So it will not collapse into the nucleus. It will not collapse into the nucleus. Hence, an atom is stable. This was the first postulate. Okay. Bohr's first postulate states that an electron in an atom could revolve in certain orbits, in certain stable orbits, without the emission of radiant energy. How many of you understood this? Please tell me in the chats. Tell me, guys. How many of you understood this? And if you have not liked this session yet, I would want you to smash the like button. Everybody out there. Great. Let's talk about the Bohr's second postulate. Since I told you Bohr gave the model in 3 postulates, second postulate. Bohr's second postulate defined the stable orbits. Okay, now, let me make you understand over here. What does Bohr's second postulate say? Bohr's second postulate says that when it comes to an atom, we know at the center it has got nucleus. This is the nucleus exactly at the center. Okay. And around this nucleus, we know electron is revolving. This is electron revolving. We say, not me, he said, an electron only revolves in that orbit. An electron only revolves in that orbit, okay, in which its angular momentum is nh divided by 2 pi. So this proves that electron does not revolve in the random orbits. No, electron revolves in the fixed orbits. Only in those orbits in which its angular momentum is 2 pi. nh by 2 pi. where n is equal to 1, 2, 3 and so on. Integers, where n is an integer. Okay. Now, if you ask me, sir, I'll just write over here, like, if an electron is revolving in an orbit in which its angular momentum is h divided by 2 pi, is it possible? Yes, because n is 1 over here. If it has 2h divided by 2 pi, it can have 3h divided by 2 pi, okay, and so on. These are the possible angular momentums. Other than this, we say, let's suppose, I'll give you the question something like this. Check if an, question is, check if an electron is revolving in an orbit where its angular momentum is 3h by 4 pi. Now you need to check it. How do you check it? Guys, please say. How do we check it? We say an electron can only revolve in that orbit in which its angular momentum is nh by 2 pi. So nh by 2 pi, make it equal to 3h by 4 pi. Now pi and pi will cancel, h and h will cancel, 2 1s are, 2 2s are. So n will come out to be 3 by 2. 3 by 2 is 1.5. So we say n can be only an integer. Here it is not. So we say, so answer is no. No. An electron cannot revolve in this orbit where its angular momentum is 3h by 4 pi. So I can say in this particular case, Bohr's second postulate defines that the stable orbits, electron revolves in only fixed orbits, stable orbits, which states that electrons revolve around the nucleus only in those orbits for which its angular momentum is some integral multiple of h by 2 pi, means where it is nh by 2 pi. Okay. Is this clear, where h is Planck's constant? Is the second postulate clear? Is the second postulate clear? I hope there is no question left in the second postulate. Great. Let's talk about the third postulate. See guys, let's suppose we have an atom. This is the positive charge of an atom. And let's suppose this is the nucleus that we have got. This is the nucleus that we have got. Okay. Okay. So this is the nucleus, and around the nucleus, this is, we say, electron revolving in this one. This is another orbit. Okay, let me make one more. Let's suppose this is one more orbit that we have exactly over here. Okay. Now guys, Bohr's third postulate states that if an electron makes the transition from lower orbit, from higher orbit to lower orbit. If an electron makes the transition from higher orbit to lower orbit. Just a second, guys. What just happened? See, Let's suppose I'll make it over here. Okay. Something like this. Something like this. Okay, yeah. If an electron makes the transition from higher orbit to the lower orbit, means an electron moves from higher to lower, something like this, then energy is released in the form of a photon. Then energy is released in the form of a photon. Then in that case we say energy is released in the form of a photon. And value of energy in that case will be this energy gap. Sir, what is this energy gap? This you will understand after some time. Let's suppose if an electron is revolving in this and it has got energy over here, E3. Here energy of the electron is E1. So you can say this will be E1 minus E3. Gap. Energy is equal to energy over here. How much is the energy over here? How much is the energy over here? Difference between these two, that is the energy gap. Okay. And if an electron wants to make the transition, if an electron wants to make the transition from lower to higher orbit, if an electron wants to make the transition from lower to higher orbit, energy has to be supplied to it. Energy has to be supplied to it. Is this clear, guys? Carbon generator. Okay. So what I'm trying to say is that if an electron is moving in the lower orbit, okay, revolving in the lower orbit, if it wants to make the transition from lower to higher, so in that case we need to supply the energy. And how much energy? Energy equal to this energy gap once again. And if an electron makes the transition from higher orbit to lower orbit, energy is released. If it makes the transition from lower to higher, energy is absorbed. Okay. This is the third postulate. I hope this is crystalline clear. I hope third postulate is also crystalline clear. Now guys, let's take a look over here. We say mathematical analysis of Bohr's theory. Mathematical analysis of Bohr's theory. Just a second, guys. क्या आवाज करना चमा गई मस्ती होत पड़ रहा हूं. Now guys, mathematical analysis of Bohr's theory. What does mathematical analysis of Bohr's theory mean? Guys, see, Bohr's model as of now explained an electron in an atom revolves in the fixed orbit, stable orbits, fixed orbits, without the radiation of emission energy, without the emission of energy. Okay, Now guys, I would want you to understand one thing over here. Okay, what is that? See, let's suppose I'm taking an atom over here. This is the atom. Okay. And in this atom, we said this is the electron, which is revolving in an orbit. Which orbit? Orbit, nth orbit. Sir, what is orbit? Orbit is that path in which electron revolves. And this is which orbit? Nth orbit. Sir, for first orbit, n is 1. For second orbit, n is 2. For third orbit, n is 3. So I'm taking general nth orbit. And this is the nucleus which is present at the center. And nucleus has charge, positive charge. How much is the charge over here? Z. Sir, what is this Z? Guys, see. We say this Z means, remember from now onwards, it is atomic number. Atomic number. Sir, what is atomic number? Atomic number means number of protons. Number of protons. If I say, for this atom, if I say Z is 1, what does that mean? How many protons are present over here? We say number of protons in that case. Is 1. So how much charge it will have in that particular case? So that will be Z into E, because charge on a proton is E. So one proton has got 1 into E. If I say Z is 2, 2 protons will have 2E. If I say Z is 3, 3 protons will have 3E. So this is what we call the charge on the nucleus. Z into E. Z is atomic number. Atomic number is number of protons. Now guys, we say this electron is revolving in nth orbit. And distance between this and this is how much? We say, sir, R. Distance between, we say this and this is, we say, sir, R. Radius. And this electron is moving with a velocity V. If they ask you to find the velocity of electron in nth orbit, with what velocity this electron is revolving in the nth orbit? Okay. This is called the mathematical analysis. Okay. First we have to find velocity. Guys, see, I'll say this is the value of velocity. V is E square. E is what? Charge on an electron. Okay. 2 epsilon naught, permittivity of free space. H is Planck's constant. Z is atomic number. N is, we say, sir, orbit. Now guys, see. We say in this particular case, E is charge on an electron. H is Planck's constant. Z is atomic number. N is, we say, number of orbits. Which orbit we are talking about? Second. N is 2. Okay. So this is the velocity of an electron in nth orbit. Okay. So I say this is the velocity of an electron in nth orbit. Sir, where does this come from? There is a long derivation for this. I'm skipping that. No, there is no need for that. No need, honestly. Okay. Now guys, take a look exactly over here. Now guys, see, we know charge on an electron is 1.6 in 10 raised power minus 19. Charge on an electron is 1.6 in 10 raised power minus 19. Value of epsilon naught, permittivity we also know. Okay. 8.85 into 10 raised power minus 12. Value of H, 6.63 into 10 raised power minus 34 joule second. Okay. If you put all of these values, it will come out to be 2.2, and solve it. It will come out to be 2.2 into 10 raised power 6 Z by N. Okay. So 2.2 into 10 raised power 6 Z by N. Or you can also call it V naught into Z by N, where V naught is equal to this, where V naught is equal to 2.2 into 10 raised power 6 Z by N. Now guys, If you are talking about an hydrogen atom, for hydrogen atom, what is the value of Z? Z is 1. If you're talking about first orbit, we say, sir, n is 1. So 1 by 1, so velocity of an electron in hydrogen atom in first orbit is 2.2 into 10 raised power 6 meter per second. I hope this is clear. Next, we say radius of an electron in the nth orbit. Again, I am saying the same thing. This is the nucleus. This is the electron revolving in the nth orbit. This is the radius between them. How much is the value of radius? We say it is h square epsilon naught divided by pi into e square. H is Planck's constant permittivity charge on an electron. N square by z. N square by z. On, we say, guys, put the value of this, and solo. It comes out to be 0.53 angstrom. So instead of 0.53 angstrom, I'll write R naught over here. So N square by Z, N square by Z. So I say this is the radius of the circular path of an electron in nth orbit. If electron is revolving in nth orbit, this is its circular path, this will be the radius, this will be the value of radius. Next, my dear friends, let's talk about, we have a question over here. Find the radius of Li2 positive ions. Guys, when I talk about Li2 positive, lithium 2 positive, we say its atomic number Z is 3. For Li2 positive, atomic number is 3. For hydrogen, atomic number is 1. For helium, atomic number is 2. For lithium, atomic number is 3. Okay. Find the radius of lithium ions in its ground state, assuming Bohr's model to be valid. Okay. So we say in its ground state means n is equal to 1. That is first orbit. What is the value of radius? Guys, can I say in this particular case, as when it comes to the radius, it will be R naught, and that is n square divided by z. And we can say R is equal to, what is the value of R naught? 0.53 angstrom. And if you multiply it with 10 raised power minus 10, it will become in meters. 0.53 into 10 raised power 10. And then I can write over here n square by z. N is 1, square is 1, and z is 3 over here. 1 is 3 over here. Guys, are you able to understand what I'm trying to say over here? Tell me in the chats, everyone out there. Okay. 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 So this will be 1.76 into 10 raised power minus 11. Okay. Do check it. Next you have find the maximum angular speed of an electron of a hydrogen atom in a stationary orbit. Guys, see. Angular speed. First is what we call the linear speed. Then you have the angular speed. We are supposed to find the value of omega. Okay. Find the maximum angular speed of an electron of a hydrogen atom in a stable or in a stationary orbit. Means it is talking about the first orbit. As if I talk about, listen. We say for a hydrogen atom, always remember for a hydrogen atom, we say atomic number Z is 1. And it is talking about over here first orbit. So means N is also 1. Now guys, listen to me very carefully. We say we are supposed to find omega. We know there is a formula. Guys, one is angular speed, second is linear speed. If I say particle is moving in a circular motion, it will have angular velocity also. It has linear velocity also. Okay. If I say this rod is moving something like this, it has linear velocity only. The rod is rotating, it has angular velocity. And what is the relation between linear and angular velocity? We say, as we know, V is equal to R omega. This is the relation between linear velocity and angular velocity, where R is radius. Okay? Okay. And here I can say omega is equal to V divided by R. And here I can say omega is equal. What is the value of V? V is 2.2 into 10 raised power 6. We say Z by N. Then we say whole divided by. What is the value of, guys, what is the value of R? You say, sir, that is 0.53 into 10 raised power minus 10. In angstrom, it is 0.53 angstrom in 10 raised power minus 10. And we say N square divided by Z. Now take this in the numerator. So you can say this omega will come out to be, guys, it is 2.6 into 10 raised power minus 6 divided by 0.53 into 10 raised power minus 10. Okay. And then if it goes in the numerator, it will become Z square divided by N into it. This N will be N cube. Okay. N cube. Okay. So omega will come out to be in this particular case 2.6 divided by 0.53. If this goes in the numerator, 10 raised power, this becomes 10 raised power, we say 16. 10 raised power plus 10, 10 raised power 6. So 10 raised power 16. Value of Z is 1. Value of N is 1. Okay. Are you solving this with me, guys? Tell me in the chats. So I can say in this particular case, this will be omega is equal to 4.1 into 10 raised power 16 radian per second. Something like this only. Guys, give me the signal in the chats. Is this question crystal and clear to each and every single student? If V, you can simply find V is equal to V naught into Z by N. That is how you can simply find. R is R naught N square by Z. Recently, I told you how to find this. V is the linear velocity, na? This is how we find the linear velocity, na? Okay. Now you have got the time period. What does time period actually mean? What does time period actually mean? Guys, see, we say you have an electron. This electron is revolving around the nucleus. We say its radius is, we say, sir, R. Okay. Now, if I say it started from this point and it is completing this one circle, one cycle. So how much time it is taking in completing one cycle? That is what we call time period of revolution. So I can write over here, it is the time taken by an electron. It is the time taken by an electron to complete one cycle of revolution. Okay. How much time it is taking to complete one cycle is what we call the time period of revolution. Okay. And this time period is, guys, listen to me very carefully. It is T naught N cube by Z square. T naught N cube by Z square. T is proportional to N cube. T is inversely proportional to Z square. Okay. And value of this T naught is 1.51 into 10 raised power minus 16. This is what we call the time period. If I say you are talking about the hydrogen atom, Z is 1. First orbit, N is 1. So this will be the time period. Okay. And frequency. Let's talk about frequency, guys. When it comes to the frequency, always remember, frequency is inverse of time period. Number of cycles per second. So frequency is 1 upon, what is the value of time period? Tell me, guys. 1.51 into 10 raised power minus 16. I'll just write over here 1.51 into 10 raised power minus 16. Okay. And then we say n cube by z square. N cube by z square. Guys, can we write it something like this also? I'll write frequency is equal to 1 divided by 1.5. I can also write 3 divided by 2. 3 by 2 is 1.5 into 10 raised power minus 16, and this will be n cube divided by z square. Now take this in the numerator. If you take this in the numerator, this becomes z square by n cube, and this becomes 2 by 3. So frequency will come out to be 2 by 3 into 10 raised power plus 16 minus 16, it becomes plus 16. 10 raised power 16. Then we say n cube divided by z square. This is the value of frequency, guys. This is the value of frequency. F is 2 by 3 into 10 raised power 16 n cube by z square. Okay. Next, one more thing. That is this. What is this? This is magnetic field due to atom at the center of the atom due to the guys. Listen to me very carefully. Let's suppose you have got this nucleus over here, and around this nucleus we know electron is revolving. Okay, this is the electron which revolves around the nucleus. Okay, and guys, listen to me very carefully. This is the radius r. We know, sir, when this electron revolves, means charge is revolving. So when charge is revolving, we say current is produced. Current is produced in the opposite direction. If electron moves in the forward direction, current is produced opposite to the direction of electron. Okay, guys, see, when electron is revolving, current is produced in the loop. Guys, electron moves in the loop, current is also produced in the loop. And we have studied in the magnetism, I have told you this. If current is produced, if there is a wire in which current is flowing, it produces the magnetic field. A current carrying wire always produces the magnetic field. So we said this will also produce the magnetic field. So magnetic field is produced at the center. Magnetic field is produced at the center. And what is the value of that magnetic field due to the electron at the center? That is B naught Z cube divided by n raised power 5. This is n over here. Z cube divided by n raised power 5. Okay. Z cube divided by n raised power 5. Okay, here we say magnetic field is directly proportional to Z cube. Magnetic field is inversely proportional to n raised power 5. And what is the value of this B naught? This B naught is this one. That is 9.27 in 10 raised power minus 24. Next you have total energy. We are about to finish this chapter. And we have some okay. Next 30-40 minutes it will take and we are done with this chapter. Then we have only one chapter left. Now guys, smash the like button if you are not like the session yet. See guys, total energy of an electron in nth orbit. Total energy of an electron in nth orbit. I would want you guys to understand very carefully. See guys, let's suppose you have got this nucleus over here. Its charge is plus Zd. Okay, this is the nucleus which is present. This is the nucleus which is over here. This is the nucleus which is exactly over here. This is the nucleus. And around the nucleus, we say an electron is revolving. Around the nucleus, an electron is revolving. Okay? Okay. Now guys, I would want you to focus. This is electron which is revolving around the nucleus. Its mass is, we say, sir, m. Its velocity is, we say, sir, v. And this radius over here is r, between the nucleus and the electron. Tell me one thing. Electron has got negative charge. Proton has got positive charge. We say here between the nucleus and electron, between the nucleus and electron, potential energy is present, or potential energy exists. Why? Because if you have two charges separated by some distance, we say they have potential energy. This we have studied in electrostatics. Guys, we say potential energy between the two charges is, that is K, Q1, Q2 divided by Q1, Q2 divided by, we can say, R square. And here in this case, we say U is equal to, K means 1 by 4 pi epsilon naught. So Q1, what is the value of Q1? Q1 is this charge, Ze charge. So I can say this is Ze. And what is Q2? Q2 is the charge on electron. And guys, remember, charge on electron is negative. So we write potential energy along with the sign. So we write minus E. In case of potential energy, you always mention the sign. Divided by this instead of K, we'll write 4 pi epsilon naught. Distance between these two charges is R. Okay, it is not R square. Sorry. Okay, yes, I like this eraser. So this is basically R. Now, can I write this potential energy comes out to be over here? What happened to this, bro? What happened to its heading? Where is that gone? Let me just write over here. Energy of an electron in nth orbit. Energy of an electron in nth orbit. Now guys, see, this is, so we can say this potential energy comes out to be equal to minus Ze square upon 4 pi epsilon naught R. We mentioned the potential energy with U. Keep that thing in your mind. This is the value of potential energy. Okay. Now guys, see, you have this mass over here. Okay, you have this mass over here. It is moving with a velocity v. Whenever any mass comes in motion, it has velocity and it will have kinetic energy. Okay, we say as due to the motion of electron, it has kinetic energy. It has kinetic energy. Due to the motion of electron, it has kinetic energy. And when we talk about that kinetic energy, my dear friends, when we talk about that kinetic energy, We say kinetic energy is simply 1 by 2 mv square. We say kinetic energy is simply 1 by 2 mv square. Okay. Now guys, see. Listen to me very carefully. How do I find the expression? We say this electron is revolving around the nucleus. Cool, absolutely cool, sir. So this is performing the circular motion. Centripetal force will act. We say here, Fc. Here Fc on the electron. So we say this centripetal force. We say this centripetal force Fc is equal to, that is mv square divided by r. Centripetal force on the electron is mv square divided by r. Okay, yes. And you have two charges. We say whenever you have two charges separated by some distance, electrostatic force will also act. And electrostatic force between them, and electrostatic force between them. Okay, so we say this electrostatic force is, that is K Q1 Q2 by R square. Now I can find this electrostatic force over here also. So I'll write F electrostatic is. We say, sir, what is the value of Q in this particular case? Q1 is ZE into E will become ZE square upon, what is the value of K? 1 by 4 pi epsilon naught, 4 pi epsilon naught, and you say, sir, R square. This is the electrostatic force between the two charges. And this is the centripetal force. Why? Because these two charges, this charge, this electron is moving in the circular motion. Now we say here also both the forces are equal. We say here also F electrostatic is equal to F centripetal. So I can say in this particular case, this mv square by r will be equals to, that is Z E square upon, we say 4 pi epsilon naught r square. Okay. Now this r and this square will cancel. So here mv square will come out to be Z E square upon 4 pi epsilon naught r. Now this is the equation first. What I want you guys to do is, we say put in equation first. I want you to put this in equation first. So we say kinetic energy will come out to be 1 by 2. Instead of mv square, we'll write Z E square upon 4 pi epsilon naught r. So 2 into 4 is 8. We say this kinetic energy will come out to be Z E square upon 8 pi epsilon naught r. 8 pi epsilon naught r. So I can say this is the value. This is the value of kinetic energy in this particular case. So this is the value of kinetic energy. This is the value of potential energy. Let's find total energy. Guys. Now, total energy. I would want you guys to see. When it comes to the total energy, can I not say this total energy will be equal to potential energy plus kinetic energy? Yes. So total energy in this particular case will be, what is the value of potential energy? That is minus Z E square upon, we say 4 pi epsilon naught r. And this is plus Z E square upon 8 pi epsilon naught r. Okay. Now this guys, Z E square upon 8 pi epsilon naught r minus Z E square upon 4 pi epsilon naught r. We say this total energy will be equals to, guys, this will be 1 by 8 minus 1 by 4 is 1 by 8. This will be minus Z E square upon 8 pi epsilon naught r. If you take Z E square upon pi epsilon naught r common, what will be there? 1 by 4 plus 1 by 8, or minus 1 by 4 plus 1 by 8. It will be minus 1 by 8. So this is the total energy. Tell me, is this clear? Is this clear? Yes, remembering the formula is the only good thing that I would recommend you in this particular case. But you should have the approach in your mind. Main thing is just remember the formulas. So this is the value of potential energy, kinetic energy, and total energy. Clearly you can see, guys, total energy is equal to minus Z square upon 8 pi epsilon naught R. Kinetic energy is equal to Z square upon 8 pi epsilon naught R. Okay, here it is positive sign, here it is negative sign. Okay, so I can say in this particular case, this total energy is equal to negative of kinetic energy. Okay, and one more thing, this total energy, guys, this total energy in this particular case, don't you think that it is Z square upon, if you multiply 2 over here, 2 into 4 becomes 8. So I can say this mod of total energy, you can write it something like this, is equal to mod of potential energy divided by 2. Mod of potential energy divided by 2. Okay. So potential energy divided by 2 is equal to this. Okay. Cool. Now guys, listen to me very carefully. Listen to me very carefully. What we are going to discuss now is graphs. Yes, graph between this and this. Let's plot the graph. See, graph between energy versus R. What is the first thing we are supposed to do? Guys, see. I say when it comes to the potential energy, U is potential energy. Potential energy is equal to, you say, sir, it is minus Z E square upon 4 pi epsilon naught R. So I can say this potential energy is inversely proportional to R, and it is negative. Potential energy is inversely proportional to R and its value is negative. Second, when it comes to the total energy, this is the first thing. Second thing, when it comes to the kinetic energy, we say kinetic energy is minus Z E square upon, we say 8 pi epsilon naught R. So we said this kinetic energy is inversely proportional to R and it is negative. Yes. Next, we say total energy. Total energy is minus, kinetic energy is positive. Kinetic energy is positive, so it is positive. Okay. When it comes to total energy, it is Z E square upon 8 pi epsilon naught R. So this total energy is also inversely proportional to R and it is negative. It is negative. Let me now plot the graph between energy versus, let me plot the graph between energy versus time, energy versus R. Okay. Let me plot the graph between energy versus, I would say this is energy E, and on this axis you have got R. Guys, first thing, I'll plot all the three graphs, kinetic, potential and total. See, potential, first of all, kinetic energy. Kinetic energy is positive. Positive energy is from upper side, negative energy from the lower side. So we say kinetic energy graph I'll be making from the upper side. This is kinetic energy is inversely proportional to R and is positive. And then if I make, sir, total energy over here, total energy is total energy is, we say, negative. So I'll make the graph from lower side, and it is inversely proportional to r. So here also it will be rectangular hyperbola, but it would be something like this. It would be something like this. Okay, so this is total energy over here. And in between this, I'll make which potential energy? So potential energy in this case, I'll make over here. This is potential energy. So why did you make it over here? Because if you check over here, guys, this is total energy is ZE square divided by 8. So in the denominator, value is more. So total energy will be less. Okay, in this particular case. Okay, and you can say in this particular case, potential energy, oh, I made a mistake here. Just this will be total and this will be potential. Okay, so this over here is potential and this over here is total energy. No, again. This is more. Okay, this is potential and this is total. This is total. Yes, this one. See, in this case, you can see total energy from the negative side. It is divided by 8. It is less. So guys, if we say from the upper side, this is, sir, as you go high, energy will increase. As you go low, energy will increase from the negative side in this particular case. Okay. So we say this will be over here total and this will be over here potential. Is this clear? Please tell me in the chats. Is this clear? Is this clear? Why did I make this total over here? It is because from the negative side, total is less than this potential. That's why, because it is ZE square divided by 8. It is ZE square divided by 4 only. So from negative side, this is more. So more will be this is less. Guys, give me the signal in the chats if everything is crystal and clear. Now guys, take a look over here. One more thing I just want to mention. What is that? See, we say as when it comes to the total energy, what will you say? It is minus ZE square upon 8 pi epsilon naught r. Guys, this is the value of total energy actually. This is the value of total energy actually. Now, can I say, as we know, what is the value of this r? R means r naught n square by z. Now, I say put in the equation first. Put in equation first. If you put this value in equation first, you'll get total energy is equal to, that is minus ZE square upon, and here you will write 8 pi epsilon naught. And when it comes to this r, instead of this r, you will be writing r naught, and this is n square divided by z. R naught n square divided by z. Now guys, when it comes to this, if you take this z and multiply over here, we say this total energy will come out to be, total energy will come out to be z into z becomes z square minus z square e square divided by, now guys, here, and you write it something like this. See, z into z becomes z square. You write it minus e square in the numerator upon, here you will be writing 8 pi epsilon naught r, and in the numerator it is z square, in the denominator it will be n square. Now, in this particular case, what is E? E is the charge on an electron. What is pi? Pi is pi. Epsilon naught, permittivity of free space. R, and this is R naught. You know the value of R naught? 0.53 angstrom. So if we put the values of charge on an electron, pi, epsilon naught, r naught, then if we solve it, it comes out to be total energy comes out to be equal to, if we solve all of this, it comes out to be minus 13.6. Then we say z square divided by n square. Z square by n square. This is an important formula. Okay. And guys, if you remember, as we say total energy is exactly equal to the kinetic energy. Okay. But this is positive. This is positive. So we can say, but this is what? This is what? Positive. So we can say, so I can say this kinetic energy is equal to minus, this will be exactly over here. That is 13.6, or you can say minus of kinetic energy and right over here, minus kinetic energy. So it will be minus, and what is the value of this over here? So you write it something like this. This is mod of this is equal to mod of Ke. So this kinetic energy will be simply, that is 13.6 z square divided by n square. I want you to put this in a box. Okay. So this kinetic energy is coming out to be this. Now guys, please have a look. Do you remember in case of de Broglie wavelength of an electron revolving in the nth orbit? Yes, this. So we say this is the kinetic energy of an electron in nth orbit. In nth orbit. Guys, see. If we more specifically talk about hydrogen atom, we say for a hydrogen atom, can I say value of Z is 1? If we talk about hydrogen atom, value of Z is 1. So can I say in that case total energy will come out to be, it is minus 13.6, minus 13.6. What is the value of Z? 1 divided by n square. This comes out to be the equation for total energy. Okay. And when it comes to the kinetic energy, I can say this kinetic energy is equal to, we say 13.6. This will be Z square divided by n square. Okay, what is the value of Z? Z will be 1. 13.6 divided by, we say, n square. So this is the value of kinetic energy. Okay, this is for hydrogen atom. For hydrogen atom, total energy of an electron in nth orbit, kinetic energy of an electron in nth orbit. How many of you understood this? Please tell me in the chats. We'll be taking the break at 11:30. Don't ask me the break till then. Okay. Tell me. Now, I just want to write one more thing over here. Guys. See, we say, I'll just write over here. Ground state energies. Ground state energies in hydrogen, helium, lithium. Hydrogen, helium, lithium. Now guys, see. When it comes to for a hydrogen atom, we say, listen to me very carefully. Z is equal to 1. We say total energy of an electron in ground state. So what will be the value of total energy of an electron in the ground state? We say when it comes to the hydrogen atom, Z is 1 and value of N is 1. So total energy in that case will come out to be minus 13.6 Z square by N square. Z is 1, N is 1. So this total energy comes out to be minus 13.6 electron volts. Next, if we talk about for a He positive helium, we say what Z is 2 and N is 1, because we are talking about the first orbit of helium. We are talking about first orbit of helium. So when it comes to the helium, atomic number is 2. Okay. We say N is 1. So what will be the value of total energy of an electron? Total energy of an electron, we say will be equals to, that is minus 13.6 Z square by N square. Z is, we say, sir, 2 square by 1 square. So this will come out to be total energy is equal to minus 54.4 electron volts. So total energy of an electron in the first orbit of helium is 54.4. And if we talk about for a Li2 positive, we say Z is equal to 3, N is equal to 1. We are talking about the ground state only, na? So this total energy will come out to be minus 13.6 into Z square by N square. Z is how much? That is 3 square by 1 square. So this total energy comes out to be minus 122.2. Okay. So electron volts. This is the total energy of an electron in the first orbit of Li2 positive. In the first orbit of Li2 positive. Okay. Great. Next. Okay. Now guys, focus on this one. Definitions valid for single electron system. Definitions valid for single electron system. Let's see. When it comes to, let's suppose this is an atom over here. This is the nucleus. So we say this is what we call the first orbit. If an electron is revolving just outside the nucleus in this path, this is called first orbit. And value of first orbit is 1. It is also called the ground state. Either you call it ground state or first orbit, N is equal to 1. And then we say this one is what we call the second orbit. Second orbit. It is called first excited state also. And its N is equal to 2. Okay, here N is equal to 2. Then you have the third orbit. This is third orbit. And it is called second excited state. It's called second excited state. And value of N is 3 over here. For this, N is 3. Then you have the fourth orbit, last one. This is not the last, fourth one. So N is 4 over here. We say it is called the third excited state. Okay. For nth orbit, we say it is N minus 1th excited state. For nth orbit, it is N minus 1th excited state. Cool? Yes. Now, I can say over here, if we talk about a hydrogen atom, guys, see, if we talk about a hydrogen atom, what I can say in this particular case is, we say, as when it comes to the total energy, you say simply it is minus 13.6, okay, minus 13.6 divided by N square when it comes to the hydrogen atom. If I say for first orbit, okay, N is equal to 1. Could you please tell me what will be the value of total energy? We say, sir, total energy of an electron in first orbit of hydrogen atom. What is the value of N? 1. 13.1. Sorry, minus 13.6 divided by 1 square is minus 13.6 electron volts. Okay. Let's talk about We say second orbit. Means if an electron is revolving in the second orbit of hydrogen atom, what will you say for second orbit? N is 2. We said this total energy will come out to be minus 13.6 divided by 2 square. 2 square is 4. So minus 13.6 divided by 4 is minus 3.4 electron volts. So if an electron is revolving in the second orbit, how much energy it will have? Minus 3.4 electron volts. If we talk about the third orbit, we say for third orbit value of N is 3. So what will be the value of total energy? You say, sir, that is minus 13.6 divided by 3 square. That is 9. So it will be minus 1.51 electron volts. Similarly, if you talk about the fourth orbit, guys, you should remember all of these like I am remembering, okay? So value of this is 4. So total energy will come out to be minus 13.6 divided by 4 square. 4 square is how much? 16. So this will come out to be minus 0.86 electron volts. And if we talk about the fifth orbit, we say for fifth orbit N is equal to 5. So we say total energy will come out to be simply, that is minus 0.38 electron volts. So this is the energy of an electron in the fifth orbit. This is the energy of an electron in the fifth orbit of hydrogen atom. Okay. Lyman series, Balmer series, I'll tell you after some time. Wait. Take a look at the question. This was asked in NEET 2016. 19. The total energy of an electron in an orbit is minus 3.4. Total energy is given as minus 3.4 electron volts. Okay. Total energy of an electron is given as minus 3.4 electron volts. Its kinetic energy and potential energy will be, guys, when it comes to the kinetic is just the positive of total. So it will be 3.4 electron volts. Now let's find potential. Guys, see, we said total energy is equal to kinetic energy plus potential energy. What is the value of total? Total is minus 3.4 electron volts is equal to kinetic is 3.4 plus potential we are supposed to find out. Take it over here. It will also become minus 3.4. Minus 3.4 plus minus 3.4. So it will become potential energy will come out to be minus 6.8 electron volts. So 3.4 and minus 6.8, option C. In a Bohr's model of hydrogen atom, the ratio of periods of revolution in n is equal to 2 to n is equal to 1. Guys, see. It says that you have got a hydrogen atom. Okay. An electron is revolving in the second orbit. An electron is revolving in the second orbit. And an electron is revolving in the first orbit. Okay. An electron is revolving in the second orbit. This is the second orbit. N is equal to 2. Here, first orbit, N is equal to 1. Okay. And it says over here, in N is equal to, N is equal to 1. We are supposed to find the time period of revolution. Guys, see. I want you to understand one thing. When it comes to the time period of revolution, it is simply T naught N cube by Z square. I forgot. T is equal to T naught N cube by Z square. Yes. T naught, we say n cube divided by z square. Now, since it is talking about the hydrogen atom, we say for both the electrons, we are talking about the same atom, hydrogen. So I can say in this case, Z is same, constant, T naught is constant. So we say time period will be only proportional to n cube. So now, time period in the second orbit divided by time period in the first orbit will be equals to, guys, n cube. We say what is n for second orbit? That will be 2 cube divided by 1 cube. So that is 8:1. So option which is matching? Option C. Okay. Option C is matching. Now, okay, let's solve this first. Consider the third orbit of He, helium. Okay. Using non-relativistic approach, the speed of the electron in this orbit will be, guys, see, when it comes to the helium, it says that third orbit of helium, for helium, we say Z is equal to 2. And it is talking about the third orbit of helium, means an electron is revolving in the third orbit of helium. Sir, fifth orbit is minus 0.541 and the same thing, bro. Okay, where is it? Minus, okay, sorry, minus 0.54. Minus 0.54. Guys, correct it. One of my friend in the chats told me this. Okay. Not one and the same thing, my mistake. Okay, it is 0.54 minus 0.5. Now see, when we talk about the helium, okay, when we talk about the helium, we say Z is equal to 2, N is equal to 3. It is talking about the third orbit. It is talking about the third orbit. Okay. The speed of an electron in this orbit will be, guys, how to find the speed? V is equal to 2.2 into 10 raised power 6. We say Z by N. V is equal to 2.2 into 10 raised power 6. What is the value of Z over here? That is 2 divided by 3. Okay, third orbit of He positive. Cool. Okay, so this will be the speed in this particular case. Okay. Yeah, Z is 3. N is 2. Cool. Now see, check it which option is matching. Next one we have this one. Okay, first let's solve this. The ratio of speed of an electron in third orbit of He. Okay. Guys, see. The ratio of speed of an electron of third orbit of He. When it comes to in He positive, helium positive. What is the value of Z? That is 2. And which orbit it is talking about? We say, sir, N is equal to 3. What is the speed of an electron in third orbit of helium? Yes. Okay. To the speed of electron in the third orbit of hydrogen. In hydrogen, what is the value of Z? 1. And it is talking about the third orbit, that is 3. Okay. Now, guys, we say as we are supposed to find velocity of electron in helium divided by velocity of electron in hydrogen. VHE divided by this, the ratio of speed of an electron in third orbit of helium to the speed of an electron in third orbit of hydrogen. Okay, detail is given. Now tell me, sir, when it comes to the velocity, it is V naught Z by N. So velocity is directly proportional to Z by N. V naught is constant. So I can write over here, V is equal to V naught Z by N. What is Z for this? That is 2 by 3 upon. What is Z for this? That is 1 by 3. Now it will be 3 into 2 is 6 by 3. 3 ones are 3 twos are. That is 2:1 is the correct answer. The ratio is 2:1. Okay, now let's solve this. This is actually a good question. See, guys, the question says, read it very carefully. The electron in the hydrogen atom jumps from excited state n is equal to 3 to its ground state n is equal to 1. From n is equal to 3 to n is equal to 1. Guys. The question says that in an atom, this is positive. This is the nucleus over here. And around this nucleus, you have got the orbit. This is the second orbit. Okay. And I'll make one more in between this and this only. Yes. Now, guys, take a look. It says that the electron in an hydrogen atom jumps from n is equal to 3. This is the third excited state. N is equal to 3. N is equal to 3 to n is equal to 1. It moves from n is equal to 3 to n is equal to 1. Okay. Yes. So an electron jumps from n is equal to 3 to n is equal to 1. Thus the photon thus emitted falls on the photosensitive. Guys, we know that when an electron jumps from higher orbit to the lower orbit, energy is released. Okay. When an electron jumps from higher orbit to lower orbit. When an electron jumps from higher orbit to lower orbit, energy is released. Bohr's third postulate, energy is released in the form of a photon. In the form of a photon. Okay. Okay, in the form of a photon. Okay. Now, guys, listen to me very carefully. In the form of a photon. And could you please tell me what will be the energy of that photon? We say energy of that photon will be energy gap. Whatever is the energy of photon in this one. Now you are able to understand, sir. That will be E1 minus E3. So energy of that photon will be. What is the energy of a photon in this first orbit over here? Or that is final minus initial, initial minus final. Okay. So can I say in this particular case, guys, or you can say simply in this particular case, that is this energy initially minus energy finally. What is the energy initially in the third orbit? That is 1.51. Okay, energy initially is minus 1.51 electron volts. Energy of an electron in this one is minus 1.51. And then energy finally when it reaches this final orbit. So that will be minus 13.6. So I can say energy of this photon will come out to be 1.51 plus 13.6 means this will be 13.6 minus 1.51. So it will come out to be 12.1 electron volts. Okay. So energy of that photon will be 12.1 electron volts. Okay. Now let's suppose that photon is this. This is that photon. Okay. This is that photon. This is that photon. Okay. And it says that falls on a photosensitive metallic surface. This is a photosensitive metallic surface. So this photon falls over here. Okay. We know when it falls on the photosensitive metallic surface, We say, sir, electron is ejected in this particular case. Okay. So we say when it falls on the photosensitive metallic plate, we say electron is ejected. When it falls on the photosensitive metallic plate, we say electron is ejected. And my dear friends, electron is ejected, so photoelectric effect takes place. Okay. And we are supposed to find a photoelectric. So photoelectric effect takes place. And we are supposed to find the stopping potential. Guys, tell me one thing. We are supposed to find the stopping potential. And work function of this is given as 5.1 electron volts. We say, so energy of photon is equal to work function plus kinetic energy maximum. What it says that an electron makes the transition from n is equal to 3 to n is equal to 1. A photon is thus emitted. It falls on the photosensitive metallic plate. Now here, photoelectric effect will take place. If photoelectric effect takes place, it will have the stopping potential. So I can say in this particular case, energy of photon is how much? That is 12.1 electron volts is equal to, work function is given as how much? That is 5.1 electron volts. Okay. Okay. And what is kinetic energy maximum? EV naught. This is what we can say. Take it over here. 12.1 minus 5.1. This will be 7 electron volts is equal to EV naught. This and this will cancel. V naught is equal to 7 volts. V naught is equal to 7 volts. So which option? Option D. Now comes the concept of spectrum. Now comes the concept of spectrum. Now comes the concept of spectrum. Now guys, see, listen to me very carefully. When it comes to the spectrum, and this is the definition, for the first time I am using this definition. After this, I'll show you with my own physics definition, but this is the definition which Wasim sir uses. And okay, and I saw this definition of spectrum from his video. This is his example actually. Now see, okay, after this I'll show you mine, that old one which I use every single time. Now see, spectrum, it is the collection of radiations of different wavelengths on a photographic plate. Now guys see, I would want you guys to focus exactly over here. Listen to me very carefully. Let's suppose you have got this white light exactly over here. Okay, you have the bulb. Okay, from that bulb we say white light is coming out. And you place a prism over here. We say this prism basically splits this white light into 7 different colors. What is the work of the prism? This we'll study in the ray optics. What is the work of the prism? The work of the prism is it divides this white light into 7 different colors. Okay, this is the first one: violet, indigo, blue, green, yellow, orange, and red. Okay. Okay. Now, my dear friends, in this, yes, dispersion. Now, my dear friends, in this particular case, we say you have got over here this spectrum. You have got over here this spectrum. Okay. And when it comes to the spectrum, I would want you to focus exactly over here. What is the spectrum? This is a screen actually. This is a screen. This is a screen. You place a screen over here on which these lights fall. These lights fall. Okay. Now, my dear friends, when this light falls over here, this makes the red dot. Okay. Red line, red dot, spot. This makes orange spot. Okay. Green spot, blue spot, indigo spot, violet spot. Now, these spots, creation of the spots, creation of these lines on this surface, on this photographic plate, on the screen is what we call the spectrum. Creation of the lines on this surface is what we call the spectrum. Okay? Creation of these spots on this photographic plate is what we call the spectrum. This is the basic definition. Now, this light will have different wavelength because it's a red spot. Wavelength of red is different. Orange will have different wavelength. That's what is mentioned. It is the collection of radiations of different wavelengths on a photographic plate. Or it is an image produced on the photographic plate. Okay? Okay. Now, my dear friends, I would want you guys to focus on this. See over here. Now, let's understand the same spectrum with the help of the Bohr's model. Since we are talking about the atomic spectrum, we'll understand this with the help of this Bohr's model. Now, guys, you said over here, I am sending, sir, this white light, a radiation. Light itself means photon, so you are sending photons. Now, see, I am sending the photon over here. This is an atom. Guys, understand please very carefully. I'm sending a photon exactly over here. I'm sending a photon exactly over here in this particular case. Okay. Yes. I'm sending a photon exactly over here. Okay. So when I'm sending a photon exactly over here, this is the screen that I have placed, and on the screen, you can see this dark spot is being created. This creation of the lines, how this is created, I'll tell you, is what we call the spectrum over here. And before this, please focus over here. We say there are two types of spectrum, absorption spectrum and emission spectrum. Absorption spectrum and emission spectrum. See guys, what I'm trying to say is that, let's suppose I'll take an atom over here. And in this atom, we said this electron is revolving in the first orbit. Okay, this is in the first orbit. And if I ask you, what is the energy of an electron in this first orbit? You say, sir, it is minus 13.6 electron volts. If I say, what is the energy of an electron? What is the energy of an electron in this orbit? You say, sir, it is minus 1.51 electron volts. Or, sir, what is the energy of an electron in this one? It is minus 3.4 electron volts. Okay. Now, could you please tell me, what is the energy gap between this and this? How much is the energy gap between this and this? We say energy gap between n is equal to 1 and n is equal to 2. And n is equal to 2. What will you say? Sir, this energy gap is simply, that is 13.6 minus 3.4. How much is this? You'll say, sir, 13.6 minus 3.4 will be 10.2 electron volts. Okay. Okay. They consider the magnitude only, 10.2. Now, what I want you guys to understand is that if I say, you have to make the transition of this electron from first to second orbit. You have to make the transition of this electron from first to second orbit. What will you do? You say, sir, what I'll do is that I'll give the energy to it, because Bohr's third postulate says that if you want to make the transition from lower orbit to the higher orbit, if you want to make the transition from lower to higher, you have to give the energy to it. And that energy should be equal to the energy gap between the two. So if we want to make the transition of electron from n is equal to 1 to n is equal to 2. Tell me, we will basically send the energy. How we are going to send the energy? So we are basically sending a photon in this particular case. So we send a photon of energy. We send a photon of energy. E is equal to 10.2 electron volts. Sir, what if we send less than 10.2 electron volts? Then we say it will not make the transition. It will only make the transition if you send the energy equal to the energy gap. If you want this electron to make the transition from this 1 is equal to this, then the gap is 12.1 electron volts. Then you have to give the photon of energy 12.1 electron volts. It will make the transition from n is equal to 1 to n is equal to 3. Okay. Now, when you send a photon of n is equal to 1 to n is equal to 3, this electron will absorb that energy. This electron will absorb that photon. We say we send a photon of energy 10.2 electron volts and it is absorbed. It is absorbed by the electron. It is absorbed by the electron. When this entire energy is absorbed by the electron, guys, see. We say on this bright screen, a dark spot is made. On this bright screen, a dark spot is made. On this bright screen, a dark spot is made. What is the meaning of this dark spot? Meaning of dark spot, this gives us an idea that energy has been absorbed. Light has been absorbed. No light is falling at this point. So no light is falling. That's why we are getting the dark spot over here. So this is what we call the absorption spectrum. Formation of these dark spots is called the absorption spectrum. Okay. And it is absorbed by the electron, and a dark line is formed on the screen. This is called absorption spectrum. This is called absorption spectrum. So what does this dark line actually mean? It means that energy has been absorbed by the photon. No light is falling actually at this point. So we say that's why we are getting the dark spot exactly at this point. So this is the dark spot on the bright background. So spectrum, what does spectrum mean? Creation of the lines. Absorption means when electron absorbs the energy, absorbs the photon. Give me the signal in the chats. Is this point clear to each and every single student? Everyone means everyone. Okay, great. Now. Emission spectrum. Understand this. See, guys. Let's suppose an electron is revolving in the higher orbit. It makes the transition from higher to lower. We know in that case, energy is released. Energy is released in the form of what? In the form of a photon. Energy is released in the form of a photon. Now, this photon is what? Light. So we say, when it falls onto the screen, here bright spots are formed. Okay, these bright spots, okay. Sir, will this red, orange, yellow, which one will be formed? Depends upon the wavelength of this photon. If the wavelength of the photon is equal to the wavelength of red, then red spot will be formed. Okay, so we say when an electron moves from higher orbit to lower orbit, when an electron moves from higher orbit to lower orbit, energy is released. Energy is released in the form of a photon. Energy is released in the form of a photon. Okay, which falls on the screen, and bright lines / spots are formed. This is called emission spectrum. Okay, and we say it depends upon the wavelength of the light, wavelength of the photon, and accordingly here bright lines will be formed. If its wavelength is equal to the wavelength of red, then red spot will be formed, yellow spot will be formed, this will be formed. And this is what we call the spots on what? Spots on dark background, bright spots on dark background. In case of emission spectrum, we say it is bright spots on dark background. What is emission spectrum? If an electron makes the transition from higher orbit to lower orbit, photon is released and bright spots are formed. This is called the emission spectrum. Okay, and what is absorption spectrum? When an photon is sent to an electron, it is absorbed by it, and then it makes the transition from lower to higher. We say dark lines are formed, dark spots. This is called absorption spectrum. Guys, give me the signal in the chats. Is emission and absorption spectrum crystal and clear? Please tell me. Please tell me. I hope there is no confusion left from now onwards in the emission and absorption spectrum. So break till 12 a.m. Okay. So let's meet exactly at 12. Guys, do not leave this. Okay. We have completed the atoms also. Now after this we have just one topic and we are starting the nuclei. And in nuclei we'll give 1.5 hours and we'll get done with that. Okay. So chill. So we have finished almost. So don't leave in the middle. Take care. See you guys at 12 a.m. So guys, we are back again. So let the people join and let's dive into the session. Now guys, let's take a look exactly over here. I would want you guys to focus exactly over here. See, we have Lyman series. This is what we call the spectral series, okay? Spectral series of the hydrogen atom. What does this Lyman series, what does it actually mean? Now see, we say, when an electron makes the transition from higher orbit to the lower orbit, guys, we know in that case, we say lines are exactly formed over here. Understand very carefully. And these bright spots or lines is what we call the emission spectrum. Cool. Now we are showing these lines on the screen over here. Cool. Yes. What if I tell you to show these lines on a kind of graph, something like this? To show these lines on these orbits over here. Like I'm saying, when an electron makes the transition from higher orbit to lower orbit. When an electron makes the transition from higher orbit to lower orbit, emission spectrum, okay, takes place. Lines are formed on the screen, okay? We say bright lines are formed on the screen, okay? Now, showing those bright lines on these spectral series is what we call, like we say, Lyman series, Balmer series, okay? Now, let's show those lines on the spectral series. Okay, like the first spectral series we have over here, Lyman series, or we call it K series. Now see guys, with the help of this line, this is what we call the first orbit. Sir, how do we make the spectral series like this? I'll show you. We say this is what we call the first orbit of an atom. We represent, in case of spectral series, we represent the first orbit of this with a straight line. Then this orbit, second orbit, this is the second orbit, third orbit, fourth orbit, fifth orbit, and this is the last orbit, n is equal to alpha. Okay, so we are showing, in case of the spectral series, this is spectral series, we represent these orbits with the straight lines. Okay, now guys, if I say an electron makes the transition from higher orbit to the first orbit, what I'm trying to say is that if an electron in an atom makes the transition from higher orbit to the first orbit, then we say, sir, lines are formed on what? Sir, screen. We show those lines something like this on the spectral series. So we say Lyman series is, guys, I'll just write over here, in Lyman series, we show lines when electron moves from higher orbits to first orbit. When electron moves from higher orbit to the first orbit, then we show those lines in the spectral series. In which series? That is Lyman series. Now guys, let's suppose there was an electron which is in the second orbit. It is making the transition from second to first. So we represent it with this line, that is what we call the K alpha. This is what we call the first line. So I'm saying, sir, if you show this in the spectrum, we say electron makes the transition from second to first, line will be formed on what? Emission spectrum. That line on the spectral series is this. And this is what we call the K alpha, or this is what we call the first line. Okay. If an electron makes the transition from n is equal to 3 to n is equal to 1, we show it with this line. This is what we call the K beta, or we also call it the second line. And then if an electron makes the transition from n is equal to 3 to n is equal to 1, then we call it the K gamma. This is what we call third line. Similarly, this is the next line. If an electron makes the transition from 4 to 1, if an electron makes the transition from 5 to 1, if an electron makes the transition from, we say last line to last orbit to first orbit. Okay, this is the last line. This is what we call the last line of Lyman series. Okay. Now guys, if we talk about this first line, K alpha, don't you think that in this particular case, what about the energy gap over here? In this case? Okay. What about the energy gap in this particular case? Guys, if an electron makes the transition from higher orbit to the lower orbit, how can you find this energy gap? Sir, that is 13.6 minus 3.4, that will be this gap. So we say in that particular case, guys, we say energy will be minimum as compared to if the electron makes the transition from here to here. Energy will be minimum. So when it comes to, guys, we say first line. If we talk about the first line, okay, we say energy will be minimum. Energy is minimum. If energy is minimum, means frequency is minimum. Okay. If frequency is minimum, we say lambda, wavelength, will be maximum. Okay. For the first line of Lyman series, so wavelength is going to be the maximum, but energy frequency is going to be the minimum. And when it comes to the last line, guys, we say last line. We say energy is going to be maximum and frequency is going to be maximum. So lambda is going to be minimum. For last line, we say this is going to be minimum. So if the electron makes the transition from higher orbits to the first orbits, so we represent in the Lyman series, in the spectral series, which one? Lyman series. This is the first line, second, third. Okay. Next we have Balmer series. What does Balmer series mean? We say if the electron makes transition from higher orbits to n is equal to 2, okay, to n is equal to 2, to the second orbit, then in that case we say in Balmer series. So Balmer series says that if an electron makes the transition from higher to second, so then we can represent this will be the first line in this particular case. This is also called L series. Okay, so we can represent what is this actually. This is the transition from this, and this is the line formed on the emission spectrum. This is the line formed on the emission spectrum. Okay, so we say this is the first line L alpha, this is the second line L beta, this is the third line, we say L gamma. Okay, and here final orbit is an initial. In this particular case, you can say n final is what? We say 2. N initial can be, we say 3, 4, 5 and so on. What about this? When it comes to the Lyman series, guys, we say here n final is 1. Finally, you have to move on to the first orbit, and n initial can be 2, 3, 4 and so on. Okay, and here also this will have the maximum wavelength, but frequency will be minimum and energy will be minimum. And this is, we talk about the first line. Next, my dear friends, is we say that is Paschen series, okay, or we call the M series. Now, if an electron makes the transition from n is equal to 4 to 3, final destination is third orbit, then we say line will be formed on the emission spectrum. But here in the spectral series, we show that line in which series? In Paschen series. If the electron makes transition from n is equal to 3 to n is equal to 1, we show that in Lyman series. If the electron makes the transition from n is equal to 5 to n is equal to 3, we show that in Paschen series. Because here I am saying in this particular case, we say final n final is 3, and initial can be 4, 5, 6 and so on. Okay. And here, this is what we call the last line. For last line, n is equal to alpha. Here also, in this case, first line will have maximum wavelength, minimum frequency, minimum energy. And last line will have, we say, maximum energy, maximum frequency, but minimum wavelength. Okay. Next. Then you have the bracket series. Then you have the, and here, we say finally electron reaches to the 4 and initial orbits can be these. And then you have the P-fund series. So what these spectral series is all about basically? It tells us if an electron makes the transition from higher orbits to lower orbits. On the emission spectrum, on the screen, you show it with the help of lines. But in spectral series, you also show it with the help of these lines. Okay? Now depends. If electron makes the transition to third orbit finally, then you show it in Paschen series. If electron makes the transition in second orbit, then you show in Balmer series. Then if electron makes the transition to the first orbit, then you show it in Lyman series. Guys, please tell me in the chats if this is crystalline clear, because this is something which I feel is confusing. Tell me. Tell me. Great. Enough. Guys. Since if I say electron makes the transition from n is equal to 2 to n is equal to 1, what actually is happening in reality? A photon is coming out, okay? And that photon falls on the photographic plate on the screen and line is formed. That line is here. And this photon will have the wavelength. This line, bright spot, will have the wavelength. So, how to find the wavelength of this line? Or you say wavelength of that photon, or you say wavelength of that bright spot. One and the same thing. So let me tell you how to find the wavelength, how to find the wavelength of the photon emitted. Guys, see, wavelength of the photon emitted. We say directly, there is a long derivation for this, we don't go there. 1 by lambda, and 1 by lambda as a whole is what we call the wave number. 1 by lambda is wave number. Lambda is wavelength. 1 by lambda is wave number. And this is m e raised power 4 z square 8 epsilon naught square h cube c. What is m? M is mass of electron. What is E? Charge on an electron. What is Z? Atomic number. What is epsilon naught? Permittivity of free space. H, Planck's constant. C is speed of light. Now all of these things you actually know, we have discussed these. And then we say 1 by n final. Final means if I am saying electron is making transition from n is equal to 3 to n is equal to 1, means n initial will be 3, n final will be 1. So after putting up these values, guys, we say replace all of these with a single constant, that is what we call R. And this R is called the Rydberg constant. Or if you put the values over here, its value comes out to be 1.03 into 10 raised power 7. 1.03 into 10 raised power 7. Okay, or we can say this is R. So where R is Rydberg constant. Where R is called Rydberg constant. So my dear friends, from now onwards, if somebody says an electron makes the transition, if somebody says an electron makes the transition from n is equal to 3 to n is equal to 1, we say photon is released, that falls on the photographic plate, makes a bright spot, okay, makes a bright line. That line in the spectral series we show something like this. And this line will have the wavelength. And how to find the wavelength of this line? That is 1 by lambda is equal to R into 1 by n final square minus 1 by n initial square. Please tell me how many of you got the feel of this particular equation. Please and please, everybody tell me in the chats. How many of you got the feel? What does this equation actually say? You got it? Please tell me. Great. And this is the value over here. You need to remember this. Now guys, let's talk. This was the question which was asked in NEET 2017. See, what does the question actually say? The ratio of wavelength of the last line of Bohr series. The ratio of wavelength of the last line of Bohr series and the last line of Lyman series. Guys, when it comes to the last line of Bohr series, we say, tell me one thing, last line of Bohr series. Guys, when it comes to the last line means n initial is infinity. N initial is, we say, sir, infinity, alpha, whatever you say. This one, n initial, this is the last line of Bohr series. So initially, we say electron was at infinity. Then it is moving to the second shell. Okay, so n is equal to 2 and final is equal to 2. So I can say n initial is equal to infinity, n final is equal to 2. Okay, so you guys are supposed to tell me how to find the wavelength. Sir, it is easy. So we can say 1 by lambda 1, 1 by lambda 1 is equal to, sir, R. We say 1 upon n final square minus 1 upon n initial square. Okay, so I can say 1 upon lambda 1 is equal to R. What is final? That is 2. 1 by 4. It will come out to be 1 by 2 square is 4 minus 1 by infinity. So this will be 0. So this will be R by 4. So 1 by lambda 1 is coming out to be R divided by 4. Okay. Okay. Now, my dear friends, tell me one thing. Let's talk about last line of Lyman series. Last line of Lyman series. When it comes to the last line of Lyman series, what is the value of n initial? Obviously, that is infinity. What is the value of n final? That is 1. Because finally, it is coming on to the 1 when it comes to the Lyman series. Now, you tell me one thing. If I find the wavelength of this line, wavelength of that line, so we say 1 by lambda 2 is equal to, that is R into 1 by, finally, it is 1. Then minus 1 by infinity. 1 by infinity is 0. So this will come out to be over here. Lambda 2 will come out to be over here. 1 by R. And when you check lambda 1, take this lambda over here, 4 over here. So lambda 1 will be equal to 4 by R. So can I say from this, my dear friends, so I'll just write lambda 1 divided by lambda 2 will come out to be, lambda 1 is 4 by R divided by lambda 2 is 1 by R. This and this will cancel. So it is 4:1. Okay. Okay. Great. Great. Next. Can you solve this question? This was asked in NEET 2016. Given the value of Rydberg constant as 10 raised power minus 7 meter inverse. Okay. Okay. Like I told you in this particular case. Okay. Great. Now. The wave number of the last line of the Bohr series in the hydrogen spectrum will be. Could you please solve this question and let me know the answer of this question? Tell me. Given the value of Rydberg constant, okay, you guys are supposed to tell me the wave number of the last line. This one and solve this one also. Ratio of longest wavelength corresponding to the Lyman and Bohr series in hydrogen spectrum is. This was asked in NEET 2013 and previous one was asked in NEET 2016. Come on, tell me the answer. Everybody. Yes. 0.25 into 10 raised power minus 7. That is correct. Okay. Ratio of the longest. Tell me about this one also. Guys, given the value of Rydberg constant is the wave number of the last line of the Bohr series is. See. Again, it's one and the same thing. Guys. Last line of the Bohr series. Last line of the Bohr series is this one. So for last line of the Bohr series, n initial is infinity, n final is 2. So if you put the values, 1 by lambda comes out to be R by 4. Okay. So I can simply say 1 by lambda for last line. For last line in Bohr series, 1 by lambda is equal to, we say, R by 4. And what is this 1 by lambda? Guys. This 1 by lambda is what we call the wave number. Always remember, this 1 by lambda is called the wave number. Only lambda is wavelength. Okay. And now I can say in this particular case, 1 by lambda, the wave number, we are supposed to find the value of 1 by lambda. So this is given as 10 raised power minus 7. 10 raised power minus 7 divided by 4. So 1 by lambda comes out to be 1 divided by 4 is how much? 0.25 into 10 raised power minus 7. Okay. Now, next one, this one. How are you supposed to solve this question? The ratio of the longest wavelength corresponding to the Lyman and Bohr series. Longest wavelength. Which one has got the longest wavelength? I guess the first line. First line has got the longest wavelength, minimum frequency, minimum energy. We say, guys. So, first line of Lyman series. Guys, it is saying that you have to find the wavelength of those lines which have got maximum wavelength, longest. That is the first line of Lyman series. So for first line, n initial is infinity and n final is 1. So you can say 1 divided by lambda 1 will come out to be Rydberg constant. 1 by n final square 1 minus 1 by n initial. Okay. So this will come out to be 1 by lambda 1 is equal to, we say, sir, R. Okay. 1 by lambda 1 will come out to be exactly R over here. Now guys, tell me, can I say here this lambda 1 will come out to be, that is 1 by R? Yes. Then if I talk about the first line of Bohr series. Guys, first line of Bohr series means Ni is equal to, oh, sorry. I made a mistake over here. This is the last line. Yeah. See guys. See. Yes. If we talk about first line in Lyman series. So we say n initial is equal to 2, n final is equal to 1. First line. Okay. So I can say 1 divided by lambda 1 will come out to be R. That is 1 by n final is 1 square minus 1 by n initial is, we say, sir, 2 square. That is 4. So 1 by lambda 1 will come out to be R. Now guys, 2 square is 4. 4 into 1 is 4. 4 minus 1 is 3. So that is 3 by, we say, 4. Okay. So lambda 1 will come out to be, that is 4 by 3. Okay. And this is exactly, or keep it 1 by lambda 1 only. Let's find out the value of first line of Bohr series. So when it comes to the first line of Bohr series, we say, sir, n initial is equal to 3, n final is equal to 2. You can exactly see over here. See guys, first line of Bohr series, n initial is equal to 3, from 3 to 2, and final is equal to 2. Now in this particular case, I can say here 1 divided by lambda 2 will come out to be 1 by r. Okay, so this will be 1 by n final square. 1 by 2 square is 4. Okay, minus 1 by n initial square. 3 square is 9. So 1 by lambda 2 comes out to be 9 minus 4, that is 5. So it will be 5 divided by 36. Okay. Okay. Now this is first and this is second. Check out what is coming out to be the value of lambda 1 divided by lambda 2. Okay, 5 by 27. Okay. Is it coming out to be 5 by 27? Okay. Yes. So lambda 1 divided by lambda 2 is 5 divided by 27. Okay. Now you just have to do one thing. Find the lambda over here. Okay. Take this 4 over here, 3r over here. So lambda 1 will be 4 by 3r. Lambda 2 will be 36 by 5r. Divide them, you will get 5 by 27. Great. Now we are done and dusted with the second chapter. We are starting the nuclei, third chapter. Now we are starting the nuclei, that is third chapter over here. Okay. Okay. And let me just tell you how much time it is going to take us. It will not take much time. In the next 1.5 hours, we'll mostly finish. Yeah, around 2 we are going to finish, mostly. No. See guys, let's talk about the nuclei. Let's talk about the nuclei. When it comes to an atom, guys, when it comes to an atom, let's suppose I'll make an atom over here. We know, sir, at the center of this atom, we have got nuclei. At the center of this atom, we have got nuclei. Okay. At the center of this atom, we have got this nuclei. And in this nuclei, it has got protons and neutrons. This is what we call the nucleus. Okay. And this as a whole is atom. Till now, we were discussing about the atom. Now, let's go inside an atom. Let's talk about this nucleus. Okay. Okay. So, we say nucleus is present at the center of an atom. Nucleus is exactly present at the center of an atom. Like here you have got nucleus. So this is the nucleus. And my dear friends, listen to me very carefully. When you talk about this nucleus, so if I just mention over here, nucleus, we say it has got protons plus we say, sir, neutrons in it. And we know electrons are revolving around the nucleus. But inside the nucleus, you have got protons and neutrons. Okay, the first thing over here is, we say inside the nucleus, what are the particles? Protons and neutrons. Now guys, see, we say the particles which are present inside the nucleus, are called, we say, nucleons. So from now onwards, these protons and neutrons will be calling them nucleons. Or we say hydrons. Or we say baryons. Okay. Hydrons or baryons. Okay. So we say these are not the fundamental particles. Fundamental particles means which are not made up of something else. But when it comes to these protons and neutrons, they are made up of quarks, up quarks, down quarks. Okay. So we say these are made up of quarks. Okay. Protons and neutrons I'm talking about. Okay. And now, my dear friends, we say electrons, positrons, quarks, neutrino, antineutrino. These are what we call the fundamental particles. We consider these as fundamental particles. Okay? But when it comes to the protons and neutrons, these are not the fundamental particles. So as of now, I told you, when it comes to an atom, at the center of the atom, you have a nucleus. Inside the nucleus, you have protons and neutrons. And these are what we call the nucleons. Okay? Now guys, let's talk about the representation of the nucleus. How do we exactly represent the nucleus over here? Okay. Representation of a nucleus. Now guys, see. We say, let's suppose we have got a nucleus over here. We say we have got a nucleus over here. Okay. And the name of the nucleus is, let's suppose, X. The name of the nucleus is, let's suppose, X. Okay. And how do we represent it? Guys, we say we represent it with some letter X, Y, Z, whatever it may be. Okay. And at top of this, I write A, and over here, I write Z. Sir, what does this signify actually? We say this A means mass number. A means mass number. And what is mass number? Mass number means number of protons plus number of neutrons. Okay? Number of protons plus number of neutrons. Cool. And sir, what is this Z over here? We say this Z is what we call number of protons. Number of protons. Okay. Z means number of protons. A means mass number. Number of protons plus number of neutrons. Or we say number of nucleons. And if somebody asks you, sir, how to find number of neutrons? Don't you think I can say number of neutrons will be simply, that is total A minus, we say Z. A is the total number. Z is the protons. A minus Z will be number of neutrons. Yes. Like if I give you the example over here. Now, let's suppose I'll make, this is the nucleus. Okay. And this nucleus has P, 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 P. We say N, 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 N. And in this particular case, name of the nucleus is X. Can I write over here, this is X? And I can say in this particular case, we say, sir, this is 8 over here and this is 4 over here. Why did I mention 8? 8 means how many number of nucleons? That is 4 protons, 4 neutrons. And how many number of protons? That is, we say here, in this particular case, A is equal to 8 and Z is equal to 4. And if somebody asks you how to find number of neutrons, what will you say? That is A minus Z. A minus Z. And that comes out to be 4. 8 minus 4 is 4. See, number of neutrons is 4. This is what we call the representation of the nucleus. Okay, next. Now, there are some fundamental particles that you should actually know. The first one is neutrino. Okay, what is a neutrino? It's not that peanut butter neutrino. It is a neutral particle. We say it is a neutral particle. Okay, means its net charge is 0. Neutral particle means its net charge is 0. And when it comes to the mass, we say mass of this neutrino is much less than mass of electron. And I say almost we say massless. Almost massless. Okay. So this is what we call the neutrino. Okay. Now, my dear friends, then you have the alpha particle. What is this alpha particle? We say this alpha particle is made up of 2 protons and 2 neutrons. So it is made up of 2 protons. We say 2 protons and we say 2 neutrons. When 2 protons and 2 neutrons combine, they form the alpha particle. Okay. And when it comes to the mass, guys, its mass is 4 times mass of proton, because we consider mass of proton and mass of neutron as same. That's why we say 4 times mass of proton. And when it comes to the charge, we say charge is simply, that is 2e, because neutrons are neutral. Neutrons does not have charge. So protons have charge. 1 proton has e, 2 protons have 2e. Then guys, you have beta particle over here. What does this beta particle actually mean? What does this beta particle actually mean? I would want you to focus over here. Beta particle means it is an electron beam. What is electron beam? It is that electron which is moving with a huge speed. An electron moving with huge speed. Okay? And we say when it comes to the charge, its charge is negative, same as the charge of electron, minus e. Then you have positron. We say it is an antiparticle. It is an antiparticle of electron. It is an antiparticle of electron. Positron means an antiparticle of electron. What is antiparticle of electron? If electron is of negative charge, this will have positive charge. So we say its charge is plus E. Okay. But, sir, what is the difference between positron and proton? Positron has mass equal to the mass of electron. But when it comes to the proton, proton has mass greater than mass of electron. So we say its mass same as mass of electron. Its mass is same as mass of electron. Okay. Now, okay, one question was asked in, by the way, NEET 2019. Alpha particle consists of 2 protons only, 2 protons, 2 neutrons only, 2 electrons, 2 protons, 2 neutrons, 2 electrons and proton. Option B. Now, let's talk about quarks. Let's talk about quarks. What are these quarks? We say these are the fundamental particles. Fundamental particles. When it comes to the protons and neutrons, guys, when it comes to the protons and neutrons, we say protons and neutrons. Neutrons are made up of quarks. And how many number of quarks are over there? We say there are 6 number of quarks, 6 types of quarks. See guys, first one is up quark, it's down quark. Top quark, bottom quark. Beauty quark, charm quark. Okay. Now guys, see, we say charge on these up quarks is plus 2 by 3e. What is E? E is the charge on the proton or charge on electron. We say E, 2 by 3e, 2 by 3e plus 2 by 3. And when it comes to the down quark has the charge of minus 1 by 3, minus 1 by 3, minus 1 by 3. Okay. Okay. Now, if we talk about over here, proton. Let's suppose I'll take the proton over here. Guys, see, this is the proton. I'm taking the proton. We say this proton is made up of UUD. That is up quark and down quark. It is not confusing at all. What I'm saying is that these quarks are the fundamental, like you have electrons. Similarly, you have another type of particle that is called the quark. Okay. And electron has got charge E. This quark has got charge 2 by 3e or 1 by 3e minus 1 by 3e. Okay. So we say total there are 6 types of quarks. We say with the help of these quarks only proton is made. A proton is made up of 3 quarks, up quark and down quark. Let's find the net charge here. When it comes to the net charge, you say simply, sir, up quark has how much charge? 2 by 3e. So we say 2 by 3, 2 by 3. We say 2 by 3e plus 2 by 3e. Then we say plus. Down quark, how much charge down quark has? That is minus 1 by 3e. So I'll write over here minus 1 by 3e. Now guys, see, 2 plus 2 is 4. 4 minus 1 is 3. 3 by 3. 3 by 3 will cancel. It will come out to be E. Correct. We say charge on the proton is E. See, if you do the calculation of the charge of these, it is coming out to be E. And if I say in this case, let's take neutron. Let's take neutron. We say when it comes to the neutron is made up of, we say DDU. Neutron is made up of DDU. Down quark and up quark. So let's find the net charge on neutron. Guys, we know net charge on neutron is 0. See, down quark has how much charge? Write the up quark first, 2 by 3e. Then down quark has minus 1 by 3e. Another down quark has minus 1 by 3e. Guys, see, minus how much it comes out to be? 2 by 3e minus, it will be minus 2 by 3e. Plus 2 by 3 minus 2 by 3, it comes out to be equal to 0. That's what I was saying. So down quark, so we say neutron has got a charge of 0, up quark, and this proton has got a charge of positive. Okay. Now guys, let's move on to this one. See guys, let's take a look over here. In this case, see, mass of a proton, guys, remember this, mass of a proton. We say mass of proton is 1.67 into 10 raised power minus 27 kg. Or we say it is 1.007 AMU. Okay, you can measure the mass in atomic mass unit also, AMU. Either this is in the kgs, this is 1 unit, this is another unit. Similarly, mass of neutron, remember this guys. Mass of neutron, we say it is also 1.67 in 10 raised power minus 27 kgs. That's what I was saying. They have almost equal mass. Okay, it is 1.008 AMU. Then we say mass of electron. Mass of electron is almost 9.1 into 10 raised power minus 31 kgs. And it is 0.0054 AMU. Okay. 0.0054 AMU. And if somebody asks you what is the value of this AMU, value of AMU is 1.66 into 10 raised power minus 27, because this is 1 only, na? Okay. And how do we define this AMU? We say it is equal to 1 AMU is also equal to 1 by 12th of mass of carbon atom. If you take a carbon atom, so 12th of that mass, 12th of mass of 1 by 12th of mass of the carbon atom will be equal to 1 AMU. Okay, so from now onwards you'll be remembering 1 AMU is equal to this, or 1 AMU is equal to 1 by whatever is the mass of carbon atom, divide it with the 12, whatever the value comes out to be, that is equal to 1 AMU. Guys, is this clear? Is this slide clear, which is on the board right now? Is this slide clear, which is on the board? Great, great. Now, let's talk about this one. Rest mass energy. Guys, tell me one thing. You say, I have an object over here. If we take it to the height h, we say here it is gained potential energy mgh. So due to the height, it has potential energy. Let's suppose if we have an object, it's moving with a velocity v, its mass is m. We say it has kinetic energy is equal to 1 by 2 mv square. It has kinetic energy 1 by 2 mv square. So we say due to the motion of an object, it has kinetic energy. Due to the height of an object, it has potential energy. Okay. Similarly, if I say I have got the mass over here m. Due to the mass of an object, it has energy associated with it. So we say due to the mass of an object, it has energy associated with it, called rest mass energy. Okay. Like, my dear friends, due to the motion of an object, it has energy with it, energy associated with it, that is kinetic energy. Similarly, if you have the mass, due to its mass, it has energy. Sir, it means this marker has mass, so it will have also energy with it? Yes. And that energy is called rest mass energy. And when it comes to the value of this rest mass energy, we say this energy is equal to E is equal to mc square, where m is the mass of an object, c is the speed of light. Now guys see, if I say, if I have an object which is having the mass of 10 kgs, if I have an object which is having the mass of 10 kgs, how much is the energy in this 10 kg? You say, sir, this energy will be, mass is 10, okay, c is 3 into 10 raised power 8 and its whole square. So energy will come out to be, this is 10 into 3 square is 9 into 10 raised power 8 whole square, that is 10 raised power 16. So E will come out to be 9 into 10 is 90. Okay, so you can say 9 into 10 raised power 17 joules. So this much of energy is stored in 10 kg mass. So this is the energy stored in 10 kg mass. And my dear NEET aspirants, let me just tell you, over here, when it comes to this energy, this energy is so huge. This energy is so huge, that it can burn this entire world. It can take this entire world upside down. Energy in just 10 kg can turn this entire world, entire galaxy upside down. Imagine. Imagine the mass, imagine the amount of energy stored in you. You have got 50 kg mass. Imagine the energy stored in you, how many galaxies you can burn. How many galaxies you can take upside down. Imagine how beautiful it is. Imagine how stronger you are. Okay. Okay. Now, guys, yes, and you guys say every single time I have zero energy, no motivation at all. Now, guys, see, listen to me very carefully. You know that incident happened back in time, like around 1950s, that the bomb was Hiroshima and Nagasaki incident, okay? Do you guys remember that? Okay, they threw the bomb on them. Do you remember that? You might have heard this about, heard about that in different stories, the nuclear bomb. You know how much mass was converted into the energy when they destroyed the complete two cities, Hiroshima and Nagasaki? It was around 0.2 grams. 0.2 grams of mass was converted to the energy, and this much mass burned the complete whole of the two cities. Just 0.2 gram. 0.2 gram of uranium. Okay. Okay. So this is what we call the rest mass energy. Such a beautiful concept. Can you tell me, this was the question asked in NEET 2020 on rest mass energy. How much is the energy stored in 0.5 gram of the substance? How much is the energy stored in the 0.5 gram of the substance? Tell me. Okay. So we can say in this particular case, E is equal to mc square. So energy you can write over here. What is the mass given? Mass is 0.5 grams into 3 into 10 raised power 8 whole square. So E will come out to be, if you convert this into the kgs, you can say 5 into 10 raised power minus 4. 0.5 grams to the kgs, 5 into 10 raised power minus 4. Okay. So I can say this will be into 3 square is 9 into 10 raised power 16. Okay. So this will be 45. E is equal to 45 into 10 raised power 12. This will be 4.5 into 10 raised power 13 joules. Okay. Option B. Great, great. This was the question in NEET 2000. The energy equivalent of one atomic mass unit is. See, guys, we say as. In this question, it is asking us to find energy. To find energy in 1 AMU. How much amount of energy is stored in 1 AMU? That's what we are supposed to find out. We say when it comes to the energy, energy is equal to mc square, is equal to mc square. And I can write over here, this energy will be equals to, what is the mass that they are asking? That is 1 AMU. Okay. Okay. Into we say, sir, C square. Now I can say over here, E is equal to, what is the value of 1 AMU? 1 AMU. We say 1.67 into 10 raised power minus 27 kgs into, okay, because I told you over here, the value of 1 AMU, the value of 1 AMU is, because I told you over here, when it comes to the value of 1 AMU, see guys, 1.67 into 10 raised power minus 27 kgs. Okay. So you can write into C square. So this will be, 3 square is 9 into 10 raised power. 9 into 10 raised power, we say 16. So if you solve this, it will come out to be 931.5 MeV. I would want you guys to remember it directly. Okay, guys, on solving this, if you convert it, and then this will come out to be 931.5 mega electron volts. Mega electron volts. I'm converting this in the mega electron volts. Okay, don't go in the much depth. Whatever I say, just remember. Now see, call this as equation first and call this as equation second. You see, sir, on solving this, we are getting this. On solving this, we are getting this. So can I say equation 1 is equal to equation 3? From, I'll write first and I'll write second. We say 1 AMU into, we say C square is equal to, we say 931.5, we say MeV. 931.5, we say MeV. Okay. Now guys, in this particular case, I would want you guys to focus, 1 AMU is also equal to 931.5, we say MeV divided by C square. Keep this also in the box. It will help us in the upcoming time. So this is the value of 1 AMU in mega electron volts. Is this point clear? Is this point clear? Okay, great. Now guys, let's take a look exactly over here. Size of nucleus or nuclear size. Let's suppose I say I have got a nucleus over here. Let's suppose I say I have got a nucleus over here. Okay. Okay. Yes. Now guys, if I say in this particular case, I have got the number of nucleons. These are the nucleons, guys. These are the nucleons. These are the protons over here. These are the protons. Protons and neutrons. Protons and neutrons. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Okay. And I have got over here these protons and these are the nucleons. Okay. And we say we have got these. Okay. These are also the nucleons. Okay. I am asking you the simple question. I say put these nucleons in the nucleus. Put these nucleons in the nucleus. You will say, sir, for these nucleons, I will require a bigger nucleus. For these nucleons, I will require a smaller nucleus because they can fit in easily in this one. These can fit in this one. So can I say, guys, we say mass number over here is large. I can say In this particular case, mass number is 16. What is mass number over here? 3, 6, 9, 10. Mass number in this case is 10. So it requires smaller nucleus. It requires bigger nucleus. So I can say in this particular case, guys, I can say in this particular case, we say simply, we say size of nucleus simply says it tells, see, simply, it tells us simply about how bigger the nucleus is. We say size of nucleus simply says, if I say size of nucleus is directly proportional to mass number. If there are large number of nucleons, it will have bigger nucleus. Okay? If there are less number of nucleons, it will have less nucleus, smaller nucleus. What is size of nucleus? Size of nucleus means volume of nucleus. Okay? Is proportional to, we say, mass number. So, volume of nucleus is proportional to mass number. And how do we write volume of nucleus? 4 by 3 pi r cube is proportional to mass number, means A. More is the mass number, more is the volume of the nucleus. Yes. So I can say 4 by 3 pi is constant. So r cube is proportional to A. R is proportional to A raised power 1 by 3. And R, replacing this with a constant. So we say R is equal to R naught A raised power 1 by 3. We say where R naught is equal to 1.2 Fermi meter. 1 Fermi meter is equal to 10 raised power minus 15 meters. Always remember this. 1 Fermi meter is equal to 10 raised power minus 15 meters. So we say here, this is what we call the radius of nucleus. Okay. Now guys, if somebody asks you to plot the graph between, if somebody asks you to plot the graph between radius and mass number, okay, if somebody asks you to plot the graph between radius and mass number, okay, so we say this is over here in this particular case radius, and this is over here mass number, and this is a radius, okay, and we say in this particular case this is A raised power 1 by 3. Guys, understand this very carefully. When you make the graph between R versus A, and when you make the graph between R versus A raised power 1 by 3, these are the two different graphs over here. Okay? These are the two different graphs over here. We say when you make the graph between a radius and A, in that particular case, what is going to be the graph? Guys, what is the relation between R versus A? You say relation between R versus A is R is directly proportional to A raised power 1 by 3. So the graph will be this, because R is proportional to A raised power 1 by 3. Now, when you make the graph between radius versus mass number raised power 1, what is the power of this? You are making the graph between this and this. What is the power of this one? What is the power of this one? So it will be the straight line. Is this clear? Is this clear? Okay. Now guys, let's move on to nuclear density. When we talk about the nuclear density, this is what we call the density of nucleus. Okay, this is called the density of nucleus. Guys, when it comes to the density of nucleus, how do we find density? Mass by volume. Mass of nucleus divided by volume of nucleus. Okay. Now, my dear friends, I'm asking you the simple question. Let's suppose I have got a nucleus over here. I have got a nucleus over here. Okay. And inside this nucleus, you have got protons, neutrons, protons, neutrons. So these are the nucleons inside. And when it comes to the mass number is, we say, sir, A. Now, mass number means how many number of nucleons are over here. If I say it has got 3 nucleons, what will be the mass of nucleus? Guys, you say mass of nucleus. What will you say? You say, sir, 3 times m, 3m. Sir, 4 nucleons over there, 4m, 5 nucleons, 5m. We say, if I say A nucleons are over here, you say AM, AMP. Because MP is the mass of one nucleus. If there are A nucleons, so AMP. Okay. And when it comes to the volume of nucleus, we say volume of nucleus is proportional to mass number. As we have discussed this, if more is the mass number, more number of nucleons are over here, we say volume will be more. So I can say V is proportional to A. So V is equal to V naught into A. V is equal to V naught into A. Replacing this with a proportionality, V naught into A. Okay. Now guys, put in the equation 1. So I can say density of nucleus will be mass of nucleus. What is mass of nucleus? AMP. Okay. What is density of nucleus? That is V naught into A. Now here, this and this will cancel. So density will come out to be MP divided by V naught. And this is 10 raised power 17 kg per meter cube. Okay. Its value is 10 raised power 17 kg per meter cube and is constant for all nuclei. Okay. So this is what we call the density. So if somebody asks you to plot the graph between density versus mass number, okay, density versus mass number, you simply say it is a straight line because density is constant. Density is constant. It is same for all the nuclei. Yes. Okay. Okay. The volume occupied by an atom is greater than the volume of the nucleus by a factor of. Guys, it is saying when it comes to the volume of an atom divided by, okay, when it comes to the volume of an atom divided by volume of nucleus. How do you find volume of atom? 4 by 3 pi radius of atom cube, okay, divided by 4 by 3 pi radius of nucleus cube. 4 by 3 pi r cube. This is spherical in shape. This is spherical in shape. So 4 by 3 pi, 4 by 3 pi. So what is the value of radius of atom? 10 raised power minus 10, okay, meters divided by, what is this? We say 10 raised power minus 15. Okay. It's cube. Now tell me, in this particular case, we can write it something like this, guys. This is 10 raised power minus 10, 10 raised power minus 15. So it will go 10 raised power 5, we say whole cube. So it will be 10 raised power 15. Okay. If you are talking about the volume more specifically. Okay. So this is what we call. Next, guys. Two nuclei have their mass number in the ratio of 1:3. Their nuclear densities will be. They are saying the mass number of one, let's suppose one nuclei, A1 by A2 is given as 1:3. Which one have more density, which one have less density? Guys, I can say density is constant for all nuclei. So, density of A divided by density of B will be 1:1. It will remain the same. Next. Next. A nuclear ruptures into two nuclear parts. You have got a nucleus ruptures into two nuclear parts. You have got a nucleus over here. Okay. Now this nucleus breaks into two equal parts. We say this one and this one. Like bomb. It's the explosion. It's the explosion. Okay. So we say its mass is m1 and its mass is m2. And this has got the velocity v1. This has got the velocity v2. And it says over here, ratio of velocity v1 divided by v2 is given as 2:1. It says that velocity of this divided by velocity of this. A nucleus ruptures into two equal parts which have their velocity equal to the ratio of 2:1. Ratio of velocity v1 by v2 is given as 2:1. Okay. You are supposed to find the ratio of their size. Okay. You are supposed to find r1 divided by r2. Ratio of their radius. Guys, see, whenever the explosion happens something like this, always remember, we say momentum in this case remains constant. Okay. We say here, whenever the explosion happens, always remember momentum is constant. We say here, momentum P is constant. Guys, initially if we talk about initial momentum is 0 because this nucleus was at rest. Finally, momentum of these two should be also how much? 0. Okay, net. What is the momentum of this? We say, sir, that is m1 into v1. It should be exactly equal to, we say, sir, m2 v2. If momentum of these two are equal and in opposite direction, so finally also net will be how much? 0. Like initial. Momentum is conserved constant means initial momentum before the explosion should be equal to final momentum after the explosion. After explosion, we say this has momentum in this direction. This has momentum in this direction. Net will be 0. Now, can I say over here, in this particular case, I can say m1 divided by m2 will come out to be, that is v2 by v1. Now, guys, v1 by v2 is 2 by 1. v2 by v1 will be how much? That is 1 by 2. Okay. Now tell me one thing. Can I just write it? Guys, m1 by m2 came out to be 1 by 2. Can we just write it as mass is, we say density is mass by volume. Mass is density into volume. So I can say this is density volume of 1 divided by density volume of 2. This v2, v1 is velocity is equal to 1 by 2. This and this will cancel. This is equal to this is equal to this. Because instead of this, I am writing density into volume, density is equal to 1 by 2. Now, volume of 1 by volume of second. How do we write the volume of first? 4 by 3 pi r1 cube divided by 4 by 3 pi r2 cube will be equals to 1 by 2. 4 by 3 pi, 4 by 3 pi. r1 by r2, I can write r1 divided by r2 whole cube is equal to 1 by 2. Take this 3 over here. r1 divided by r2 will be 1 by 2, 1 upon 2 raised power 1 by 3. Because if this cube goes over here, it will be 1 upon 1 by 3. 1 upon 2 raised power 1 by 3. Is this clear? Is this clear? Next. Okay, this was asked in 2017. Radius of 2He4 nucleus is 3 fermi-meter. You have got over here radius of 2He4. 2He4 means helium nucleus. Radius of helium nucleus is given as how much? 3 fermi-meter. Okay. And when it comes to this, guys, when it comes to the helium, what is the mass number of helium? Guys, it is 2He4. What is the mass number of helium? Mass number of helium is 4. Because this means mass number, this means atomic number. So you have got this helium nucleus. It says that its radius is given as 3 fermi-meter. Okay. Then, my dear friends, you guys are supposed to find then the radius of 16s32 will be. So you guys are supposed to find radius of this sulfur. Okay. Now, guys, we say when it comes to the 16s32, this nucleus, could you please tell me what will be the mass number? Mass number in this case is 32. So you have helium, you have sulfur. Mass number 32, mass number 4. Now tell me one thing. As we know, radius is proportional to mass number raised power 1 by 3. We recently saw this. Radius is proportional to mass number raised power 1 by 3. So can I say radius of what? Helium. Okay, or directly you write radius of sulfur divided by radius of this helium is equal to mass number of sulfur raised power 32 divided by mass number of this, that is mass number of sulfur is 32 divided by mass number of helium is 4 whole raised power 1 by 3. 4 ones are 4 8s are. Cube root of 8 is what? 2. 2 into 2 into 2 is 8. Okay. So RS divided by RHE is equal to 2. Now this, what is the value of RHE? That is 3. So RS will be 3 into 2 is 6 fermi-meter. Okay. Now tell me the answer of this question. Tell me the answer of this question. Tell me the answer of this question, guys. The nuclear radius of Al27 is, we have got over here, radius of Al is given as 3.6 fermi-meter. Okay. And when it comes to the mass number, A is equal to, that is 27. And then it says that, the approximate nuclear radius of Cu64. So when it comes to the radius of Cu, copper, you guys are supposed to find out. And mass number of this Cu is given as 64. Now tell me, guys, we recently saw radius of Cu divided by radius of Al is equal to, radius is proportional to what? Mass number raised power 1 by 3 is equal to, tell me, we say this is mass number of Cu is 64 divided by mass number of A is 27. Okay. And this is over here cube root in this particular case. Okay. Now tell me in this particular case, guys. So just this is we say, sir, it will come out to be 6.8, I guess. Okay. So just put the values over here. RCU will come out to be 6.8 per meter approximately. Okay, 4.8, 4.8. Yes, 4.8 per meter. Okay. Yeah. Next, binding energy mass defect. Two, three, four topics are left. Guys, let's take a break of 10 minutes. What do you think? I need the break, guys. I'm not saying it for you. I need the break actually. Okay, let's take the break of like 5 minutes, like 10 minutes. Okay. So what's the time right now? It'll just take us more 45 minutes more and we are done with this. 28 break till we say 1:42 a.m. Yeah, yeah, yeah. Check, check. Check, check, check. Okay, we are live. Back. Now, guys, let's move on to binding energy now. See, I'll make you understand this concept of binding energy. See. Let's suppose I have got a balloon over here. I have got a balloon over here. Understand this. Okay, this is a balloon. And inside this balloon, I have got this mass. I have got this ball. I have got this ball. I have got this ball. And mass of each ball is, we say, sir, 5 kg. This is 5 kg. This is 5 kg. This is 5 kg. And this is 5 kg. Okay. And when it comes to the collective mass of this balloon, how much is that? 5 kg plus 5, and that is 20 kgs. Simple thing I am saying over here. I have got a balloon. Inside the balloon, I have got 4 balls over here, 4 masses over here. And I'm saying, what is the net mass of this balloon? 20 kgs. Now, what I'm saying in this case is, I want you to break this balloon. Okay, I want you to break this balloon and take out all of these masses. Or I say, break the balloon and take out all of these masses. So don't you think that if we break this balloon, it requires some energy? Yes. So we have to, okay, use some energy. Consider it as a thick balloon. Okay, we have to use some energy in taking out these masses. While we took these masses out of this balloon and placed over here, and we calculated their mass, net mass came out to be, guys, we saw mass of this was increased, mass of this was increased, mass of this was increased, mass of this was increased. We saw it came out to be 22 kgs. It came out to be 22 kgs. When they were inside the balloon, what was the mass? 20. When we took them out of the balloon, how much is the mass? 22. Don't you think that here mass defect has occurred? What does defect in mass mean? 22 kgs, 20 kgs. So it was supposed, it should have been 20 only. But when it comes to the mass defect, that is delta M, that is how much? We said 22 minus 20, that came out to be 2 kgs. Okay. We say mass defect has occurred over here, and that is how much? Okay, that is 2 kgs. Now, my dear friends, I would want you to understand that is, let's suppose I'll take the example over here. I have got the nucleus. This is the nucleus. Okay. And in this particular case, mass number of this nucleus is A is the mass number. A is the mass number. Mass number means number of nucleons. And we say Z is the atomic number. Z is the atomic number. Number of protons. And when it comes to the mass, of this nucleus, collective mass, it is M, capital M. Now I want you guys to break this nucleus. Okay, I want you guys to break this nucleus. Break. Okay. While you break this nucleus and take out all the nucleons present inside it, we say you will have to use the energy. We'll have to use the energy in breaking the nucleus. And then, my dear friends, you'll take out all of these masses individually. We say, while you are taking Z protons over here, what will be the mass of Z protons? So that will be ZMP. Okay. individual mass. Then we say plus. How many neutrons are over there? We say A minus Z. So we say A minus Z. And this is MN, mass of neutrons. So we say collective mass of this is M. If you break it, you are taking these protons out, you are taking neutrons out individually. What is the mass of the protons? Sir, that is ZMP. How many protons are there? Z protons. How many number of neutrons are there? A minus Z. So how much is the mass? Mn. A minus Z into Mn. And we saw here also we saw this individual mass, okay? This individual mass while you taking out them. So ZMP plus we say A minus Z, we say Mn is greater than the collective mass. Like over here, final mass came out to be greater than initial mass. Same happened in case of the nucleus. Can I say here also mass defect has occurred. Here also mass defect has occurred in this particular case. Okay. Here also mass defect has occurred. So my dear friends, why this mass defect is occurring over here? This mass defect is occurring because you are using the energy in breaking the nucleus. And that energy is getting stored in the form of mass in these nucleons. So the energy which you are using in breaking the nucleus, so that energy is not wasted, but that gets stored in the form of mass in these nucleons. So we say this is because the energy which is used to break the nucleus, because the energy which is used to break the nucleus is stored in the form of mass of nucleons. Okay, and this energy is called binding energy. So what is binding energy from now onwards? Binding energy is that energy which is used to break the nucleus so that you can take out all these nucleons. And we said this energy gets stored in the form of mass of these nucleons. So can I say, guys, so mass defect occurs due to binding energy. Mass defect occurs due to binding energy. Yes. And how much is this mass defect? Guys, if somebody asks you how much is this mass defect, what will you say? When it comes to the mass defect, and this mass defect is, we say delta M is equal to, guys, what is final mass? That is ZMP plus A minus ZMN minus, we say this is final mass minus initial mass, that is the collective mass of the nucleus. Okay. Now guys, if you want to find this, see, if I say you have got 2 kg mass over here, see, in this case I'll show you. If I say how much is the mass defect in this case, 2 kg. Now if somebody asks you how much energy has been used to store this much of mass, you say, sir, that energy is equal to mc square. How much energy is in this 2 kg mass will be the energy that has been used. So if we find the binding energy here also, and guys, and this binding energy will be directly say binding energy is simply that is mass defect into c square, delta m into c square. So I can write this binding energy simply. What is the value of delta m? That is ZMP plus we say A minus Z, we say Mn minus this m multiplied by we say c square. So this is the value of binding energy that you can say over here. And now. So we say divide this over here. You can write in this particular case binding energy divided by c square is equal to we say this Z MP plus A minus Z, we say Mn minus this m. Okay. Now I would want you guys to take this m exactly over here. Okay. Take this m exactly over here. So we can write over here, this will be ZMP, okay, ZMP, or you can write it something like this also. If you want to find this m, take it over there, m will be over here. That is ZMP plus, we say A minus Z into Mn minus binding energy divided by c square. So put this in a box also, because this was once asked. This was once asked. This is what we call the collective mass of the nucleus. This is called the collective mass of the nucleus. Okay? Okay. I hope this is crystalline clear. So binding energy is that energy which is used to break the nucleus, and that energy gets stored in the form of mass. And if somebody asks you how much is that binding energy, delta m into c square. Delta m is the mass defect. Okay, next. Okay, one more thing I just want to tell you over here. That is, remember this concept, guys, that is binding energy. Binding energy per nucleon is proportional to binding energy per nucleon is proportional to, we say, stability. What does that mean? Binding energy per nucleon is proportional to stability. Binding energy per nucleon means how much amount of energy is used in taking out one nucleon from the nucleus. Guys, this is the nucleus. I'm saying binding energy is, let's suppose, 10 electron volts. What does that mean? That means you require 10 electron volts. It requires 10 electron volts to take out all the nucleons from this nucleus. Okay. If I say binding energy per nucleon is 10 electron volts, it means it requires 10 electron volts to take out one single nucleon. Binding energy per nucleon. How much amount of energy is required to pull out one single nucleon is binding energy per nucleon. Okay. And we say it is proportional to stability. Okay. It is proportional to stability, binding energy per nucleon. So we say binding energy per nucleon is proportional to stability. Okay. So don't say, because this is a confusion that maximum number of students have. Binding energy is proportional to stability. They say the more amount of energy it requires to break the nucleus means nucleus is stable, very much stable. That's why it requires more energy to break. No, it is binding energy per nucleon. Now, guys, let's suppose we have two nuclei over here, X and Y. Okay. You have got X nuclei over here, that is 4x6. Okay. And it says that 4x6 and 6x12 has binding energy of 24 and 36. This has got binding energy of 24 electron volts. And when it comes to the Y nucleus, that is 6Y12, it has got the binding energy of 36 electron volts. What does it mean? It means that if you want to break this nucleus, take out all the nucleons, it requires how much energy? 24. What does this mean? If you want to break this nucleus and take out all the nucleons, how much energy it requires? 36 electron volts. Okay. Let's find binding energy per nucleon. Guys, we say binding energy per nucleon divided by mass number. Binding energy per nucleon. Binding energy divided by A. We say, in this particular case, this will be 24. What is mass number over here? That is 6. 6 ones are, 6 fours are. So this comes out to be 4 electron volts. So in this case, if you want to take out one nucleon from this nucleus, how much energy is required? 4. Let's find binding energy per nucleon over here. What is binding energy over here? 36 per nucleon, that is 12. 12 ones are, 12 threes are, so 3 electron volt. So if you want to take out one nucleon from this, it requires 3 electron volts. As we know, binding energy per nucleon is proportional to stability. We say as binding energy per nucleon is proportional to stability. Okay, so can I say from this has got more binding energy per nucleon, this has got less. So I can say X is more stable than Y. More stable than Y. X is more stable than Y. Similarly, you can solve this question. It says binding energy of 2He4 is 27.3. Okay, so 2He4, it has got binding energy as 27.3. And 3Li7 is 39. 3Li7 is, it has got binding energy of 39.3. Tell me guys in the chats, which is more stable? Which is more stable in this case? Is it 2He4 or Li? Helium or lithium? Which is more stable? Which one is more stable? Here, which one is more stable? What will you say in this particular case? Binding energy per nucleon, that will be 27.3 divided by 4. And what about the binding energy per nucleon over here? That will be 39.3 divided by 7. Okay. So this will come out to be approximately 6.8, something like that. Something like, please do it, check it, okay? And this will be, okay? Okay. And this is 39 divided by 7. So clearly I can say in this particular case, He is more stable than, we can say, Li. Okay. Simple, simple, simple. It depends upon the binding energy per nucleon. Now guys, there is an important concept that we need to discuss over here. What is that? That is, see, that is, let me tell you over here. See guys, I'll make the graph between binding energy per nucleon, okay, binding energy per nucleon. We know either you write binding energy per nucleon or you write stability, okay. I'll make the graph between stability versus mass number. Stability versus mass number, or binding energy per nucleon versus mass number. Now guys, understand very carefully. We say we have got the different nuclei out there. Let's suppose I'm taking this nuclei, I'm taking this. In this particular case, when we talk about, let's suppose this nuclei, this nuclei, this nuclei, this nuclei, we say this has got mass number, let's suppose 10, this has got mass number, we say 15, this has got 20, 30, okay? And we took all of these nuclei and we plotted the graph between stability of these nuclei and mass number. See, graph came out to be something like this. First, I'll make the graph. The graph came out to be something like this. Graph came out to be approximately something like this. Graph came out to be approximately something like this. Okay. Now, guys, in this case, we say, as you keep on increasing the mass number, guys, what is the mass number? Oh, 0. What is the mass number at this particular point? 10. Sir, this is that nucleus which has got 10 mass number. What does that mean? This is that nucleus which has got 10 nucleons. What is mass number over here? 20. This is that nucleus which has got 20, 30, 40, 50. Okay. My dear friends, we saw that as you keep on increasing the mass number, you see curve is going up, means stability is also increasing. So means as number of nucleons in a nucleus are increasing, we say stability is also increasing. If I ask you, what if I tell you is 30 more stable or 20? If a nucleus has 30 nucleons, is this stable or 20 is stable? Tell me which has got more stability over here. Tell me which has got more stability over here. We say as you keep on increasing mass number, stability is increasing. So I can say, guys, yes, exactly. I can say as we keep increasing the mass number, stability is increasing. Cool. And my dear friends, you can see exactly over here. You can see exactly over here. Okay. We say at A is equal to 30. We say this is A is equal to 30 mass number. From A is equal to 30 to almost A is equal to 170. A is equal to 170. Means this is that nucleus which has got mass number of 30. This is that nucleus which has got mass number of 170. Don't you think that all of these nuclei, let's suppose 100 will come over here, 120 nucleus will lie in this. All of these nuclei has got large stability. They are highly stable. Yes. And if you keep on increasing beyond 170, again stability decreases. So I say, those nuclei, guys, I'll just write over here. We say those nuclei, those which has mass number A is less than 30 are called lighter nuclei, and are unstable. Why? Because they have got less binding energy per nucleon. I'll make it somewhere around over here. Okay, they have got less binding energy per nucleon. Okay. So we say this nucleus, it can be this nucleus. Okay. So these nuclei are lighter nuclei and they are unstable. Okay. And my dear friends, one more statement I'll just write over here. Those nuclei also, see, and are unstable. And those nuclei which lie, I'll just write those nuclei those nuclei which has mass number A is greater than 170 are called heavy nuclei and are unstable and are also unstable okay. And I'll just mention over here those nuclei which lie in between A is equal to 30 to A is equal to 170 are highly stable. Okay, so those nuclei which lie in this category so are highly stable. Okay, yes. Now guys, in this particular case, we say these nuclei which are less stable, everything in this universe wants to become stable. So they will basically fuse together, they will merge together, okay? They will fuse together, merge together, okay? And they form a bigger nuclei. And this process is called fusion. Like if I say there is a nuclei, guys, if I say there is a nuclei, this has 15 mass number, this has 15 mass number. They are unstable. So we say in this particular case, they will merge together, fuse together to form a bigger nuclei. How many now? 15 plus 15 is 30. Now they will come under this stable. They will become now stable. Okay. So I can say in this particular case, two lighter nuclei fuse together in order to become stable. Two nuclei fuse together in order to become stable and forms a bigger nuclei. The process is called fusion. And energy is released in the process. Why, sir? Because whenever something goes towards the stability, always remember energy is released. Okay. And one more thing, there is a bigger nuclei over here. Okay. It wants to become stable. So what will it do? It will be splitted into two smaller nuclei. This process is called fission. So if there is a bigger nuclei, it wants to become stable, it will be splitted into two smaller nuclei. This process is called fission. Okay. So we say when a bigger nuclei breaks into two smaller nuclei to become stable, the process is called fission. Like this is, its mass number is 200. If it is breaks into 100 and 100, that will lie between 130. That will lie between 30 to 170. So it will become stable. So this process is called fission, and energy is released in this process also. process also. Why? Because whenever something goes towards stability, energy is released. Guys, is this crystalline clear to each and every single student? Okay. Is this crystalline clear to each and every single student? Please tell me in the chats. Everyone means everyone. Great. Great. Let's talk about nuclear force. Let's talk about nuclear force. What is a nuclear force? Guys, see, let's suppose we take a nucleus. Inside this nucleus, you have large number of protons and neutrons. These are the nucleons basically. And if I say over here, inside the nucleus, okay, nucleus is a very small place, okay, extremely small. We say inside the nucleus, protons are placed very close to each other, very close to each other. And we say distance between them is extremely small. So they apply large electrostatic force. On each other. So they apply large electrostatic force on each other. So let's suppose inside this nucleus, this proton and this proton, they are applying the large electrostatic force on each other. Why? Because they have got the charge. Whenever you have two charges separated by some distance, they apply the electrostatic force. And I can say in this particular case, this electrostatic force will be K Q1 Q2 divided by R square. Okay, this electrostatic force will be K Q1 Q2 by R square. Yes. Now, my dear friends, we say here R is very small. Very small. If R is very small, we say F is very large. F is very large. Okay. Now, my dear friends, don't you think that this force, which is very large, is in the outward direction? This force tries to break the walls of the nucleus. This force is very large and it will try to break the walls of the nucleus. Okay. And makes the nucleus as unstable system. But we know when it comes to the nucleus, it is highly stable. Okay. So it will try to break the walls of the nucleus. Okay. Now, my dear friends, we say in case of a nucleus, if the proton are at very small distance, they apply the force on each other, which is repulsive force. Okay. And this is in the outward direction. It will try to break the walls of the nucleus. But this nucleus is a stable system. We say what happens actually is that due to the nucleus, we say another force will act over here. I'll just write as another force will act between the nucleons, called nuclear force, which will overcome the electrostatic force. which will overcome the electrostatic force. Another force will act over here between the nucleons, which will overcome the electrostatic force. This nuclear force is attractive in nature. Okay. So if let's suppose you have got proton and proton, you are saying, sir, proton and proton will repel each other in the outward direction. Proton and proton will repel each other in the outward direction. With what? With electrostatic force. Okay, F electrostatic. But, and due to this electrostatic force, it will make it unstable. No, we say another force will act over here. That is F nuclear force. So due to this nuclear force, these protons, this inward force will overcome this outward force. So the system will remain stable. And when it comes to guys, this nuclear force, we say it acts between all the nucleons, be it proton, neutron, proton, proton, neutron, neutron. But when it comes to the electrostatic force, that acts only between the charged particles, protons and protons. So we say this nuclear force between this will be equal to force between two nucleons is equal to force between two protons is equal to force between neutron and proton. This will be equal. Nuclear force will be equal. Okay. Okay. And we say this nuclear force, okay, is 10 raised power 39 times greater than gravitational force. It is extremely huge. Okay, it is 10 raised power 39 times than the gravitational force. Keep that thing in your mind. And when it comes to this nuclear force, we say this nuclear force is 100 times bigger than electrostatic force. Okay, it acts between all the nucleons. We say it acts between all the nucleons. It acts between all the nucleons. Okay. Okay. Now, guys, let's make the graph between potential energy and distance in nucleons. See, guys, listen to me very carefully. If I plot the graph between potential energy, okay, and distance between the nucleons, U versus R. As remember, see. Let's suppose you have got over here the nucleons, okay? You have got the nucleons over here. I'm saying in this particular case, there exists the potential difference between the nucleons. Sorry, potential energy between the nucleons. Like you have the two charges, Q1, Q2. Sir, between these two charges, they have the potential energy. Similarly, if you have mass M1, M2, between these two charges, they have potential energy. Similarly, we say you have two nucleons, proton, 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 neutron, neutron, neutron. So there also exists the potential energy between the two nucleons. Like you say, U is equal to K Q1 Q2 by R square. This is the electrostatic potential energy. Here we say U is inversely proportional to R. U is inversely proportional to R. But in this particular case, we say between the nucleons, potential energy will exist. There will be potential energy between the nucleons. And if we make the graph between potential energy of the nucleons versus distance, it would be something like this. It would be something like this. It would be something like this. Okay? And the graph between U versus R. What is R? R is the distance in the nucleons. Potential energy and distance between the nucleons is given exactly like this. Okay? Like you say we have Q1, Q2, sir. Between them, a distance is R. Here also distances are. So the graph is this. Now, my dear friends, listen to me very carefully. If I say over here, this point is A. This point over here is B. Okay. And let's suppose this point is C. One thing I would want you to remember. We say, as we know, the relation between force and potential energy. This I have told you in the electrostatics. We say force is equal to minus du divided by dr. So if you know the potential energy, you can find force. What? By differentiating potential energy. I have told you many times, du by dr is F. Okay. So if you want to find force, you can differentiate this potential energy. Okay. And also one more thing I just want to say over here. Also, what is that? That is, when it comes to the slope of this graph, slope of this graph. Guys, let's suppose you have got y versus x graph. This is y versus x graph. Okay. I say, what is the slope of y versus x graph? You say dy by dx. Whatever is on y-axis divided by whatever is on x-axis. If I say, you say v versus t graph, what is the slope over here? dv by dt. And similarly, if I say, in case of u versus r graph, what is the slope over here? That is du by dr. du divided by dr. Call this as equation first, call this as equation second. Okay, see. Here force is equal to du by dr. Here du by dr is equal to slope. Can I say force is equal to negative of slope? Transfer this over here. Or slope is equal to negative of force, or force is equal to negative of slope. So I can say from equation first and second. So can I say force is equal to negative of slope? Yes. Means from this particular graph, if you want to find the force, you have to find the slope. You will be able to find the force. Okay. Now, guys, let me talk about positive and negative slope. Let's suppose the graph is this. If theta is less than 90 degrees, angle of this line with the x-axis, always remember slope is positive. What is slope? Slope is how steeper the graph is. What is the inclination? So more slope, less slope, less slope, less slope, no slope. Okay. Now, if the graph is something like this, means theta is greater than 90, less than 180, less than 180, greater than 90, 180, less than 180. In that case, we say slope is negative. Slope is negative. Now, look at the graph. Guys, see. I would want you to understand. We say from A to B. Guys, from A to B. Clearly, if you check the angle with the x-axis, it is greater than 90 degrees. So, can I say slope? Slope is negative. From A to B, slope is negative. If slope is negative, what will be the value of force? Force is negative of slope. So, force is negative of slope. Negative of slope. And slope is negative. You say force is negative of negative. Whatever be the value of slope, it is negative. Negative multiplied by that negative, force will be positive. force positive means force is repulsive. Force is repulsive. Now guys, understand one thing very carefully. This is what we call R is equal to 0.5 Fermi meter. Means from the left side A to B, graph is this. When R is less than 0.5 Fermi meter, matlab means this is the nucleon, this is a nucleon. Between the two nucleons, if the distance becomes less than 1 Fermi meter, like that is, if the distance becomes less than 0.5 Fermi meter, we say in that case, my dear friends, the potential energy graph is this. In that case, we say force is repulsive. So what I'm trying to say is that, so if R is less than 0.5 Fermi meter, we say force between the nucleons is repulsive. Yes. See, you have two nucleons. You say, sir, nuclear force is attractive in nature. They will attract, come close. When the distance becomes less than 0.5, now they start repelling. Why? The reason is, if they keep on attracting, they will collapse. This will become unstable. So that's why if they come more close to each other, it starts repelling. Now, if they try to go away, it will attract them. So that is the reason force becomes repulsive over here. Okay. Now, if you check from B to C, okay, can I say a value of R is greater than 0.5 Fermi meter? Yes. And my dear friends, listen to me very carefully. We can say, sir, slope is positive. Okay, slope of this graph will be positive. If you check the angle with the x-axis, it is always positive. It is always less than 90. If slope is positive, we say force will be what? Force will be negative. Okay, force in that case will be negative of positive. Force is negative of slope, so force will come out to be negative. What does negative force in this case mean? Force is attractive. Force is attractive. That's what I was saying. If the distance between the nucleons increase, this force will try to attract them. If the distance between the nucleons decrease, this will try to repel them. This is how system remains stable. If you ever get a question, nature of nuclear force, in this particular case, you always mark what? Attractive. Okay, you mark attractive. Because over there, they don't tell you it is, if the distance is this and that. Okay. Now tell me the answer of this question. Two nucleons are separated by a distance of 1 Fermi meter. The force between them is F1 if both are neutrons. They say if this is a neutron, it says that the net force between them is F1. Guys, the net force here is F1. The net force between them is F1. If both are protons, if this is a proton, then they say the net force between them is F2. This is F2. This is F2. And F3 if one is proton and another one is neutron. If one is proton and another one is neutron. This is what we call F3. This is what we call F3. Now tell me over here, guys, which option is correct? Which option is correct over here? Which option is correct over here? Tell me. D option. Don't you think option B is correct? Guys, see. Two neutrons. We said these two will attract each other with a nuclear force only. Okay, they will apply nuclear force only. So what is the net force between them? That is F1, and that is nuclear only. Okay. Now guys, we say in this particular case, proton and proton, they will each other repel each other with electrostatic force. Okay. And inwards is which force? Nuclear force. Nuclear force. Now what is the net force? Net force will be inward force minus outer force, outward force. So we say in this particular case, guys, please understand this. In this particular case, we say F2, that is the net force here, will be less as compared to F1. Why? Because here two forces are attracting only. No force is pulling in the outward direction. So F1 will be large. Here, the force which is inward, outward forces are also there. So here force will decrease. Here also there will be only nuclear force. Nuclear force. Okay. Like if I say this is 10 Newton. This is 10 Newton. This is 10 Newton. In the outward direction, here it is 5 Newton, 5 Newton. So how much is this? 10 minus 5. So only 5 Newton is acting inward direction. Here it is 10, here it is 10. So can I say in this case, F1 is equal to F3 is greater than F2. Now check. F1 is equal to F3 is greater than F2. Okay, next. If they ask you the question something like this, if FPP, FPN, FNN denote the magnitudes of nuclear force between a proton on a proton, by a proton on a neutron, by a neutron on a neutron, respectively. Okay, then we can say option B is correct. Then equal. In this particular case, equal. Why? Because they are talking about the nuclear force. They are talking about the nuclear force. Nuclear force between all remain same. But when it comes to this, here they were asking net force. Net force. Let's talk about Q value of the reaction. Let's talk about Q value of the reaction. Guys, see, what does Q value of the reaction mean? Let's suppose we have got a nucleus over here. This is the A nucleus, okay? And we have got one more nucleus over here, that is B nucleus, okay? So it is like A nucleus is fused with B nucleus. A nucleus is combined with B nucleus, like in fusion, okay? And they form C nucleus plus D nucleus. A and B nuclei are fused or combined together, they form C plus D. And in this reaction, we say some Q, some energy is either absorbed or energy is released. We say Q is the energy absorbed or released. Okay, so this is what we call the reactant nuclei. A reactant nuclei. And these are what we call the product nuclei. These are what we call the product nuclei. These are what we call the reactant nuclei. So when two reactant nuclei are converted into product nuclei, in this reaction, either some energy may be released or some energy will be absorbed. Some energy will be absorbed. We have, this is the last topic, and after this topic, we have 4 or 5 questions. That's it. That's it. Till 3 o'clock, we'll finish it. Till 3 o'clock, we'll finish it. Okay. So we say when reactant nuclei are converted into product nuclei. Product nuclei. Some energy may be either absorbed or released, called Q value of the reaction. Called Q value of the reaction. Okay? Yes. And if somebody asks you how to find this Q value of the reaction, if somebody asks you how to find the Q value of the reaction, we can say this Q value of the reaction will be, guys, see, we say mass of reactants minus mass of products multiplied by C square. Okay. Mass of reactants is mass of A, mass of B. So that is simply mass A plus mass of nucleus B minus, we say, mass of C plus mass of D into, we say, C square. This is called the Q value of the reaction in terms of mass. If we talk about in terms of binding energy, what is the Q value of the reaction? We say Q value of the reaction in terms of binding energy is, guys, see, it is binding energy of products minus binding energy of reactants. Okay? Directly, don't multiply C square over here. Okay? So you can say this Q is binding energy of binding energy of C plus binding energy of D minus binding energy of A plus binding energy of B. Binding energy of B. This will be the Q value of the reaction. Now, one more thing I just want to tell you over here. We say if binding energy of products is greater than, binding energy of reactants, if binding energy of products is greater than binding energy of reactants, in that case, what will be the value of Q? In that case, what will be the value of Q? We say Q in that case will be positive. Okay? Okay, Q in that case is positive. We say Q in that case will come out to be positive. See, guys, if I say binding energy of products is greater than binding energy of reactants, if I say this is 10, this is 5, so 10 minus 5 is plus 5. So Q will be positive. Q positive means energy is released. Energy is released. Released in the process. Energy is released. And it's an exothermic process. It is an exothermic process. Okay. Yes. As simple as that. Next, if binding energy of products is less than binding energy of reactants, in that case, Q value will come out to be negative. Sir, how? Because I am saying if this quantity is small, this quantity is big, small minus big will be negative. So that means energy is absorbed. Energy is absorbed. Okay? If energy is absorbed, we say it's an endothermic. It is an endothermic. process. Okay, great. Let's talk about this question. Let's talk about this question. In a nuclear fusion process, energy is released. Then binding energy greater than, equal to, greater than, less than. Guys, see. We say if in nuclear fusion process energy is released, we know if energy is released, guys, we recently saw what will be the Q value. Q value will be positive. Okay. Q value will be only positive if binding energy of products is greater than binding energy of reactants. You see over here, recently you saw, if binding energy of products is greater than reactants, Q is positive, that means energy is released. So we say in this question, binding energy of products is greater than reactants. C. This one, in a fission process, nucleus A divides into B and C. This is nucleus A. It divides into B and C. This nucleus is B and this nucleus is C. Their binding energies are EA. It has got the binding energy EA. It has EB. It has EC. Then, guys, tell me one thing. This is a fission process. Don't you know that in fission process, energy is released? I told you. Energy is released means Q is positive. If Q is positive, we say it is only possible if binding energy of products is greater than binding energy of reactants. So binding energy of B plus energy of C is greater than energy of A. Tell me which option. B plus EC is greater than EA. Option B. This is by learning the binding energy concept. If by this Q value of the reaction, if you understood the concept, you can solve these types of questions very easily. Next, the binding energy per nucleon of 3Li7 and 2He4. Guys, reaction in this case is given as 3Li7 plus 2He4. It gives 3Li7 plus 1H1 plus 1H1 gives, it is actually 1H1 and here it is He. 2He4 plus 2He4 plus Q. And you are supposed to find the Q value of the reaction. This is the process, guys. This is the reaction. What will you say? Simple, sir. Binding energy of products minus binding energy of reactants. As simple as that. Now, the binding energy per nucleon of 3Li7 is this much. Means when you talk about 3Li7, it says that its binding energy per nucleon is given as 5.60. How do you find the total binding energy? Sir, total binding energy will be multiply this. Sir, this is 5.60 multiplied by A. Because this is the binding energy of one nucleon. Binding energy of all the nucleons will be 5.60 multiplied by all nucleons. And for this, what is the value of A? That is 7. So binding energy here will be 5.60 into 7. This is called the binding energy, total binding energy of reactants. Guys, I'll write over here. It is binding energy of products. Guys, see, product is this one and this one. It says binding energy per nucleon of 2He4 is 7.60. Means, in order to take out one nucleon, of 2He4, how much energy is required? 7.60. How many nucleons are there in total? 4 plus 4 is 8. So 8 will have how much total binding energy? We say it will be 8 into 7.06. I hope you understood this. Sir, one nucleon has got this much binding energy. Total are how much? 8 nucleons will have 8 into this binding energy. Forget about this. Direct, apply direct. Then we say minus. Binding energy of reactants. Sir, this is the reactant. In the reactant, it says binding energy per nucleon of 3Li7 is 5.60. Means one nucleon of 3Li7 has this much energy. 7 will have how much? 7 into 5.60. Sir, why didn't you write for 1H1? Because 1H1 means it has got one mass number. What will you You can separate 2. How can you separate 1? Okay. Now solo this, Q will come out to be 17.3 MeV. I hope this is clear. Next, the binding energy per nucleon for a deuteron and alpha particle are X1 and X2. Okay. Your reaction is given as 1H2 plus 1H2 gives 2He4 plus Q. 2He4 plus Q. Okay. Okay. Now in this particular case, guys, you are supposed to find the value of Q. How do you find? Binding energy of products minus binding energy of reactants. So you say Q is equal to, guys, tell me, binding energy of products, binding energy of products. See, binding energy of product. Helium in reactant. Helium is not in the reactant. Bro, I told you this is 1H1. And this E should have been over here. Helium is here. Helium is not in the reactant. It is 1H1. It is a mistake. It is a mistake in the question. Now see, we say binding energy of products 2He4. We say binding energy of alpha particle is X2. Means binding energy of one nucleon. Binding energy of one nucleon of this alpha particle is X2. How many nucleons are there? 4. 4 will have how much binding energy? 4 into X2. Simple. Then we say minus. We say reactants. Guys, in case of reactants, how many nucleons are there? 2 and 2. 2 plus 2 is 4. Okay. So binding energy per nucleon of deuteron. This is called deuteron. 1H2, 1H2. Deuteron has binding energy per nucleon as X1. This is for one nucleon. How many are total? 4. So 4 will have how much? 4 into X1. Simple maths, bro. Class 8th maths. Okay, take 4 common. It will be X2 minus X1. 4 into X2 minus X1. Simple maths, simple maths. Okay, tell me about this. The mass of 3Li7 nucleus is 0.042 U. The mass of 3Li7 is 0.042 U. This is AMU. We say mass of nucleus is given as mass of nucleus is given as 0.042 AMU. Okay. The binding energy per nucleon of this will be, okay, first mass is given. Guys, mass is given. Forget about binding energy. Binding energy per nucleon. Let's find binding energy first. If this much is the mass, how much is the binding energy in this mass? We say, sir, binding energy will be simply, that is m into c square. Okay. What is m over here? 0.042 AMU into c square. Guys, if you remember, I have told you this AMU into C square. This AMU into C square. See, I'll show you over here. I'll show you over here. What is the value of 1 AMU into C square? 931.5 MeV. That's why I told you over there it will help us. 931.5 MeV. So I can say in this particular case, this will be 931.5. Okay. It will be 0.042 instead of this AMU into C square, 931.5 MeV. Now guys, see, consider it 1000. Okay. We'll change it later. Consider it 1000. 1000 multiplied by 0.042, it will be 42. 42 MeV. So this is the total binding energy total. But we have to find the binding energy per nucleon. Guys, this is the total binding energy present in this nucleus. Total. And to find, my dear friends, to find, we say binding energy per nucleon. Now, binding energy per nucleon of 3Li7. So what will you say, sir? That is total binding energy is how much? Total binding energy how much? 42 divided by 7. It will come out to be 6. But here we took it approximate 1000. So 6. So answer should be 5.6. Because we took here approximately 1000. That's why it came 42. 42 divided by 7. So answer should be less than this. Why? Because we took here 1000. Okay. Is this clear? The binding energy per nucleon in a deuterium and helium are 1.1 MeV and 7.0 MeV respectively. This is the J means previous year question. When two deuterium nucleus fuse, that is 1H2, two deuterium nucleus fuse, 1H2 plus 1H2 gives, to form the helium nucleus, gives 2He4 plus Q, and the energy is released, that is Q. And we are supposed to find the value of Q. Guys, again, value of Q is equal to, tell me one thing, it is binding energy of products minus binding energy of reactants. Okay, so we say Q is equal to, Q is equal to binding energy of products minus binding energy of reactants. Okay, so I can say when it comes to the binding energy of products, guys, product is this. The binding energy per nucleon in deuterium and helium are 1.1 and 7.0. Guys, binding energy of one nucleon of helium are 7.0. But how many nucleons are over here? 4. So 4 will have 4 into 7.06. 7.0. 4 into 7. 4 into 7. Okay. Then we say minus binding energy of reactants. Reactant is what? Deuterium. So in deuterium, how many nucleons are there? 2 plus 2 is 4. And what is the binding energy of one nucleon? 1.1. So 4 into 1.1. Okay. Okay. So answer will come out to be 23.6. Okay. 23.6. Is this clear? This one I'll give you as homework. And one more thing I just want to show you. This question. Look at this question, guys. Look at this. Binding energy per nucleon versus mass number curve is shown as in the figure. Okay. Binding energy per nucleon versus mass number. The process that would release the energy C to D, A to C plus D, B to C plus D, A to C. Guys, see. If I say C to D, let's talk about first C to D. If you move from C to D, so what is binding energy per nucleon? Binding energy per nucleon is stability. So while you are moving from C to D, tell me what happens with the stability. Stability will decrease. If stability decreases, guys, if stability decreases, we say energy will be absorbed. Energy will be absorbed. So this is the wrong. This is wrong. This is incorrect. We have to check in which process energy is released. Here stability is decreasing. Energy will be absorbed. When stability increases, energy is released. Okay. Now, my dear friends, we say, sir, from A to C, if you move from A to C, in this particular case, you are moving towards here, this is stability, here, this is stability. You are moving towards stability. So energy will be released. Yes, this is A to C. It is A to C to D. A to C to D. It says that from A to C, then C to D. Again, from A to C, stability will increase. Then from C to D, stability will decrease. So, no. B to C plus D. It says from B to C, yes, stability will increase. And then from C to D, stability will decrease. Again, so energy will be absorbed again. So, no. So, we say on moving from A to C, stability increases. So, energy is released. Energy is released. So, ladies and gentlemen, that's all for today. Thank you so much. Do let me know in the comments later on how was the session. Did you like it or not? Everything. Okay. Done and dusted. Thank you. Okay.